What if we could start now?
Okay.
Thank you.
Yeah. So welcome back, everyone. So for the invited talk this session, it would be from Jerry McLean, who is a staff research scientist at Google Quantum AI. He has worked extensively on building a better understanding for using near-term quantum computers for tasks like quantum material science, as well as machine learning. In particular, one of his works on Barren Plateau has opened up a new field where people utilize quantum information tools to study the trainability of quantum neural networks. So today, he's going to tell us about the power of data and simple methods for assessing the possibility of quantum advantage in learning. So please start, Jerry.
Great. Thanks so much for the introduction, Robert. It's rare to have the privilege of giving a talk where the chair of the session has done a lot of the technical work you're about to present. So I'm going to defer all tough questions to you. So yeah, I'm happy to be here today to talk about a project that changed a lot of my mind about not just quantum machine learning, but also kind of my views on the way science is done in general. And I hope to share some of those exciting technical results with you, as well as a bit of philosophical musing that I hope you'll find interesting about the way in which data and machine learning fit into the way that we do science more generally. So we all kind of are familiar with the couple application areas that are often thrown out as useful for near-term quantum computers and perhaps fault-tolerant quantum computers as well, depending on the details. And they're ones that often track very closely with things we would think of when we think of machine learning, including optimization, so maybe better ways to train our models. But what I'm going to focus on today is more how does it influence our conception of machine learning, or more broadly data that we take into a system, process, and then try to do useful work with. And I'm going to argue that maybe that's a little bit more connected to quantum simulation than we might have imagined. And maybe each of these two can tell us a little bit about the other. So I'm going to imagine for a minute, so you don't need to be a chemist to understand this slide, that we're living in a world where maybe the past few hundred years of chemical research haven't been done, but someone gives us the governing equations for how molecules move around, how they react, and things like that. And so I'm going to try to do chemistry without knowledge of what I would call theoretical chemistry. So someone gives me some set of reagents or reactants. These are my input chemicals. They give me a bunch of jars. They give me an infinite supply of these things and some other tools to mix them and portion them out. And I know there's some chemical that I want to make on the other side. And maybe I would like to ask questions like, how long does this reaction typically take? Or does this ever happen at all? And without knowledge of chemistry, but knowledge of these equations of motion of the universe, I can sit down and create an instance of these molecules in some kind of computer simulation. And I can step forward in time and try to do what I can to move things forward and watch things evolve. So the next step is, of course, wait. And perhaps I end up waiting for a very long time. And then maybe I see or don't see that product, but what can I really say about the system at that point? And so you say, okay, well, you've suggestively written the time-dependent Schrodinger equation here. So chemistry is obviously a very quantum phenomenon for many of its reactions. And we know that quantum computers are very, very good at that. So what can we say about what is now enabled with a quantum computer, given that I'd like to do chemistry without knowing chemistry? And interestingly, before we have quantum computers, we have learned something from results in quantum computer science about what's possible and what's not possible for our simulations to handle. And if I imagine that I just have some molecule or backbone governed by a Hamiltonian, and I want to watch a charge move across a system such that I'm going to simulate that with a quantum computer, and it's a great tool for the job. We've made rapid advances in our ability to do this. I think every day I feel like I see some advance in bringing the cost of quantum simulation for various systems down by optimizations or system-specific tricks or things like that. And we've gotten very, very good at this to the extent that numerically exact evolutions are often sublinear in the number of discretization points that we're interested in. So this is something, of course, that we think the exact classical competition is very, very hard for. It tends to hit a hard exponential wall for the most interesting systems, and entanglement truncation for this problem of strong dynamics seems to be quite hard. And so you might say, well, what can a quantum computer do if it's exponentially faster than a classical one? Well, it turns out that even a quantum computer has limits. So this is kind of a caricature of this no fast forwarding theorem that I'll use here, but it basically says the simulation time of some interesting physical system done to very high fidelity is always greater than the physical time it would have taken. And so if I'm sitting there in my chemistry without chemistry simulation, and I'm trying to study like a rust reaction, and that takes hours in real time with 10 to the 23 molecules, and here I am with a single one propagating it, I'm probably not going to see that reaction happen. So what does that mean? Can we not use quantum computers to study reactions? So you sit there for a second and say, but wait a minute, that's not exactly what people usually propose when they talk about chemistry. I'm used to seeing this slide and this canned quote about how chemistry is completely known and quantum computing is about to solve it. And so you'll notice a slight difference between what I've written before and what I've written here is that I've written the Schrodinger equation in this time-independent form. And so you might say quickly, well, why is this a useful perspective? And shouldn't this Hamiltonian as input in some initial state be roughly the same amount of information that's contained in the other perspective? Why are they in some sense different? And the reason is sort of that while this one is limited to physical timescales, I can often use the ground states of my system and the low-lying excited states and the observation from my physical world that the world is not actively on fire. So perhaps the lowest of these excited states are the most interesting. And then I make another hop, skip, and a jump to say thermodynamics is predictive of longer time behavior that I care about. So this T goes to infinity limit is relevant to this T much, much greater than 1 that I actually care about. And this allows me to, in some cases, make predictions on timescales much longer than physical. So what I've done is I've incorporated some amount of knowledge about my world that was hard to bake into these equations without exiting my math cave in order to figure out how I can do more effective simulations. And of course, it can't be better for all systems because of some complexity theoretic reasons. But this kind of gives you a hint of this perspective that I'm trying to get at, that data helps influence what we do and simulate about the physical world, and that knowledge can change our ability to address interesting problems. And so I won't belabor this point, but of course, this type of perspective is what leads us to be able to take some physical molecule, break it down into have what we term understanding. So we build up physical models from data we collect and patterns, and hopefully use that to control the physical world. So that might lead you to ask a question like, well, if these thermodynamic models are so much more predictive, so I can compute a single number about some isolated system, and it tells me something interesting about a time limit that's much, much longer than I could ever access without that knowledge, can I do this for almost anything that I would be interested in? This is the subject, obviously, of a large part of quantum simulation, is to look at these eigenstates. And so you ask yourself, can all physically interesting questions be answered by some reduced model? And interestingly, quantum computing has given us some answers here as well, whereas you might ask a related question, does a system ever thermalize? Does a system have an electronic gap? Or will molecule X ever form from constituents Y? And it turns out that these problems fall into this interesting class of undecidable. So meaning, I'm not going to go into an elaborate definition, but perhaps for this audience to borrow a physical one that I think is very telling from Chris Moore, which says that as the system evolves in time, there are sudden qualitative changes that cannot be predicted in any way except evolving forward in time and seeing if it happened, and no answer in finite time can ever tell if it happened or not. And so you might say, okay, that sounds very interesting. It sounds like a lot of phenomenon that we see, like the emergence of life, but why are you telling me about that? That seems like a rather depressing perspective. And I think I'm telling you that because of an interesting idea that undecidability can formally be broken by advice, which of course requires infinite time pre-computation. So we don't think we're getting actual advice in here. But it will turn out that data is a restricted form of advice. So this is a perspective by which you can view how the data you gather from the real world helps to empower your computations or your work to do more than you could with simple forward computation. And so let's take a step towards actual learning with variational algorithms. This will move a little bit away from the more philosophical points towards the results that we're interested in. So of course, a lot of people here are familiar with the kind of concept of variational algorithms in their original conception, kind of mapping an eigenvalue problem to a ground state minimization and iterating until you do better and better on some objective where you use a quantum computer to hopefully represent probability distributions that are hard to do classically. And of course, this has now touched a lot of domains in chemistry, physics, machine learning, and optimization. And just to kind of quickly remind people that haven't looked at this so much, what a sketch of that might look like. This is kind of an oldie but a goodie, and I like it because it shows you the translation between software and hardware fairly easily. At the bottom, we of course have our quantum circuit diagrams that we read like music notation from left to right. As we hit some operation, it becomes a lookup up to the hardware on the top where we perform some other operation. At the end, we have a prescription of measurements that we do, and this gives us our objective value. And you can see my one tunable parameter here in the middle, and that allows us to adjust and update and learn what we can with such hardware. And so we've, of course, moved a little bit beyond that, and I'm going to highlight one circuit in particular. You might be worried that I'm saying a lot about chemistry. Don't worry, I'm going to pivot away from it soon. But I think this will be a particularly interesting connection for the machine learning aficionados in the audience. In particular, we did a follow-up experiment more recently to prepare eigenstates of this system of kind of chains of hydrogen, basically, which is an interesting kind of model system that you can pull apart. And we specifically studied something called a Hartree-Fock approximation. And so this is a system where we're going to use n qubits, but it's very explicitly a mean field state. You might think of it like a fancy version of naive Bayes or something like that if you're more from a machine learning background. And we're going to choose this circuit because it's a nice primitive and because it has this sort of exponential redundancy in it. So it forms on this very small manifold in the overall space, and it's one that we can efficiently simulate, we can learn properties of, we can see where our errors are because we know literally everything about this system as we go up to larger and larger sizes. Even if we got to sizes we couldn't simulate a real hard circuit classically. And so we chose this circuit, and I'll just have you remember the general structure. The details of the gates aren't super important other than to know that putting all of these together makes something that is efficient to simulate classically and is kind of a nice sub-manifold of the set of all states. And one thing you can do, of course, with that redundancy is check a lot of the errors that you might fall victim to and kind of project yourself back into a space to do a more interesting simulation or really just analyze the errors that you might have there. But for the purposes of this talk, I just kind of want you to remember what you saw here, essentially. And I think this perspective of quantum circuits as neural networks is one that many people at this conference find very near and dear to their heart. Of course, making connections with the classical literature and the classical expertise that comes with our knowledge of neural networks or deep neural networks, I think is a very valuable tool. And we've already seen some nice connections, for example, gradient vanishing problems or other ways to train our networks through stochastic gradient descent, acceleration methods, and things like that. And one connection that I'm particularly interested in is, of course, connections to networks that look closer to quantum than perhaps the other ones do. And so one enticing connection you might find in the classical community is in this subfield called unitary neural networks. So of course, classical deep neural networks, if you're not careful, can have vanishing gradient problems of a slightly different origin than the ones that we see in barren plateaus, but they persist nonetheless. They're often to do with depth. And so if you imagine you would like a very, very deep neural network, and you would like it to be maybe even infinite depth formally in some kind of recurrent neural network, you might appreciate things that don't decay or explode as you apply them repeatedly. And this led a few people in the field to look into these so-called unitary neural networks, and after that, efficient unitary neural networks. And it turns out that the efficient unitary neural networks are, of course, built from this unitary nonlinearity piece. And if you zoom in a little bit and look in at what's going on, that unitary piece, in fact, it's actually the efficient unitary piece, which was a slight modification, is exactly these free electron rotations of the Hartree-Fock wave function that I showed you before. So in fact, I don't know that the connection was noted in the papers, but these are kind of these free fermion rotations form the exact sort of same structure. They're decomposed into Givens rotations in the same way when we compile them to quantum computers. So they're in very same sense the same. So you look at this thing and you say, okay, here are classical machine learning experts who have made a performant network that already contains a piece of something that looks very much like a quantum primitive that we use, but it's a quantum primitive over n qubits that we force to be classically easy, and also one that we know how to systematically expand into the entire space. So this seems like it presents a wonderful opportunity to spice it up with a little quantum and do much better than anyone can do classically. So let's give that a whirl. So we're going to boost the power with quantum computing. Is everyone ready? All right. So the classical case takes n inputs and has n outputs. So a natural choice in this fermionic picture is, for example, to encode in particle number or to spread a single particle across n modes. And then we're going to put this into our quantum circuit. And I'm going to track down here the effective dimension of this problem. So far it's n, like the number of modes, roughly speaking, because I can efficiently simulate that. And then I'm going to make some particles. Then I'm going to interact them. And I'm going to loop this kind of rotations and interactions over and over again while making some particles. And it doesn't take too long to show yourself that this is essentially a universal quantum circuit. You can do anything you want with it. And now I'm going to come out the other side. I'm either going to destroy some particles or measure them down, and I'm be back at my effective dimension n. So I'm gone from the input dimension n to output dimension n. I can plug this in that thing that I had before, and I've wildly boosted the power with this very hard to simulate circuit in the middle that's in principle quantum universal. So I must have expressed some wild class of functions that no one can match, right? Right. So just before we take that perspective, though, let's let our model have a little bit of data as a treat. So I put in some data, which is just specified generically as my inputs xi, my outputs yi. And I'm going to encode that data into a quantum state in its amplitudes as follows, where I've changed n to p, just to keep you on your toes. And I'm going to let my outputs be defined by some arbitrary length quantum circuit and some Hermitian observable. And if I make my circuit have some ancilla space and make this an arbitrary map on the ancilla space, this is basically any function of a quantum computer that I would like. And direct simulation of this has to be at least as hard as BQP. And I told you it was arbitrarily long, so it might be even more powerful than that. So you have to imagine that I've done something incredible. And so just before I make that claim, I'm going to go look at what that observable actually looks like. And I'm going to zoom in and I'm going to expand it out. So I lump all the complexity of my giant quantum neural network or quantum function into these coefficients B, KL. And I notice something, which is despite all of my wild computation, this is at most a quadratic function with p squared coefficients, where p was probably kind of modest. And so in a general learning theory sense, I only need about p squared over epsilon squared pieces of data to learn this function rather well. So what's happened here is that with no data, I have an arbitrarily hard quantum circuit. And with data, I have an almost trivial learning task if I've set my problem up that way. And of course, this is because of the encoding that I've used that rigged things in a little way. But you might start to worry, well, when else does having data change the complexity of my problem? When do I have to worry about this? And so this is kind of the work that we proved in this paper, that this is a meaningful separation. There is a class that is this sort of BPP SAMP class that shows you that having data present, especially if that data came from a quantum computer, has the power to elevate you in some cases above what simple classical computation would be and make some of those problems easy. And of course, this has some connection to the advice class, but in this case, we imagine really collecting data from the world. And so you might want to say, well, I'd like to be able to diagnose when this happens. and when I might fall vulnerable to this. And this is some of the work that we did in this paper, which I'll dive in a little bit now on, not specifically on the details of this chart, but a few highlights, and I'll leave it up to you to read the rest. So to do that, I'm going to take a brief detour into quantum kernel methods, which are a nice, powerful method for essentially evaluating the function you'd like on a quantum computer. And in case you're not as familiar, we want to take advantage of the fact that there are high-powered, good machine learning methods that really only require some pairwise proxy for the geometry, so some similarity measure, which we'll call the kernel. And once you have that, you can plug it into all of these existing methods and be successful. And so just to give you a refresher, this kernel can sometimes be a relatively easy similarity measure that implies some very interesting and possibly even infinite dimensional map into a linear space where you then do the bulk of your work. But importantly, all you really needed was that kernel similarity function. And just to kind of show you how sensitive that similarity function can be, if you're coming from quantum mechanics, I think it's sometimes surprising when you see this very slight difference, makes kind of a big deal, is that if you have this kind of quantum kernel, which you might find most natural to you, which is to take the overlap between two pure states if you've encoded them, this implies this linear feature map here, which then if you try to predict something like that quadratic term on the last slide, you find that you miss the cross terms and you're fairly unsuccessful in the general case. Whereas I make the tiniest modification, I still do these same inner products and make this kernel matrix, but now I do something like square the element-wise entries. And this is what gets us to this original quantum kernel paper by Havlicek and co-authors. And you find that the feature map, in fact, naturally includes the cross terms. So learning in this linear space becomes well-behaved, it functions very well, and everything succeeds. So that just tells you how a tiny, subtle change in the kernel can make a big difference in the power of your function, especially in quantum computing. So let's now set up a model that we can break down a little bit more and understand. So I'm going to have some model where I have input data, xi, and this could be my initial state or a Hamiltonian or general data. I'm going to use that in this encoding map on some initial state. And then I'm going to use some function that defines my dividing surface. So this will just be the function to be learned on this data, and I'll build it out of this encoded state. And so this could be like a magnetization or transition probability or something like that. And I'm going to have some data and the function values that I'd like to learn. And some fun observations that I believe have been made a few times is, of course, the quadratic quantum kernel is invariant to this choice of the dividing surface. And of course, this is kind of manifestations in a way of these representer theorems and other nice things that come attached to kernel methods. And let's take for a second, though, this similarity measure that I've written down, which is strongly related to the fidelity of two quantum states or two input states. And if you think about what fidelity is for example, data encodings that are very natural to us as people. So imagine you have a bit string, and two of these bit strings differ by a single bit flip. Under a fidelity metric, if I now flip 2 bits and flip 3 bits and flip 4 bits, these are all just as far apart from each other. Whereas intuitively, we might feel that that's not true. You shouldn't be able to flip a single bit and have that be just as far as n bits or some generalization in the x and z basis. And how this manifests in kind of these other studies is that as you scale the system size up, you find that there's some very sudden drop off where everything starts to look like it's equally far apart. And this has sometimes been called a Van Vleck catastrophe in chemistry, which is to say, as your wave function tiles together, even very, very similar things fall off exponentially. It becomes very difficult to specify things under this metric. So we're kind of advocating for more, and I'll be a little bit more specific about what this is, perhaps local successive fidelity approximations or measures that could converge to the fidelity if you wanted them to, but in the regime that you use them, take advantage of things like these intuitive notions of distance that would come from classical or local systems. And so this kind of inspires, in a way, the creation of a projected quantum kernel, which is one that, if you remember the original quadratic quantum kernel, something else that we can do is instead work with these local surrogates. For example, if we take the one particle reduced density matrix that we have for every single one of these qubits, and then define our distance on these, it's a handy thing to work with for a number of reasons. In part, the quantum queries scale linearly in the number of data points rather than quadratically, so you still have to do it offline. But the other is it becomes very easy to spice it up with the power of something like a nonlinear kernel, like what you do classically. There's actually a generalization in the appendix that uses a classical shadows formalism that interpolates between the low order RDMs and the high order ones. But in fact, even the low order ones tend to work fairly well. And I think there might be an interesting connection here to, say, density functional theory, where we know even low order, or even the density, is perhaps universal for reproducing the functions we would like. But that is just to say that we define some similarity measure that is evaluated with a quantum computer that has this nice property of kind of giving you an intuitive feel of similarity that goes from 0 to n spins in either basis. And we can spice it up with this kind of exponential function so that we can learn more interesting functions. And I think the central result in sort of understanding how then we can talk about prediction error on these systems is that I'm going to reference this kind of basically data distribution, which I'm going to draw some amount of data from. I'm going to have a model that I learned. In many cases, this will be my kernel model, and some form of truth. And we can essentially bound this using these learning theory type bounds that tells us that this error is going to go down with some central quantity that I'll tell you about, and the number of training samples that I take. And so already, if you're looking at this, you can say that, well, if the dependence on this similarity measure isn't too strong with n, then essentially there's going to be a number n for which my learned method is always going to catch up to whatever competition it has, whether it be classical or quantum. And intuitively, this quantity, this SK quantity, is telling me that when the function values are close, the similarity measures are large. And for example, this is just kind of the construction in the paper. But can we say something a little bit more general, kind of a little bit quicker? We can talk even about, once I've chosen some embedding, I can tell you something about all possible kind of quantum functions that I can use, or all possible label functions that I'm trying to learn. So interestingly enough, we can take that previous element and bound this work, and this gives us some measure of if I have a quantum kernel with its embedding that I think is going to do very well, and I have another classical kernel, this quantity that's bounding my prediction error, telling me about my prediction error, can be bounded by this geometric similarity measure between the two. And importantly, if this geometric similarity measure is small, that means that this classical function can essentially do as well as my quantum embedding on any possible function. And that basically means I should be using classical. And of course, if it's large, there might exist some function where quantum has the edge, though my particular label function might not. And of course, this doesn't say something about all possible classical or all possible quantum, but this gives you a very useful tool. Say you've written down some embedding for your quantum circuit, and you wish to embed that data and check if this is going to be a useful way to classify that data. So you conjecture what your quantum kernel should be, and then you go back to your classical computer. You write down a few models like a squared exponential, all of your favorite classical kernel methods competition. You screen through them quickly, and if the data was somewhat regular, your quantum embedding wasn't so interesting, you often very quickly find that one of the classical methods has a very small GQ or GCQ, and this means that essentially that quantum embedding, even if it was hard to compute classically, is not going to be useful for beating classical on this set of functions. And this gives you a very simple way to check and evaluate whether, once you've imbued this type of problem with data, whether it actually matters if your quantum circuit was hard or not. And so there is, interestingly, a simple method that exists to create a label function that saturates this bound. And it's a good way to kind of study which functions might be amenable to this type of separation. So let's go on to perhaps how well it works in practice. So we're going to do some numerical studies, and for that, we're going to need some form of data source. So we start with the fashion MNIST data. We pop it in, as is often done in the literature, to a PCA to reduce it to n components that I'm going to use on n different qubits. That's going to give me also a length n vector is what I will feed my classical machine learning algorithm. And so that will be my data. And I'm going to choose a series of embeddings. So recall that I have some amount of choice in the way that I put my data into a quantum computer. And we saw earlier that an amplitude embedding was a kind of very trivial way of doing that. But let's explore the more general ones. And I'm going to take something that's not as trivial as an amplitude encoding, but is still pretty easy. It's obviously classically easy, which is separable rotations for each of the qubits. So this is obviously classically simulatable, but it gives me a good baseline for what this type of embedding would look like. I can make it a little bit more quantum to moving something like an IQP circuit. So this is one where expectation values are still probably easy, but sampling is hard. And so it's kind of like a little bit quantum. And then I can move to something that's kind of contrived and very quantum, which is a Heisenberg model done in what you would call a very coarse trauterization, where the idea here is really to induce strong correlations in the system that would be difficult at scale to simulate classically. And so now I can say what label functions I'd like to learn. So for example, if I'd like to learn the original classical MNIST labels, that's one option. Or I can tip the scales in favor of quantum a little bit more, and you'll see why I have to do this in a minute, where I'm going to learn some interesting U, Q, and N functions. So it's kind of like a very quantum function, and the output of this on some qubit that I select. But importantly, this function already contains a bit the data encoding that I've put my problem into. So it tips the scales towards quantum a bit. And of course, the most stilted thing I can do is use that method that I mentioned to saturate and make the hardest possible function to learn, meaning the biggest separation between quantum and classical. And as classical competition in the next few slides, it will be some buffet of methods where many were tried and the best one was selected in each case. And that will be an assortment from Gaussian and linear SVMs, random forest, neural networks, gradient boosting, etc. And let's go ahead and examine this first metric that I said was interesting. So let me just break this figure down a bit. So this, as I mentioned, as I'm increasing the amount of data, I'm increasing the number of qubits at the same time. So this x-axis is number of qubits and also components of the PCA I'm embedding. This G is that geometric difference quantity, where I mentioned that having a very low number means classical is probably a better choice, or at least as good. And at the top, I've labeled the embeddings E1, E2, and E3. And the basically Q is the original quadratic quantum kernel that's based largely on the fidelity, and PQ is this projected quantum kernel based on these 1 RDMs with a squared exponential in them. So already you can kind of see that as you go with this most quantum, sorry, the red should have been E3, you have some kind of turnover effect where the fidelity, even evaluated in double precision, starts to drop off and you start having to make very hard choices about memorization versus not, but the projected quantum kernel stays reasonably away from the baseline. And this kind of maps directly to performance on actual label functions. Remember, this geometric difference is something that applies for all possible label functions, whereas I might be interested in specific ones over here on the right. So over here on the right, I'll just kind of give you a brief summary of what's going on. Essentially, in the classical data set, we have something where basically projected quantum kernel manages to mimic more or less. So in these cases, prediction error is what I'm measuring, or classification in the classical side. And in all cases, lower is better. The classical methods do extremely well, where here I've now had the best classical in this color that you can see. So those do extremely well, to the point where you probably don't really desire to use a non-classical method, so that makes sense. And then we may start to make things a little bit more quantum. So we remember this E1 is a separable encoding, so it's not that quantum. And true to form, classical essentially matches the quantum one and the projected quantum one. And this is even in the case where the projected quantum and quantum have knowledge of the kernel in some way. So we make things a little bit more quantum with E2. We see that the kind of fidelity-based metrics right around the turnaround point for where you start to get memorization still continue to struggle beyond a few qubits, but you kind of match the performance with the projected quantum kernel. And finally, we make it very, very quantum with these Heisenberg evolutions, and you start to see a bit of separation. But you look at this and you kind of remember that, well, this was for some particular amount of training data. And a core part of this argument of the power of data was that if I added a little more, this gap might well close. So as not to be satisfied with these, we put our hands on the scale even more, and we tried to tip things in favor with these engineered functions. And so this is that case where we saturate things with respect to this bound. And so this is the biggest separation between these kernels that we can get for a particular choice. And so with this kind of not very quantum embedding, you can see that the separation between quantum and classical is basically negligible. And here we've actually plotted two sets of amounts of training data. So what happens if I have 100 data points or 600 data points? And you can see how much that moves the accuracy, where higher is better in this case. And you start to move over here. So you get a little bit more quantum and see some separation. And finally, with this very quantum embedding, you see that there is kind of a very there exists a label function where quite a bit of separation exists. So that suggests that there are at least some functions that we could look for, though where they would occur naturally is, of course, a big open question. And so I'd say I wanted to mention that I think it's very important for these numerical studies that kind of confirm theoretical results to make sure it actually works at a scale that you're actually interested in. So many studies, of course, drop out because of the expense of going beyond a handful of qubits. And in this case, we wanted to see if things were sort of getting better or dropping down as we got larger. And so to us, reaching 30 qubits was a very important benchmark to see that these methods continued to work as we increased the number of qubits, at least to the scale that we could get. But doing so is a bit expensive, and so I wanted to give a hat tip to Michael Broughton and TensorFlow Quantum for making these simulations work, where we reached a good petaflop per second peak and an exaflop of total compute to get these numerics out, which I think were pretty essential to supporting the message that this continues to work into slightly larger system sizes. And so in the last few minutes of my talk, I wanted to highlight a few more cases where learning is seeming to be getting a legs up. So this is kind of tailing back to the philosophy of machine learning as related to quantum simulation. So another paper that came out recently showed a very exciting result that in many cases, ground state properties were something that you could efficiently learn from data samples, even in systems you might view to be heavily entangled. And so from a chemical point of view, it's a little bit more discrete, but if these results naturally apply? And if we start to buy into this idea that basically we could take data from enough quantum systems and boost our classical learning that we would always be successful, do we start to ask if the fate of quantum computers in chemistry is to provide training data for classical models? So this would, of course, be a very useful way to proceed, but it's kind of an unexciting fate for one of humanity's most interesting modern technologies. And the same authors, one of which who happens to be the chair of this session, went on to prove a number of other results that I found fascinating that showed that there might be hope for these systems which can process copies of data from nature in interesting ways that in fact allow us to do things that without these kind of quantum computers to hold our models themselves, we might be exponentially disadvantaged against learning certain features of the physical world. So I think perhaps not all hope is lost with regards to that. So if we take another computational look at chemistry through this kind of lens of learning, I kind of mentioned that data from quantum computers seems to lift classical machine learning above its direct competition. What can quantum simulation data do for chemistry? What can it do for physical sciences? And what can these types of results tell us about machine learning with data as being distinct from more traditional computation? Many of the problems in things like design, synthesis, and biology feel like undecidable problems. What can we say about the way that data from nature actually helps us? And is the fate of quantum computers largely to provide data to classical machine learning? And I argued that I think that's not the case, and that there's going to be some more exciting results in the near future that tells us even more so. And so we took these like kind of wild perspectives and we condensed them in case you're curious about what we viewed these types of results in quantum computer science and machine learning as telling us about the physical world. And if you're interested, I would invite you to check out this perspective. I think it's an interesting change of pace from a quantum molecule goes into a quantum computer and gives you a solar punk utopia. I think it gives an interesting perspective on other ways it might inform our opinions about the physical world. And so just kind of in summary, I told you a little bit about this connection that I started to view between learning problems and simulation, and the way that we do effective simulations by not just running things forward in time blindly, but incorporating data even at the basic level of our models. I told you about this complexity separation that one can prove exists if you have data from a quantum computer that you can use to empower your classical models. And I told you about this kind of practical toolkit where you can at least quickly screen whatever embedding for, say, a quantum machine learning problem you like, and try to differentiate between the two and see whether the classical model is going to be always better that you've chosen or not. And I showed you how this sort of manifests in some numerics where we try very hard to tip the scales. But importantly, the story there is very often the classical machine learning equipped with data is competitive with even stilted quantum problems. So with that, I'd like to thank the people most involved in getting the hard technical work done, which includes Robert Huang, our esteemed chair, Michael Broughton for scaling up those simulations to unfathomable sizes, and the whole Google Quantum team for helping to enable this research, as well as all of you for listening to me. So thanks a lot.
Yeah, thank you so much, Jared, for the great talk. We have 4 more minutes for questions. I think Min has a question.
Oh, thank you, Jared, for the great talk. I have a quick question on the kernel, on the quadratic kernel. So does it make any physical sense to go beyond to this quadratic kernel? Like, what a polynomial kernel, we can go like quadratic kernel, for example. Does it make any physical sense to do so? Because we know a lot about like classical kernels. We know, I used to compute all the feature maps and so on about these polynomial kernels, Gaussian kernels, and eigenvalues and eigenfunction and so on. So we actually know a lot about these classical kernels. Like from a quantum viewpoint, does it make sense to go beyond it?
Yeah, I mean, my personal view is that it certainly makes sense to explore other kernel functions and see how well they perform. For example, as you were mentioning a whole litany of them, I would personally worry that especially fidelity-based metrics are very hard to get to high precision. And then if you had to square or cube or take 1 to the 4th power, you might end up needing a ton of measurements to get the precision that you're interested in. But that's not to say one could maybe split the difference. There might be some intermediate power where you don't pay so much, but certainly I think it's worth playing with. It's less obvious to me, though it might be obvious to someone, which new functions or observables that might directly enable by going to higher powers. But I think it's certainly a tool that people should play with.
Thanks a lot. Thanks a lot for the great talk. Very fascinating. Thank you.
I can actually also add on to that question. So basically, if you consider quadratic kernel, then you will be able to learn any observables. Consider quartic kernel, then you will be able to learn observables that acts on 2 copy of your density matrices. So for example, maybe you could estimate purity of your initial state and so on. So that's sort of the other things that you could learn, and that could potentially be useful. But as Jared said, there's also a downside to that in the sense that estimating this quartic kernel might require a really large amount of measurements.
Great, thanks.
Yeah, are there other questions? Okay, if not, I could ask one of them. Actually, Kwok have a question.
Oh, Okay. Thank you so much for very fascinating talk. So I think we are talking about the power of classical data in quantum machine learning, but I wonder that we assume that we have many type of quantum data. The data come from quantum state having some special property like entanglements or something like that. So, and I want to ask your opinion. That's how to utilize and how to use the property of quantum data in classical machine learning tasks. I mean, it is very different with classical data in basically.
Yeah, so if I understand your question correctly, maybe it could be viewed in two ways, and I'll try to get to both of them, and you can tell me which one is more right. One is if you imagine yourself empowered, instead of classical data, someone delivers to you directly quantum states that contain some amount of information. I think you can utilize the correlations and data that's there using methods kind of when one of the papers that I referenced towards the end, these information theoretic bounds papers. And I think you utilize the power of a quantum computer to be able to check correlations between them more handedly than you could otherwise. So things like Bell state measurements and things like correlations that you see between the states are things that might be very hard to access if you first destroyed the state and then kind of tried to reconstruct it from its classical images. And so that's one way in which you can, I think, very much exceed the power of classical machine learning to say something about very quantum systems, is if you can be delivered actual quantum data from the system. How exactly, maybe the second part I imagine you might be interested in is, can you then use that same power to enhance a problem in classical machine learning, but now using the power of like importing that data as quantum states? And I'm not sure, but I think it's a very interesting question. So.
Okay, thank you. Thank you so much.
Yeah, thank you so much, Jared. I think based on the time, we should probably go on to our next talk by Zoe Holmes.
Right.
So could you try share your screen?
I'm going to share my screen.
Yep, so Zoe Holmes is a postdoctoral fellow in Los Alamos National Laboratory. And today she's going to talk about barren plateaus, preclude learning scramblers. So please take it away.
Yeah, thanks, Robert. Thanks for the introduction. I really appreciate this opportunity to present this work to you today. So this is collaborative work done with Andrew Eversmith, Bin Yan, Patrick Coles, Andy Ulbrecht, and Andrew Sornbodger. Title of my talk is Barren Plateaus Preclude Learning Scramblers. Okay, so to sort of illustrate the result I want to share with you today, to sort of add a bit of color to it, I'm going to start by recalling the Hayden-Preskel thought experiment. So in this thought experiment, Alice attempts to destroy her secret diary by throwing it into nature's fastest scrambler, a black hole. And then the question is, well, how safe is Alice's secret? Could an observer, called Bob, of course, recover it? So this secret, of course, is encoded in a quantum state. So given that black holes are nature's fastest scrambler, the information contained in Alice's diary in the initial state is rapidly going to be spread throughout the entire large black hole. So you'd have thought that it'd be pretty hard to recover Alice's secret. But surprisingly, Hayden and Preskel argued that actually, if Bob knows the unitary dynamics implemented by the black hole and shares a maximally entangled state with the black hole, then in fact he can actually recover Alice's secret diary just by collecting a few additional photons emitted by the black hole. But then the question is, well, how the hell would Bob learn that unitary implemented by the black hole in the first place? And well, what we've shown is not using quantum machine learning. So more specifically, we've shown that any quantum machine learning method that you might try and apply to learn a scrambling unitary is going to encounter a barren plateau, and so you're not going to be able to learn your scrambler. Okay, so that's sort of the main idea, but before I get there, I'm going to have to introduce a bit of background. So what are scramblers, what are barren plateaus? So this talk will probably be, well, hopefully be reasonably pedagogical. Okay, first things first, what is quantum scrambling? Well, in broad terms, quantum scrambling is the way in which quantum information and entanglement can be rapidly spread through certain many-body systems. So it's, of course, very relevant to black hole physics, but it's also relevant to a wide range of other areas of quantum physics. So it can be used to understand how quantum information spreads through quantum channels. It's highly relevant to thermalization phenomena, the way in which systems rapidly become entangled with their environment and so start to thermalize. It's got close connections with random circuit theory. It's even got close connections with fluctuation relations in quantum thermodynamics. It's got connections with entropic uncertainty relations and many other things I just don't have space on my slide for. Okay, so quantum scrambling is important to a wide range of areas in quantum physics, but how do we diagnose it? Well, a good way of diagnosing quantum scrambling is through using out-of-time ordered correlators, or OTOCs. So a particularly natural one is this one that I've sketched on the right-hand side of the slide here. So this is just 1 minus a half times the expectation value of the commutator squared, where the commutator is a commutator between some local operator y and some time-evolved operator x tilde. So yeah, x and y are local operators. These could just be Pauli operators acting on different qubits, for example. X tilde is the time-evolved version of your initial x operator, working in the Heisenberg picture. So these evolution unitaries will typically be time dependent. So x tilde is also a function of time, so your OTOC is also a function of time. And then this expectation value here is just taken typically over an infinite temperature state. Okay, so at sort of time 0, x tilde is just equal to x, because v is just going to be identity. And your x and y are local operators, so they commute. So your OTOC is just going to be 1 because the commutator term vanishes. But if you're scrambling, if your unitary v is a scrambling unitary, then your x operator is going to be rapidly transformed into a global operator, and then it's going to stop commuting with y. So this commutator will become large, and so your OTOC will rapidly decay. Or more concretely, the OTOC of a scrambled system has been shown to rapidly tend to a minimal value that is equivalent to taking its average over a random distribution of unitaries. So this is a really nice and fundamental result, and I recommend you go into the Roberts and Ishida paper that I've put down there if you want to learn more about it. But this means that we can model a scrambling unitary as a typical random unitary, because typical random unitaries also have these rapidly decaying OTOCs. So that's what we're going to do in this paper. But before I go on, let me just sort of make a quick technical comment. So you'll note that this OTOC here only actually involves 2 copies of the evolution unitary v. So it only involves up to the second moment of v. And that means we don't actually need a fully random unitary for the OTOC to decay. You only need a unitary that is sort of random up to its second moment. So a distribution of unitaries that agrees with the random distribution up to the second moment. And these are known as Tudor signs. So we can in fact model a scrambling unitary as a typical pseudo-random unitary rather than fully random unitary, i.e. a unitary drawn from a Tudor sign. Okay, so that's scrambling. What is quantum machine learning? Well, I probably hardly need to justify that to this audience. But that said, I mean, arguably the term itself is not that well defined. I've certainly ended up in many arguments with my colleagues over what exactly we mean by quantum machine learning. So just to pin it down slightly for the purpose of this talk, the definition I'm going to use is any method that optimizes a parameterized quantum circuit by minimizing a quantum cost function, potentially using training data. And a particularly sort of promising family of quantum machine learning methods, as I'm sure many of you are very, very well aware, are variational quantum algorithms. So here the idea is that you run some optimization algorithm on your classical computer. So it could be gradient descent, Bayesian methods, or whatever your favorite optimization technique is, but with your cost function evaluated on your quantum computer. And by picking a cost function that is hard to compute classically, but relatively easy to compute quantum mechanically, the hope is you might obtain some form of quantum advantage. So just in a little bit more detail, variational quantum algorithms have a structure of this form. So you run some parameterized quantum circuit on your quantum computer. So I'm going to consider fixed parameterizations. So you've got a fixed gate sequence, and your parameters are going to be rotation angles, continuous rotation angles that you want to optimize. So you run your parameterized quantum circuit with a particular set of parameters. You then measure your output, and that will give you some cost function evaluated with respect to a particular set of parameters. That's fed to your classical computer. Your classical computer runs its favorite optimization algorithm, and you just keep on looping around until you minimize your cost. And the solution, the parameters that minimize your cost will be, in some sense, a solution to whatever problem you're solving. So in the case of trying to use a variational quantum algorithm to try and learn a particular unitary, a scrambling unitary, then the aim is to try and find some parameterized quantum circuit and some optimum angles theta opt, such that U of theta opt equals your target scrambling unitary. So you're going to want to pick a cost function such that the unitary that minimizes it matches the target unitary like you have here. Okay, so many different costs that you could use, but they're all broadly going to be of this general form. So the idea here is that you're going to prepare some initial state psi I. You're going to evolve it under your target unitary V. You're then going to evolve it applied to the inverse of your parameterized quantum circuit, and then you're going to perform some measurement HI. And the idea will be to predict your state psi I and measurement HI such that the unitary that minimizes it agrees with your target unitary. And a particularly natural choice in measurement would just be to take your measurement to be a projector back onto your initial state. In that case, this cost function here measures your average gate fidelity. So that is the average fidelity between a state psi I acted on by V, your target, and a state psi I acted on by your parameterized quantum circuit, averaged over a set of states psi I that can effectively be seen as your training states. So within an input-output training pair picture, V psi I would be your output state, and psi I would be your input state. And this would just be your loss function. Okay, so most cost functions will be broadly of that form, but actually in the paper we want to make things a bit more general, so we consider more general compiling costs that allow for entangled training data and distributive answer. But in all cases, the broad idea is you want to pick your cost such that the unitary that minimizes it matches the target unitary. Okay, so that's how you can use a quantum machine learning or variational quantum algorithm type approach to try and learn some target unitary. But these methods are only going to work if your landscape is sufficiently featured to enable training. So say you were trying to learn with gradient descent. I presume you could try and learn with other methods, and most of what I say equally applies to other methods, but I'm going to focus on gradient descent. And I'm sure most of you are very aware how gradient descent works, but in case anyone isn't, the way I like to picture it is to imagine that you are lost on a mountain in the fog and you're trying to find your way down. What would be the easiest way of finding your way down? Well, a good bet would just be to keep going the steepest route down at any moment in time, which is roughly what water does, which is why this little lost man would end up following the stream down. But this strategy of just following the route of steepest descent at any moment in time is only going to work if you can actually discern which way is the steepest route down at any moment in time. It's not going to work if your landscape is overwhelmingly flat. So this little man is basically going to end up performing a random walk, struggling to find the lowest point of this field on the right. Okay, now this is particularly a problem in the context of trying to minimize a quantum cost, because if your gradients are small, then you're going to need very, very high precision evaluations of your cost gradients, so very high precision evaluation of your costs to determine the minimization direction. And now evaluating a cost to high precision, of course, is resource intensive. It requires a large number of shots. So specifically of order 1/σ² shots are required to evaluate a cost to high precision. So if sigma is small, you're going to need lots and lots of shots. So trying to navigate to the minimum is going to be shot intensive on a flat landscape. Okay, so how do you determine whether you are on a nice trainable landscape or a too flat untrainable landscape? Well, the trainability of a variational quantum algorithm can be assessed by studying the expected cost gradients. So that is the partial derivative of the cost with respect to all of your continuous rotation parameters. And it's straightforward to show that for typical parameterized quantum circuits and cost functions, your cost function gradients will vanish on average. So this is essentially saying that your landscape is unbiased. You're equally likely to come across positive gradients and negative gradients, or as anyone who likes walking knows, what goes down must come up. But an unbiased landscape can be either trainable or untrainable, depending on the extent to which your gradients deviate away from zero. So both of these landscapes are unbiased, but the top one is going to be hopefully trainable, but the bottom one clearly isn't. So to evaluate whether or not your algorithm is trainable, it's helpful to employ Chebyshev's inequality. So Chebyshev's inequality bounds the probability that the partial derivative of the cost deviates away from delta in terms of the variance in the partial derivative of the cost. So if the variance is small for all parameters, then the probability that the partial derivative of the cost deviates substantially away from zero, or some small value delta, is also going to be very small. So small variance entails small cost gradients, entails a very, very flat cost landscape, and so it's going to be hard to train. Okay, so what is known as the bound plateau phenomena has now been established for a wide range of sort of quantum machine learning and variational quantum algorithms. So this is the phenomena whereby the variance in the partial derivative of the cost has been found to vanish exponentially with the size of the problem. So n here is the number of qubits your parameterized quantum circuit acts on, or your sort of algorithm is defined with respect to. So given Chebyshev's inequality, the fact that the variance in the partial derivative of your cost vanishes exponentially entails that the probability of observing non-zero gradients vanishes exponentially with your problem size. And that means the number of shots required for training is also going to grow exponentially with problem size. So for relatively small problems, your cost landscape may be sufficiently featured that you can train, but for larger scale problems, to get up to many, many qubits, or not even that many qubits, in fact, your cost landscape is going to rapidly become too flat for training. Okay, so the bound plateau phenomenon was first sort of discovered by our previous speaker, so Jared McLean, well, he's in a quantum context. So he showed, and he and his co-authors showed that bound plateaus can be induced by an inappropriate choice in parameterized quantum circuit. A bunch of subsequent papers have sort of, in some ways, refined this, saying that if you use a parameterized quantum circuit that produces too much entanglement or is too expressive, can be used to solve too many problems, this can lead to bound plateaus. And then it's also been shown that bound plateaus can be induced by your choice in cost function. So if you use what is known as a global cost function, where all of your qubits are measured at the end of the problem, then you can end up with bound plateaus. And the result I want to share with you today is a new way in which bound plateaus can be induced. Essentially, we found that the choice in target problem matters. That if you're trying to learn a scrambling unitary or a typical random unitary, you will also encounter bound plateaus. Okay, so this is the meat of it. What we've proven is that for compiling costs of the sort I introduced earlier, if these are used to try and learn a scrambling unitary, which we model as a unitary drawn from a 2 design, then firstly, you're going to find that the average cost gradient vanishes. So your cost landscape is unbiased. And secondly, and more importantly, the variance in the gradient of the cost vanishes exponentially with the number of qubits your scrambling unitary acts on. So this average and this variance here are both taken over an ensemble of scramblers, an ensemble of pseudo-random unitaries, i.e. a 2 design. And if you take these two things and you put them together, combining them with Chebyshev's, well, what this shows is that the probability that the gradient of the cost is non-zero for a typical scrambler vanishes exponentially with the size of the problem, i.e. you have a bound plateau. And now really crucially, this result holds for any choice in ansatz. So no matter what clever techniques you try and employ to avoid this bound plateau, and a number have now been proposed by different groups, they're not going to work here. You're going to inevitably end up with this bound plateau. And so in this sense, this is a no-go theorem for learning scramblers, or more generally typical random unitaries using quantum machine learning. Okay, so I'm just going to end by sharing some sort of numerical results to back up our analytics. So here we plot the cost landscape as a cross-section of a compiling cost that we use to try and learn a scrambling unitary. So we model a scrambling unitary now using this minimal model of a scrambler proposed by Belansky et al. So this model is helpful because we can use it also to model approximate scramblers as well as perfect scramblers. So the model is composed of alternating layers of random single qubit unitaries and all-to-all entangling gates. So T here determines the number of layers we apply, so essentially the scrambling time and G here is the entangling rate. So for large G and large T, we are dealing with highly scrambling unitary. So in that case, as shown in blue here, the cost landscape is overwhelmingly flat with just a narrow gorge where the cost dips down towards the minimum. So that's going to be hard to train. In contrast, for weaker scramblers, so short times and low entangling rates, the cost landscape is much more textured and the valley is much broader. So it's going to be much easier to train weaker scramblers. So I think it's just a nice visual representation of how the barrenness of the cost landscape depends on the degree to which your target unitary is scrambling. And here is sort of similar effect, but shown in a different way. So here we plot directly the variance and the partial derivative of the cost as a function of scrambling time. And what you can see clearly is that the cost gradients decrease with increasing time, and so increased scrambling. And then indeed for late times, when we're dealing with a perfect scrambler, the variance and the partial derivative of the cost does indeed vanish exponentially with the number of qubits, demonstrating that we do have a bound plateau as predicted by our analytic results. Okay, and that's more or less everything I had to say. So we've shown that bound plateaus will be exhibited by scramblers. So that is, if you're trying to use a compiling cost to learn a scrambler, you will find that the probability that the partial derivative of the cost deviates from some amount delta, vanishes exponentially with the number of qubits that your scrambler acts on. So that means you're going to end up with very, very flat cost landscapes for highly scrambling unitaries, which will be hard to train. And crucially, because a scrambler can be modeled as a typical random unitary, which is what we did, our results also apply to learning typical random unitaries. So in this sense, sort of randomness is a barrier to trainability using quantum machine learning. But I think sort of luckily, thankfully, most physically interesting processes do not resemble a typical random unitary. So this result in no way sort of condemns quantum machine learning. It just rather tells us that we need to pick our target problems carefully. There'll be fundamental limits to quantum machine learning. The physics of the problem matters. And I think it sort of would be interesting to investigate in more detail sort of what systems can or cannot be learned. Thanks for everything I had to say. So hope maybe there are some questions.
Yeah, thank you, Zoe, for the nice talk. Are there any questions from the audience? So I actually have a few questions. So the first question was, here you consider random unitaries from two designs, but what about like a long time evolution under some chaotic Hamiltonian? So when you have a Hamiltonian, you also have certain preserved quantities or preserved symmetry. Do you think that under those conditions, this result would still hold, or?
So if that Hamiltonian is, okay, so.
Like even just numerically, like if you just pick a random Hamiltonian, like a local Hamiltonian where you have random coefficients, random coupling, maybe because the material or the black hole is kind of have like.
So if you know a bit, yeah. So if you know a bit about the physics of the problem, so potentially if you know about the structure of the dynamics and maybe you know that certain symmetry properties are maintained.
Yeah, like for example, Hamiltonian would be a symmetry, right? So there's at least that symmetry. Maybe there's a bit more, but maybe knowing those symmetries is still going to be hard.
I think it is still going to be really hard. Essentially, you have additional information. It's also tricky given that our results holds for any choice in ansatz, any parameterized quantum circuit. It's kind of hard to see how you would use that information. So it's just
right. No, the starting, like, because the result hold only when you sample from two design, but like when you just have a Hamiltonian evolution, like maybe long time, I don't think it's known that it's a two design. So that
I think the Hamiltonian evolution at long times will resemble closely resemble a unitary that's drawn from a 2 design, is the point. So I think it will resemble a typical random unitary, but the question is, can you use information about the physics of the problem, sort of the symmetries, to construct an ansatz in some way so that you can actually learn it? And when we first wrote the paper, we thought, aha, yes, if you had prior information, maybe you could do something along those lines. But given the result holds for any parameterized quantum circuit, it's hard to see how that extra information would help. Because the natural way of doing it would be to pick your parameterized quantum circuit so that it is symmetry preserving for various symmetries. But I don't think that's going to actually help here. My suggestion of how to get around it is to, and this actually helps if you have access to the Hamiltonian, is try and do sort of the equivalent of growing the ansatz, but growing the target. So try and learn the evolution of the Hamiltonian at short times, and then learn it in short time sequences and see whether you can sort of sew it together in order to learn the dynamics at longer times. And that is actually something you can do potentially if you have access to the Hamiltonian rather than the unitary. You can simulate shorter times, because at short times, a scrambling system will actually only resemble a 1 design. This result doesn't hold for 1 designs.
Yes. All right, thank you so much. So in due of the time, Joey Gibbs, could you share the screen?
Sure.
Yeah, so our next speaker is Joey Gibbs, also from Los Alamos National Laboratory, who will be telling us about long-time simulations with high fidelity on quantum hardware. So please go ahead. Thank you.
Hi, guys. Thank you for inviting me to speak today. I'm really grateful to be here. My name's Joe Gibbs. I'm a scientist at the UK's Ministry of Defence, but this work was completed in collaboration with the Los Alamos Lab and with the support of many great scientists there. And so today I'm going to be presenting a new variation quantum algorithm for dynamically simulating quantum systems. So why do we want to simulate quantum systems? Well, we're interested in numerically investigating materials at the atomic level, and we want an alternate route to understanding these materials rather than pure experimental investigation. And a accurate numerical simulations is going to be really critical for the development of high temperature superconductors and topological materials. So how are we going to simulate these quantum systems? Well, if we're using a classical computer, we're clearly going to have great difficulty. Although there are a wide class of electronic systems that can be solved efficiently with classical methods, for a sort of general many-body Hamiltonian with highly entangled states, it's going to have this. We're going to need these exponential resources to store the state of that problem, which is motivating the need for quantum computers, which also have an exponentially large Hilbert space. So we're interested today in dynamically simulating quantum systems rather than calculating a static property like you would do in a variational quantum eigensolver. So this is going to mean at some point solving the Schrödinger equation. So your first method of how you might do this might be to construct a trotterized operator. So on your quantum computer, you're going to have some finite gate set. And from that finite gate set, you can construct an approximation for a short time evolution by splitting up your Hamiltonian into local terms and applying each of these local terms in short succession. And then iterating this short time operator many times will evolve your state forwards. There is a trotter error associated with this approximation due to the non-commuting terms in your Hamiltonian. And this error is amplified for larger delta t's here. So can we just make our delta t arbitrarily small and as a solution to this? Well, so the trotterization inherently has this linearly increasing circuit depth. And we're wanting to run these algorithms on near-term devices, what we call NISQ devices, noisy intermediate scale quantum devices. And these machines will be non-error corrected and they will have noise in their gates. And if you've got this linearly increasing circuit depth, each of these gates is going to inject a small amount of noise into your computation, which will decay your fidelity as the simulation progresses. So that means that these devices have what we call a coherence time, a sort of time after which your state has been completely corrupted by all these the noise introduced by your gates. And after this point, you're unable to do meaningful or useful computations. So we really want to get around this linearly increasing circuit depth. So and a method that you might try to do this is by diagonalizing your trotterized operator. So what that means is we want to get our trotterized operator into this form, WD, W dagger. And once it's in this form, our W, what this is doing, it's rotating between our eigenstates and the computational basis. And our diagonalized unitary is applying an energy-dependent phase to each of these eigenvectors. Now, what's interesting about this form is if we imagine applying this operator twice, we're going to get a W and a W dagger cancelling to the unitary, and our the rotations in our diagonal gate are going to simply sum because they share an eigenbasis. So we can sort of arbitrarily apply, we could simulate applying arbitrarily many trotter unitaries by simply scaling up the rotation angles in this diagonal matrix, which is sort of the crux of why we like this diagonal form. So once we've got this diagonal form, our Hamiltonian can be fast forwarded with a fixed depth circuit, allowing simulations beyond the coherence time of the quantum computer, because we ideally compile some fixed depth circuit that is sort of comfortably within this coherence time. So this is the schematic that might be familiar, but we are trying to compile this. The aim of the game is to compile this diagonalized unitary, and we're going to use a variational quantum algorithm to do that. So our diagonalized unitaries is going to be parameterized by some rotation angles. And we're going to optimize these in a quantum classical feedback loop with the help of our optimizer. But can we know anything about the structure of W and D before we start? Well, D needs to be diagonal. So it needs to be composed of essentially tensors of I's and Z's. And so one form of this could be using k local Z rotations. So where one local is our single qubit RZ rotations, two local is terms that are like e to the minus I ZZ, and so on. And so increasing k will make our D more expressive. And our W is the more interesting one. That's the main challenge of compiling into this form. So we can use some sort of hardware efficient ansatz. We can encode some symmetry preserving properties using information about our Hamiltonian, or we can scrap the fixed structure and actually go to some sort of variable structure where we're optimizing the discrete structure. And for the results that I'm going to present, we use some combination of all three of these. So the first method proposed, this was presented at last year's QTML, was the variational fast forwarding algorithm as a variational method to construct this variational, this diagonal form. So they used the results in the quantum assisted quantum compiling paper to help approximate this evolution unitary, this trotter operator. And they used the Hilbert-Schmidt test as a way to compute a similarity between the trotterized unitary and the diagonalized unitary. And this test is really nice because it doesn't matter how many qubits wide your trotterized unitary is. This will always be a fixed depth circuit. So this is nicely suited for NISQ hardware. We've scrapped the linearly increasing circuit depth. However, to run this test, it requires the generation of these two N bell pairs here. And this is quite expensive to do on NISQ hardware. And requiring these 2 registers of n qubits can be quite prohibitive in terms of what topology we can use to run on the quantum computer we seek to run it on. And what VFF is doing, it's quite a tough task. It's diagonalizing over the whole Hilbert space. Whereas this is actually potentially overkill for many tasks. In many instances, you just have one state and you just want to fast forward that one state. So it can be overkill to diagonalize on this whole Hilbert space. So this is where I introduced fixed state variational fast forwarding, which is our specialization or like refinement of VFF. And the main idea we're using here is we're diagonalizing the Hamiltonian just on the subspace spanned by this initial state. And it's going to turn out that by refining the task that we're performing, we can significantly reduce the resources required, making it even more NISQ friendly than VFF. So summarized here are the main differences between VFF and fixed state. So instead of fast forwarding all states, we're going to fast forward some fixed input state. It turns out we can halve the width of the qubits that are required. We can find shorter depth diagonalizing unitaries, and we don't need any Bell pairs generated as an input. So if we can represent our initial state as some superposition of the eigenstates of the Hamiltonian, and it's going to be this superposition of these eigenstates, and we're going to call the number of these superpositions n-eig. And we note that when this state is evolved by the Hamiltonian, all that happens to these states is they pick up a phase, so they don't leave this subspace. So we're wanting to learn the evolution within this subspace. So there's a quantum version of the no-free lunch theorem, and that tells us that to learn the action of a unitary on a d-dimensional subspace, this requires d training states. So straight away we see that we need n-eig training states. So the training states that we're going to use are going to be the first n-eig iterations of evolutions via our short time trotterized unitary. And this motivates our cost function, where we're going to maximize the overlap between our diagonalized unitary and our trotterized unitary. So this is an overview of the algorithm. So we start with our Hamiltonian and our state of interest. We construct a short time trotterized evolution unitary. Now we've got this optional step where we do have an algorithm to compute this n-eig quantity. However, I'm going to skip the details of this today because it turns out that we don't need to compute this. There is an alternate method where we could say you train on increasing numbers of n-eig states until your cost function stops increasing in value when it starts to generalize. So then we enter our classic variational quantum algorithm feedback loop, where we're calculating this cost function, and we're then iterating by calculating the gradients for which we have an analytical formula for. And then once we've sufficiently minimized this cost function, then we're left with this diagonal form, which we can then use to fast forward our algorithm on the subspace. So we've fully executed this algorithm on some real quantum computers, on these IBM and a Rigetti device. And on the top here, we can see the training part of this algorithm. And the dashed line here is the noisy cost measured on the quantum computer. But the bold line is the same ansatz, the same circuit measured with no noise. And we can see there's a separation between the two. This continues to train whilst the noisy cost plateaus. And this is evidence of the noise resilience of this algorithm, which has been sort of proven in Sharma et al.'s paper. And down here, this is the results of the fast forwarding. So we're wanting, as the simulation progresses on the x-axis, we're wanting to keep a high fidelity of this simulation. So we can see here that the iterated Trotter's fidelity, it decays exponentially. The linearly increasing circuit depth The C knots are introducing so much noise that it quickly decays to the maximally mixed state. Whereas with fixed state VFF, it has constant noise errors due to its fixed circuit depth. And it turns out that the fidelity will only decay quadratically rather than exponentially, which is a result that we show in our paper. And if we define the fast forwarding ratio to be the fast forwarding for the 0.2 is the ratio of the times between when each simulation, their fidelity drops 0.2. The ratio between these two times for both simulations is 159. So we've sort of managed to simulate 159 times longer here. So we've done some larger scale numerical simulations. So here we're doing a 4-qubit XY model. We're using a superconducting noise model. We've got this initial state, and we're seeing the same behavior here. We're seeing the separation between the noisy and the noise-free cost because this is noise resilient. We've got this nice outperformance by the fixed state method. And here we're fast forwarding a Fermi-Hubbard Hamiltonian. This is 4 sites, so that requires 8 qubits to simulate. We're using a trapped ion noise model. Our initial state is a superposition of 5 eigenstates, and we're getting this really large fast forwarding ratio. One thing that's interesting to note here is we plot the diagonalizing unitary at successive points. So this optimization was done, well, these both were with an ansatz that is, for one, conserving the symmetry of their respective Hamiltonians, and 2, the discrete structure is being optimized. So that is why the earlier diagonalizations perform better for shorter times, because the gate sequences were shorter at this point. And as the training progressed, the circuit depth increased, and that's why there's a small penalty for the short times. This performs very well in the long time. So as well as reducing the width of the quantum circuits required by half, as i.e. all the unitaries are applied on the same n qubits rather than 2 n qubits as required in VFF, we can achieve shorter depth diagonalizing circuits. And this arises from the greater available set of unitaries, which can simulate evolution on the subspace rather than the whole Hilbert space. So here I'm performing fixed state VFF and VFF for the same Hamiltonian, this one here. I'm using the same layered ansatz, and I'm using the same optimizer. But all that I'm doing is comparing fixed states to VFF and seeing how well they respectively perform. So I'm seeing here that for 6 layers, I can get this nice low cost for fixed state VFF and this nice fast forwarding. Whereas for our standard VFF, even after increasing the depth of my ansatz, I'm still unable to find a diagonalization, and I'm getting no sort of appreciable fast forwarding here. So stochastic gradient descent has become a de facto method for training machine learning models. It's often unnecessary to train on your full data set, and it's often infeasible to do that. And it turns out you can get pretty good generalizations using sampling your gradients with a small random subset of your training set. So we can analogously do something similar. So we can compute our cost function gradients with much less than NI states per iteration, which could seem to be prohibitive if we've got a state with a very large NI. So, and going a step further, if we instead to randomly sample from the continuum, we can avoid computing NI altogether. So this results in this modified cost function, where R here is a set of random real numbers in the interval 1 to -1. And our T max is some short time that we deem to be the maximal, to have the maximal acceptable trotter error. So every time the cost function is called, we're choosing some random points on this interval. And a nice thing about this cost function is we now don't need our trotterized unitary to be able to be decomposed into NI repeats. And that means we can really optimize the structure of our trotter. So we can get a smaller trotter error for the same circuit depth. So using this modified cost function, I'm training a 5 and 6 qubit XY model. I'm looking at a domain wall state with half ones, half zeros. And for the 6 qubit case, this actually has an NIG of 12. But for each time the cost function is called, I'm only sampling two points. And I can still get to these low cost levels and get these good fast forwarding results. So some other results that didn't quite manage to get their own slide, but are interesting nonetheless, that are contained in our paper are, we've got a local cost for improved trainabilities for barren plateau mitigation. We've got the quantum algorithm I mentioned earlier, which we can calculate NIG explicitly on the quantum computer. We've got this nice bound here that says that our infidelity of simulation at worst scales quadratically with our simulation time. And we can also use fixed state VFF as a method of improving quantum phase estimation. You can actually get an exponential circuit depth reduction once you've found your diagonalizing unitaries. So in summary, we've started with a problem. The iterated trotter method is unsuitable for long-time simulations because of this linearly increasing circuit depth. So we tried to solve this with VFF. We've diagonalized our unitary into this nice fixed depth form. So then there's another problem that's arisen with the restrictive need for these 2n bell pairs, the 2n qubits, and these are like expensive on NISQ hardware. So our new solution is, by specializing the task that we're performing, we can achieve superior performance with reduced required resources. So that concludes my talk. I'd like to thank you all for listening and for the organizers for hosting us today, and I'd welcome any questions.
Thank you, Joe, for the very nice talk. Are there any questions from the audience? So one question is, so previously I've seen works that talks about variational quantum simulation, and where they have an ansatz that represents the evolved state, and then they try to modify the ansatz whenever they add some additional trotter steps to it, and then try to modify it, kind of like condensing it back. It does feel like the two methods share certain similarity. Could you maybe comment on how different they are, or have you seen this variational quantum simulation work? Or
so it sounded like you were saying you're appending a new trotterized evolution operator, then you're somehow compiling that down.
Yeah.
So I guess that's one approach, but I think that would be very time consuming, and I think you'd be incredibly lucky to keep appending these trotterized unitaries and expect your circuit depth to retain the same depth. And there are other methods of having some sort of ansatz and then updating the parameters, like Lee and Benjamin's method of using like Maclaurin variational principles. So yeah, there's different ways of maintaining a fixed circuit depth simulation. Yeah, and it's an interesting space.
But in a sense, isn't your method sort of saying that there does exist such kinds of ansatz, which is this WD dagger diagonalization form that could be used as one of their ansatz, and then maybe you can apply this Maclaurin kind of evolution in order to do it, for example. So just wondering.
I'm not sure. I'm not sure if you need to use them if you've got it in your diagonalized form, as long as your cost function is sufficiently low and it's you're showing it's generalizing. You don't need to do the Maclaurin updating. You just scale up your D parameters, and you're automatically fast forwarding your Hamiltonian.
I see.
Yeah. So once you've got it in this once you've got it in this form, then your W stays constant because it's just encoding information about your eigenvectors, and all you do is
Right.
increase the value.
Right. I was thinking about the situation where where you update your W. So you don't go through the process that you're proposing here. I'm just using the same ansatz as what you're doing here, where you have, if I recall correctly, I thought you also parameterize this W and then you do optimization to minimize this W. I was just wondering, like, if you actually do this other step of like a variational quantum simulation style, but using the same things, would that be beneficial, or that's actually an inferior version of yours and so on? So I'm just
I
wondering.
think on a similar version to what you first proposed, that there is it could be that your quantum computer has a very short coherence time, and you're not able to get in enough trotterized steps. So what thing you could do then is compile a diagonalized unitary for a short time evolution, and then iterate that forward, I think, which is possibly what you're getting at. So then, so that is a more meta version where you're sort of iterating diagonalized unitaries, which somehow compress many trotterized unitaries.
I see. Yep. If there's no other question, then thank you again for the nice talk, and thanks all the speaker for this session. I think we're going into a coffee break for now.
Thank you very much, Robert, for chairing the session, and thank you to all the speakers for all the wonderful talks. So let's have a half an hour break, and then we be back here for the invited talk of Roger Melko. And then don't forget that in 3 hours, we have the industry session. So thank you very much again. And thank you, Robert. Let's have a break.
Hello, can you hear me?
Yes, yes, we can.
Okay, great. Can I briefly check my
Yes, sure.
slides? Great. Can you see my slides?
Yes,
Yes.
perfectly.
Okay, great.
Thank you.
So, and stop sharing. Okay.
Hi, Roger. How are you?
Hey, how you doing?
Good.
Can
How
you
are
hear me?
you?
All good, all good.
What time is it over there?
It's almost bedtime.
It's pretty late over there, right?
Yeah, I can just hear my kid going to bed now. It's 9 p.m.
Oh, okay. Well, it's not so bad.
Yeah, it's not bad. How's things been going? Pretty smooth, I think, from what I've seen.
Yes, it has been going on pretty well. Yes, there are a lot of very interesting talks, and it's been very, very intense. Actually, it has been a pretty intense week, but very nice. So let's wait for a few more minutes. We have what we have here. Roger, have you been to Tokyo? Have you been to Japan?
I've only been to Osaka and
Oh,
Kobe.
okay. Okay, but not to Tokyo.
Oh, you know, I did go there once for a day, I think. I guess I
okay.
didn't see the whole city in a day, though.
Okay, next time, man. Sorry, this
But
time
it's-
it didn't happen.
Yeah,
It's
no,
too complicated.
yeah, I'd love to visit again.
It's one of the best time to visit, actually. One of the best season to visit.
Not too warm, right?
Very beautiful. No, and now it's like 20 degrees Celsius. It's very beautiful. The summer is really hot and humid.
I was in, I think I was in Osaka in August. I remember how hot it was.
Must have been very hot, right? It's very hot here in July and August, actually.
Hot for a Canadian. Yeah.
Yeah. The humidity. But now it's beautiful. Now it's like the fall season in like the northeast of the US and in Canada. With all the fall colors, it's spectacular.
Well, winter's approaching fast here. It's already freezing, so.
In Tokyo, it's pretty mild. The winter is pretty mild. So let's see who else. Let me see. Matya. He's supposed to be. We just want to ask him to check his screen sharing, but I think he's not. He's online, but he's not there. I think we just ask you to. Oh, sorry, I thought. Why do we have this recording on the talk and stuff? So I keep on forgetting with the recording and the pausing of the recording. I'm doing what Johnny did last year. It's kind of in charge of all the all the Zoom and everything. It'd be nice to have some IT professional to kind of do it, but when you do it, you keep on forgetting, because when you listen to the talk, actually, then you keep on forgetting that you're supposed to do the admin job. I think you should have sharing your talk now, just kind of sharing your screen now, because we'll be starting.
You want me to share my screen?
Yeah, I think so. We have like 2 minutes away. Just 2 minutes away from the talk.
How does that look? Is it working?
Yeah, I think yeah, it looks perfect.
Can you see Feynman's face?
Yes.
Okay, slides are advancing. Good. Right, I'm set.
Kasuke, I think we'll be starting very soon. Thank you.
Okay.
Just 1 minute away. Okay. Ima, please.
Okay, just okay. So welcome to the second morning session, and I am Kosuke Mitarai from Osaka University, and I am chairing this session. And so in this session, we have one invited talk and two contributed talks. And the first talk will be the invited talk from Roger Melko from University of Waterloo, and he is going to talk about generative models and the future of quantum simulation. So please go ahead.
Okay, thank you very much. And thanks for the introduction. Thanks to the organizers and everyone who's chipped in to put together a wonderful conference again this year. It's great to see. Before I start, I just want to acknowledge all of the, oh, sorry, my dog's going wild here. I just want to acknowledge all the great people who've kind of contributed to this work that I'm going to talk about, and I've pictured most of them here. The group here is the group at University of Waterloo and Perimeter Institute who's interested in sort of the cross sections of quantum physics and machine learning. And so we call ourselves the Perimeter Institute Quantum Intelligence Lab. And most of the work that I'll talk about today was spearheaded by a couple individuals who used to be at Perimeter with us. That's Giacomo Torlai, pictured here, eating a pizza at Flatiron Institute. And also Juan Carrasquilla, who is currently at the Vector Institute for Artificial Intelligence, where I'm also an affiliate faculty member. So I'm going to talk about generative models and the future of quantum simulation. And to start off, I think I just want to define what I mean by quantum simulation. And because we have a couple sort of different contexts that we use when we talk about simulation in the quantum world. And so, you know, at risk of seeming unsophisticated, let me start out with this quote by Feynman: "Nature isn't classical, damn it. And if you want to make a simulation of nature, you better make sure it's quantum mechanical and all this stuff, right?" And so I think we understand, you know, very sort of generally what Feynman was talking about when he was thinking of quantum simulation. And, you know, there's essentially two contexts that I want to talk about. Just give me 1 second, everybody. Sorry to do this live, but I have a kid and a dog barking at the same time. I'll be one. Okay, situation fixed. So quantum simulations. All right, so I'm a condensed matter physicist. So what I work on is what I'm going to call in silico simulations of quantum, you know, the quantum problem. And in condensed matter are sort of like holy grail in some sense, is to solve strongly correlated or strongly interacting models. And I'm going to use as just kind of a conceptual example the Hubbard model. And so the Hubbard model is something that's been abstracted, you know, from a a quantum reality. So, a natural phenomenon, which is, cuprate superconductivity. So the cuprate superconductors are ceramic materials that superconduct at, liquid nitrogen temperatures. And we as condensed matter physicists would love to understand, the mechanism by which superconductivity occurs in these models and how electrons pair and, condense and form sort of charged superfluids, if you will. And so we form models from these many body Hamiltonians by, abstracting out from the crystal structure, perhaps two-dimensional copper oxygen planes, which have electrons that interact with, a certain Hamiltonian that involves, tunneling interaction, tunneling, between lattice sites and perhaps some sort of interaction. And, we believe that if we could, quote unquote, solve this model, which means, taking this Hamiltonian perhaps on this lattice, finding the corresponding ground state wave function, maybe the low-lying excited states, the nature of topological defects, the nature of the low-lying spectra, maybe the dynamical properties, then we would be able to design materials that superconduct, say, at room temperature. So that's kind of the the holy grail, if you will, of in silico simulations, which means, in our conventional computers. And of course, condensed matter physicists and, quantum information physicists have developed a very sophisticated toolbox of numerical methods, which can be used to attack these problems. But even with our best methods, like I've illustrated perhaps a tensor network here, which is some sort of variational ansatz for the wave function, ground state wave function, or something like quantum Monte Carlo. Even with our best methods, some of these problems remain essentially intractable or unsolvable for us. So that gets us back to Feynman's original, I guess, vision of a quantum computer, which in some sense is to simulate quantum mechanical properties, of nature that, for whatever reason, are difficult to simulate, in silico. So I'm going to call those as experimental simulations or emulators or simulators or quantum simulators. And I think we've heard, several sort of talks which have talked about simulators in this context. We can imagine, the superconducting quantum processors like Google, trapped ion systems, or Rydberg atoms, which I'll talk about, my favorite quantum simulator. And all of these are really computers in the sense that they're highly controlled programmable devices, right? That can be used to emulate, models in some of these interesting classes that I talked about on the previous slide. So, for example, the common sort of scenario is that, the Hubbard model tunneling and interaction, which usually occurs in the crystal lattice of some material, can be simulated or emulated in one of these highly controlled devices, either by some interaction which is induced by standing, either optical tweezers or standing waves of light, and basically tunneling and so on. So what's I find really exciting is that in today this day and age, that these quantum simulators are giving us systems of qubits that are bordering on the hundreds or thousands of qubits in the devices. And so the devices that I'll talk about mostly going on in this talk are the Rydberg atom or Rydberg arrays, which in recent literature out of the Harvard group have achieved at least 256 atom devices. So that's what I mean by simulators in these two different contexts. And I'm going to focus on quantum simulations in the latter setting. So when we have an experimental quantum device, which I'm just going to abstract into a black box at this point. And then, basically we're going to talk about what we do with that data. So of course, an experimental quantum device is linked, crucially with your classical computer for all aspects of its, design, number one, but also the kind of the control and readout, feedback loop, which has to occur at every stage of operation of the quantum computer. So I'm going to focus mostly on the readout, because that's the kind of data-driven aspect in some sense at the lowest level. And what I'm going to talk about is how we use machine learning architectures like neural networks, but specifically generative models to kind of enhance and to amplify the use of our data. So how does this look? Just very schematically. Oh, so you can imagine having a projective measurement data set that comes out of this quantum computer, which is distributed according to some distribution. And that distribution, according to our fundamental postulates, essentially, is a distribution given by the Born rule related to the wave function through this relationship here. And I can imagine that the data that comes out of my quantum computer as sort of a list of vectors. Each one of these vectors is it's like an image of a cat or a dog. Each one of these is a pixel. And so for one data vector X, I have n different elements in that vector, which are the projected state of the qubit in whatever basis, that's the computational basis of my device. So that's typically fixed somehow by the hardware. And so generally I have a fairly limited data set. There's some shot budget associated with these experiments. Of course, depending on the architecture and so on, you can get a few of these vectors a second, or you might get a faster rate if you're lucky on some devices. And so the goal of this talk is to basically leverage generative modeling to enhance the amount of information that we can get out of that device. So for example, learning in some sense a model, a parameterized model of the underlying distribution is kind of the most basic task. I think that can be done. And when we have this setting where we have data being, data coming out of a quantum computer, and we don't have any sort of a priori knowledge of what's in the black box, it's completely a data-driven problem. And the cost function that we're going to optimize is strictly, the cross entropy between the data set and the model, or something of that ilk. So I'm basically imagining something like a Kullback-Leibler divergence, where I have a trace over all possible, in principle, all possible configurations of these qubit measurements. But in reality, I really only have a limited data set here. P log P over P lambda, okay? And P of X is what's coming out of the black box. And P of lambda, that lambda is the parameters that are, I'm using to represent essentially my probability distribution in this model. Sorry, I see that there's a chat, but I can't read it. Is that a question?
No question.
I've just posted it. Please feel free to post a question.
Okay, so continue. Okay.
Yeah. Well,
great. Okay, so.
Okay.
Oh. So okay, so the goal is to learn a parameterized model of the wave function. So I'm going to do that with generative models. And so I think everyone at this conference, is at least has some experience in machine learning, perhaps. So I'm just going to kind
Roger,
of.
Sorry. Would you like to take questions now, or would you like to wait until the very end?
Oh yeah, no, hit me with questions in real time.
Zhao Kai Li has a question.
Oh, okay.
Please.
Yeah.
Zhao Kai Li, he raised his hand. Sorry, please go ahead. Actually, maybe he forgot. Maybe he did it by mistake.
No worries. Yeah, no, feel free, any of the panelists here, to just kind of unmute and interrupt, just because I can't really see the hands in the chat. So, okay. All right, so what is a generative model? Perhaps we know. I like to use this kind of taxonomic tree that was introduced by Ian Goodfellow in kind of one of his NeurIPS papers from 2016 or 2017. And so generative models, in principle, under the heading of maximum likelihood, which, again, maximum likelihood is just related to the fact that I can calculate the expectation value of log, p lambda, from data drawn from the distribution, and so I can define a likelihood estimate from that. So maximum, I maximize the negative log likelihood or the log likelihood in all of these types of models. But different generative models have different sort of ways of representing distributions, right? And so, of course, Ian Goodfellow, famous for the generative adversarial network. So that the GAN is really an implicit density generative model, which means that I don't have an explicit parameterization of a probability distribution that lives inside the generator in this case. And as you know, GANs are trained by an adversarial relationship between a generator and a discriminator. The generator generates quote unquote fake images. These are fed into the discriminator, which determines whether they're real or fake. And in some sense, the generator is updated by that procedure. But you don't really crack open the generator to see exactly how you've parameterized the likelihood or the density. So the explicit density branch, as identified by this kind of tree, is where we mostly focus for this work I'm going to talk about. And that explicit density branch has, I think, two interesting sub branches. One's approximate density, one's tractable density. And so, the approximate density branch is in some sense unnormalized models or unnormalized distributions. And my favorite of which is the restricted Boltzmann machine. So, its precursor, the Hopfield network, was, is essentially a fully connected Ising model, right? John Hopfield, condensed matter physicist, by the way, so it's nice to see this all come full circle. The restricted Boltzmann machine has a probability distribution. This is the joint distribution between the visible and hidden units, right? Parameterized by a set of weights and biases, and I'll just imagine that I just have weights here for simplicity. But the visible units, there's n visible units for n qubits, okay? And they're Ising variables. They take a value of 0 or 1. And of course, there's h hidden units in the latent space, which are connected via these weights, which are the parameters that we want to optimize. And the latent space, or the hidden units, the number of hidden units can be adjusted in order to adjust the expressiveness of the model, right? So for a quantum wave function where we perhaps have a lot of entanglement or something like that, we can adjust it accordingly, by increasing the number of hidden units. So these, I'll mostly use restricted Boltzmann machines in the data that I'm showing coming up, just because they're sufficiently expressive and trainable. However, I also want to point out the other sub branch of the explicit density branch on this tree, which is the tractable density branch. And the tractable density branch is something we don't see all that much in physics, or maybe we're not all that sort of used to in physics. Because the tractable density branch essentially implies that we have some sort of normalized representation of a probability distribution. And so maybe the most familiar might be something like a NAID or an RNN. An RNN is a nice example where you would feed in a hidden vector, and instead of a word from a dictionary, if this is an NLP problem, you're feeding in a projective measurement from a qubit. That's your X. Right, and what you're getting out is the conditional probability distribution of the next qubit state in line, conditioned on all the previous ones. And then, of course, from this autoregressive property, the resulting joint distribution over all the qubits, if you will, is normalized. So there's a sort of very powerful new set of ideas related to these autoregressive models on this tractable density branch, which I believe are being introduced now into this field, and I think are really promising in terms of some of the physics I'm going to talk about. So all of these generative models can be used to represent probability distributions. They can learn probability distributions, from given data, from a quantum computer, from whatever else, and just by inverting the Born rule, if I assume that my wave function has no phases or no sign structures, then of course, simply the square root of the distribution that, whatever it is, the distribution that's in that black box or the model distribution is a faithful representation of the wave function. But of course, nature, conspires to be more complicated. And, a wave function typically has an amplitude and a phase, even if it's in the ground state or in a pure state. And even more complicated, of course, you typically get a high degree of mixing in most experiments, or at least some degree of mixing. And so what you might really want to represent is a density matrix. And so these seem at first glance to be outside the realm of generative models, but I think all I want to do is reassure the audience is that, essentially all generative models that I've encountered can be generalized in order to represent, quantum wave functions or quantum states corresponding to density matrices. And again, I find that Boltzmann machines to be, sort of very physical in terms of this understanding. So, for example, the plain Jane, conventional restricted Boltzmann machine and all of its cousins can, of course, represent probability distributions, which means sign-free wave functions. If you have to parameterize a phase, that can be done with another latent space, so another set of hidden units in some clever manner. And any sort of density matrix can be represented through a purification process, where you just add like another set of hidden units corresponding to the ancillaries that, if you will, purify your state. So this is sort of, this is sort of the most, I would say, plain vanilla version of representing wave functions and density matrices. And I think all of the, like I say, all of the generative models and all of their sort of iterations of different, different schemes for representing states. I'm going to simplify my life for most of the remainder of the talk by assuming a priori that the wave functions that I'm going to reconstruct inside of these generative models come from data which is drawn from a ground state that has no sign structure. And that might seem like a big restriction. However, it's actually something that occurs fairly commonly in many of these Hamiltonians that we're interested in condensed matter. And specifically, it's the Hamiltonians that we call stochastic. So given a basis, this is a basis dependent statement. If your Hamiltonian, which represents the interactions in your system in some sense, are, if the off-diagonal matrix elements are all negative, I think I did this right, then by the Perrin-Frobenius theorem, the extremal eigenvalues are real and of that Hamiltonian. The eigenvectors, in that basis are all real and positive. And so they're sign-free, and that includes the ground state wave function. So if I say that again, if I have a stochastic Hamiltonian, it means that I can make the assumption that my ground state is free of any phases or free of any signs. And so that's going to be it seems like a huge restriction. However, it happens to be exactly the case in my favorite experiments, which are the Rydberg atom array experiments that are coming out of various groups all over the world. I'm going to talk about what they are and what the Hamiltonian is in a minute, but what I'd like to sort of just start with is a little bit of an idea about what these experiments are like. And the images I'm showing here come from our collaborators at Harvard University that work largely within Misha Lukin's group. Misha also has a startup called QERA, which one of my students, Roger Luo, was involved in. And so the basic idea behind these experiments is that you have an atom, rubidium-87 or some other atom, which can be excited by a laser from its ground state into a high principal quantum number state, something like n equals 100-ish, which is a Rydberg state, okay? So that's what, I'll just use the term Rydberg atom, but it's a two-level system, so it's a qubit. There's a ground state and a Rydberg state, and this apparatus can be used to, number one, control the position of an array of these atoms using optical tweezers. It seems not that long ago there's a Nobel Prize for optical tweezers. Now, very large arrays of optical tweezers which can hold Rydberg atoms in any geometry that you can imagine can be constructed. It's actually amazing. These systems are loaded probabilistically, so you don't get 100% chance of an atom falling in every one of your optical tweezers at every point. But there's an algorithm, a feedback loop in these experiments where these atoms are rearranged to form a regular grid. Then once you have a full grid or an array that's full of the actual atoms, like rubidium, they're allowed to adiabatically evolve according to some Hamiltonian, which I'll show in the next slide. And so they're allowed to interact and evolve according to quantum mechanics into the ground state of the Hamiltonian at whatever time you're interested in. And then, just using a CCD camera, because there's fluorescence in, I forget if it's either the ground state or the Rydberg state, very clean projective measurements in that Rydberg occupation basis are sort of the results of these experiments. And so this is our data. We can get a large amount of high quality, binary data from these qubit systems, for system sizes, again, in the hundreds of qubits. So very powerful experiments capable of programming a variety of Hamiltonians. Actually, I'll show you the most basic one. Again, any lattices of any spacing in 1, 2, or 3 dimensions can in principle be constructed, and we get great data out of these systems. So the Hamiltonian, the essential Hamiltonian for the Rydberg atoms arrays, is this so-called blockade Hamiltonian. And the blockade Hamiltonian has 3 terms. Okay, one of them is associated with the Rabi frequency, or so, the frequency of the laser used to excite the state between the ground state and the Rydberg state. There's a term which breaks the symmetry, okay, between the ground state and the excited state. So we call that the detuning delta. So Ni is just the Rydberg occupation operator. It gives you a 0 or 1. There's a Rydberg state, that's site I. Okay, that I've written this sigma x as the off-diagonal piece, which flips you, between the 2 states of the qubit. And importantly, these are natural, of course, quantum systems. There's an interaction that is actually a decaying interaction. It decays with like a van der Waals type interaction, 1/R6. The strength of the interaction for any 2 positions of the array is adjusted by adjusting the lattice spacing, of the optical tweezers, actually. And so the point is that if 2 atoms in this array are too close together, according to whatever this interaction is, then there can be a significant energy penalty if they're both excited into the Rydberg state. And so that's what they call the Rydberg blockade Hamiltonian. So you can actually try to entice Rydberg states with the second term, but they will only form, atoms will only be excited, if they're sort of outside of each other's blockade. And so depending on the lattice geometry and the spacings and all the stuff, you can get a very rich ground state phase diagram from this type of Hamiltonian. And so that's what's been going on in these Harvard experiments. And I just threw up a couple phase diagrams, which have actually, been probed with simulations. But so, the basic features of these phase diagrams, which have been confirmed by experiments, are, on the left-hand side for small detuning. Sorry, I'm swapping out big and small deltas here. My bad. You get, the disordered phase is everything in its Rydberg state. And I'll show this in the next slide, which will make more sense. But as you increase detuning and you change the lattice spacings, which affect the Rydberg blockade, you'll get all sorts of different ordering wave vectors in the condensed matter sense here. And what's really fascinating about these experimental simulators is, the experimentalists are able to, and I won't get into this, I don't have time, but they're able to stabilize, quantum critical points. This experiment that came out of the Harvard group is the first time a 2+1 dimensional, quantum critical point in the Wilson-Fisher universality class has been realized experimentally. I find that fascinating. It's amazing. And also, on frustrated lattices, which I won't talk too much about, there's some fairly serious proposals for finding quantum spin liquids which again are, one of the holy grails of condensed matter research, is finding these things in nature. Anyway, that was just motivation for how cool these Rydberg atom systems are. Let's step back and look at a slightly simpler sort of phase diagram from the previous slide. And that is a one-dimensional Rydberg system, okay? And here's a simple phase diagram at the bottom here, where you can imagine tuning the system from everything in its ground state, let's say maybe that's the top image here, to depending on the interaction range or the Rydberg blockade radius, tuning, this system can be tuned across a quantum phase transition into different ordered states that have different ordering wave vectors, like pi or whatever. So Z2, Z3, Z4 states. So that those experiments, can produce data for us. Essentially any point of this detuning line. Let's stick to the kind of disordered Z2 phase, which we can use to train a generative model. So that's what we're going to do. We obtain data from these experiments. I would like to imagine that, we have a machine learning model attached to the optical table, but of course they just email us the data in reality. According to the shot budgets available at the time in this experiment, 3,000 projected measurements per various detuning parameters were available. We assume that the ground state of the experiment is pure. So we're going to use a pure state onsatz. And also, if we've got the Hamiltonian right here on this slide, again, which is stochastic, then we can assume that the wave function is real and positive. So, we can cook that into the sort of inductive bias of our model. And I'm not going to show any of the training of the generative models that we use for this. But after the generative models are trained, we're going to use them to produce new samples, which is what generative models do. They generate, right? And from those new samples, or that set of synthetic data that we can produce from the generative model, we'll produce estimators. Okay. So I hope that procedure was clear. You can interrupt me if you have any questions. I'm just going to jump straight into some results here. So these are the results from training a generative model on data obtained from a Rydberg array experiment in one dimension. Okay, so it's a simple one-dimensional system. And here's an example of the data. So for small detuning parameters, here's some number of atoms in the ground state. And as the detuning is increased, there's essentially a phase transition is crossed. And then here you see the Z2 state, which is, Rydberg ground state, Rydberg ground state, Rydberg ground state. And so I've just plotted, I don't know, I guess it's the density of ground state, ground state occupied lattice sites or something like that, as a function of detuning. And the black line is the experimental data. So like literally what you're seeing here, averaged over 3,000 measurements. ED means exact diagonalization. So this system is small enough that it can be, fully diagonalized. The Hamiltonian can be diagonalized to get the ground state wave function exactly. So that's kind of like what you hope the experiment is doing. You hope that you have the right Hamiltonian and the right dynamics that govern the system in the ED. And sure enough, for this measure, it matches between exact diagonalization and the experiment. What is the triangle? So the triangles is this generative modeling approach. So what we did again is we assumed positivity and purity of the wave function. We took the 3,000 measurements available at every single step here, and we fed them into a generative model. We trained it. And then once that generative model is trained, we produce samples of the visible layer. So, P of lambda x is the probability distribution that's approximated inside the generative model. The hidden units have been traced out in this case, right? So it's a joint distribution typically over x and h. H has been traced out. We can produce, x, I've used x and v interchangeably here. So x is the visible layers here. So we produce new data. And from that data, we can calculate clearly, any sort of expectation value of any diagonal operator. Okay, so if I have some diagonal operator and I have data drawn from this distribution, then I can like simply calculated. And that's what we've done here. And you can see a great match between the restricted Boltzmann machine and the actual experiment, which is to be expected in some sense. I mean, if everything's working well, of course, these things should match. So what's great about the generative models is, for those of you that do variational Monte Carlo or any sort of variational methods, of course, once you have that variational wave function in hand, right, you can do quite a bit with it. And so what the generative models do is give you this, like, it's not variational, but they give you this model wave function that's been trained from data in hand. And you can do all sorts of manipulations to get information out of it. For example, you can calculate the expectation value of off-diagonal operators. So here's the expectation value of the sigma x operator. So we have the exact diagonalization, the expectation, that the system should be governed by the Rydberg blockade Hamiltonian. This isn't something you can easily get from the Rydberg occupation data, in the Rydberg occupation basis. But if you train a generative model like an RBM, then you can form something that's well known to VMC people called the local estimator. And so the local estimator is written as an estimator over, the model distribution with this, additional, essentially ratio of the wave function for x prime and x, right? X prime is traced over. And so as long as this is a sufficiently sparse object, whatever that means, then, you can turn this into an estimator and estimate it directly from the generative model. So that, this is the same experiment as I showed on the previous slide, but now, we're comparing the reconstructed, wave function or the reconstructed estimator for sigma x to the exact diagonalization, and you can see significant discrepancies. And this is, I think, one point of what we're doing. We hope to be able to feed back, these types of quote unquote discrepancies or feedback back into the experiments. And in this case, the significant discrepancy was found to be due to some sort of calibration in the device, which was subsequently fixed. But you could imagine doing more fundamental sort of probes of the experiment using this stuff. So that's one thing you can do. You can calculate off-diagonal observables. You can get more sophisticated. You can take your generative model. You can do my favorite trick for calculating the second Renyi entropies by replicating the system and applying a swap operator. You can do this all, in the virtual, reconstructed wave function without having to do any sort of further experimental tricks. All the experiment has to give us, which is the forte of the experiment, really, is clean projective measurement data in the Rydberg occupation basis. And I guess this is an 8-site system where I've, divided the system into region A and B, calculated the bipartite second Renyi entropy, and I've compared the restricted Boltzmann machine results to what we expect from exact diagonalization. And you can see, I believe, how well the experiment is doing in capturing the entanglement that it intends to capture, given the model that they're trying to design in the device. So this is all fairly basic in some sense, but I think it illustrates a kind of a nice feature of how these generative models can be used to leverage data. And so for the last couple minutes, I just want to look forward to the future. What are we going to use this technology for? So I think one obvious thing is to, again, once these experiments get into the hundreds and thousands of atoms, neutral atoms range, which they clearly are getting at now, there's a lot of information that, we'll want to extract from this data set. And, for example, if I'm looking for a spin liquid in some region of the ground state phase diagram, we may want to calculate the topological entanglement entropy for the, condensed matter experts out there. So one way to do that is to take all that data, just take clean projective measurement data, feed it into a generative model, do what I did on the previous slide, calculate the second Renyi entropies, and do all sorts of geometries, that you can help identify, for example, these exotic phases of matter. So, it's just helping you leverage your data in sophisticated ways to do exploration and discovery of matter and materials. I believe, there is a role for generative models in, I think in other systems. So moving away from Rydberg blockade systems, either systems like trapped ions that you can apply, rotations to perform measurements in other bases, or sort of any sort of general quantum circuit. This kind of trick that I use to enhance the estimators in some sense using a generative model can be used in other contexts. One example I really liked from this group a year ago, it showed how the sample complexity of estimators for, in this case, the energy of some sort of small molecules, it can be enhanced with generative models. So when you have a generative model, just like in the previous slides that I showed, you can train it from projective measurement data, in this case, in multiple bases. Once that thing's trained, it can be sampled as much as you want. So you can get a very, very small variance on whatever estimator you calculate in it. If you have some sort of limited data set that's coming out of the machine, that thing, the equivalent variance can be very large. And so what you're trading is sort of a lot of variance for hopefully a little bit of bias. There's a bias variance trade-off here. But it really affects your sample complexity. So M is the amount of samples required in this case to reach a certain amount of accuracy in your energy, what they call chemical accuracy. And let me just say, QC is just kind of if you're just taking the measurement straight out of the quantum computer, and QC plus NN is with a generative model. So you can see orders of magnitude improvement of the sample complexity required to get a certain energy, just by leveraging generative modeling, right? So in some sense, you're smoothing the data, you're interpolating, you're doing all these things that generative models do, but they buy you a couple of orders of magnitude in your sample complexity, which for a real experimental quantum device is very important. I think the last kind of example I'll imagine is just sort of like, how we combine, generative and say other types of optimization, not from data. So data-driven generative model and say variational methods. So one nice thing about these models is that, they're kind of generic in the sense that, they can be used in the data-driven context, like I've been talking about. But you can also assume knowledge of the Hamiltonian and try to update the parameters based on the variational principle, I think, which we're all used to. And I think that was pointed out very nicely in the recent paper, which leveraged, a combination of data-driven and variational methods. And so you can imagine doing some early phase training with the data, followed by additional variational steps. And that could help kind of smooth out the errors, like the thermal errors or the measurement errors of the data. Or in some cases, we know that variational methods don't work very well on some large frustrated condensed matter type systems. And, enhancing that variational exploration with actual data from a real quantum computer, I believe will help, in the optimization of the variational method. And I think that's where the sort of idea of quantum advantage will really lie on these large simulators is in the near term. I think we'll be leveraging data, to help hybridize between different methods. And I think the point is that the data optimization with maximum likelihood, the parameter optimization through maximum likelihood, or the parameter optimization through the variational method, actually can have very different optimization landscapes. So I'm out of time, so let me just throw the discussion up. The one point I hope to get across was that standard generative models are today being used to reconstruct states, and we're going to hear in the next talk about, I think, a more tomography approach, maybe a little less hand wavy than what I just showed you. Also, what I hope to get across is that there's many architectures that we can adopt from standard machine learning, and one of, I think, the most intriguing is either transformers or RNNs. Two-dimensional RNNs have been constructed now that are very promising. And also, all of these architectures, like I said, can be used variationally. And so what is the future of all this? I really believe that in the very near future, even today, a hybridized method where we're leveraging both knowledge of the Hamiltonian and data that comes from quantum computers, right, to basically both share in the task of training generative models is going to be a very powerful paradigm going forward. Thank you very much for your attention. Hopefully, we have a couple minutes for questions if there are.
Yeah. Thanks for the great talk. And yeah, Enrico, please go ahead.
Oh, yeah. Thank you very much. Can you hear me?
I can hear you.
Yeah. Thanks, Roger. Actually, this was great also introduction for my talk tomorrow with generative models. My question is about the scaling of these models to, well, first of all, larger systems, 2-dimensional, 3-dimensional maybe, or even what is the scaling with the size of the system? And then how much training data do you need? So if you want to use it for quantum circuits, like you were showing in your future of simulation, quantum simulation slide, how much data is required, and how do these things scale? Thank you.
Yeah, good question. And I think what I like about these systems that we're looking at now is you can actually address this concretely with simulation studies. So we do have some, I should have a citation here, but I forgot. Maybe it's on the slide. Okay, so there's a citation. So we have performed scaling studies, okay? So for example, the transverse field Ising model, which we can generate data with quantum Monte Carlo, and we can, which is the same kind of class as the Rydberg blockade. We can ask, how many hidden units or how large of a latent space do you need to get a good energy, good accuracy on your energy. And, here is number of hidden units versus number of qubits, okay? And this is, the black is a quantum critical point, and the other lines are moving away from the quantum critical point. And you can, I can't get into it, but you can compare this to MPS and other tensor network methods. So generally, yes, you can study these things. It's a big open question, and you can ask how different architectures scale, how RBMs versus RNNs versus transformers scale, wide open. I would encourage people to study this, actually.
Yeah, so you don't actually, for this system, you don't need anything that is deeper than just one layer, right? Just an RBM. Right.
You could do deep networks again and study the scaling. You can study the sample complexity, and we've had some studies of the sample complexity. I don't have any slots here, but you have to have an informationally complete data set in principle, but how much data really for one of these systems depends on I think all sorts of features of the interactions and so on. So completely wide open field, which I think is like one of the most interesting things we could be working on.
Yeah, these things are now also being used for quantum field theory, quantum chromodynamic simulations, and yeah, it's very interesting. Thank you.
Thanks for the question.
Thank you. So since we are running out of time, and we also have a question in the Q&A, so please, would you answer by text?
Certainly.
Okay,
yes.
Thanks.
Thank you.
So we will go on to the next talk, and it is from Clemens from Riken, and he's going to talk about eigenstate extraction with neural network tomography. So please go ahead.
Yes, thank you very much for the introduction. Can you hear me?
Yes.
Can you see my screen?
Yes.
Okay, great, thank you. Yeah, we all know that this talk is about quantum state tomography, and we all know that quantum state tomography is, of course, more important than ever to assess the quality of state production in experiments. But we also know that quantum tomography can be a very challenging big data problem, which makes it, of course, interesting for machine learning approaches. And as a matter of fact, in the previous talk, we have already met one of the pioneers for applying machine learning to these kind of questions. Now, in this talk, I would like to present or in some detail our contribution to this, which is a method how to promote machine learning pure state tomography towards full-fledged mixed state tomography by extracting the eigenstates of the mixed state. Now, let me briefly introduce the collaborators for this project. I mean, this was joint work together with Abhijit Melkani, who used to be an internship student in our group and who is now at the University of Oregon, and with Franco Nori, who is the head of our group here at RIKEN. Now that's the outline of my talk. In the beginning, I will briefly recapitulate why tomography is such a challenging problem if you scale to larger systems. In the second part, I will then introduce the concept of neural network quantum states, which are based on restricted Boltzmann machines, as we have already learned in Roger's talk, and which can be used for pure state tomography. Then in the third part, I will present our approach, how this pure state tomography can be promoted to mixed state tomography by the iterative eigenstate reconstruction. And if I have time, I will in the last part briefly elaborate how the extraction of the dominant eigenstate could actually work as a scheme for error mitigation. Okay, now let me briefly recapitulate the challenge of quantum state tomography. I mean, very briefly, quantum state tomography, we all know it's meant to reconstruct quantum states from measurements, and in the states generated in the experiment are generically mixed states. So in the simplest case of a single qubit, we can parameterize the density general state by a Bloch vector, and which has 3 components. And then if we measure, like say, the Pauli matrices in the basis of the Pauli matrices, then we can reconstruct the full state. Yeah. But in the case of n qubits, then if we want to perform measurements in all possible Pauli combinations, we would already have 4 to the n measurements, which scales exponentially. Of course, we don't have to do all these measurements, but that's the scaling behavior is basically what it is. Yeah. And also in terms of the post-processing cost, we have, in general, the states are mixed, but in the experimental data is also noisy. So we have to do a maximum likelihood estimation, ideally, which is also very costly. And as a consequence, for example, there was an experiment with trapped ions in 2005, where they generated an 8-qubit state, an approximate W state. And it took them an entire week to reconstruct the full quantum state using maximum likelihood estimation. Of course, there are clever ways of speeding this up, for example, by exploiting compressed sensing or linear regression. But the general challenge remains that this scaling for large systems is very is in general exponential. Yeah. And this then, of course, raises the question. I mean, we see we have in quantum state tomography this big data challenge, and we know machine learning has been designed to cope with such big data problems. And this, then it's of course natural to ask if machine learning can help with quantum state tomography. And this is what I will try to elaborate in the following. Now, the specific flavor of machine learning model that I want to focus on is so-called restricted Boltzmann machine. We have already heard about it a lot in Roger's talk. And let me also just briefly summarize the main idea. I mean, on the one hand, we can think of it as like a 2-layer neural network where we have a visible layer and a hidden layer, and they are coupled by the weights. And there's also biases, but they are not shown in this graphic. But on the other hand, we can also think of this as a physical model, as physics inspired. We can think of it as a spin model, where the couplings, the W's can be thought of as like the couplings. And correspondingly, we can associate to this model energy function, a Hamiltonian. Yeah, and the restricted in the name refers to the fact that we don't have interactions between the spins within one layer. Now, from the energy function, we can, of course, formulate the Boltzmann distribution, which is a probability distribution. And then the target distribution that we are interested in and that we want to model is the marginal of the visible layer. So we trace out the hidden layer. Yeah? And one of the appealing things about restricted Boltzmann machines is that they can very efficiently be sampled by Gibbs sampling, where we don't need to know the normalization. Roger emphasized this as well. And it's a generative model in the sense that we can we can get samples of this probability distribution by just running the Boltzmann machine. Yeah? Now, how can we use the RBM, the restricted Boltzmann machine, to describe a quantum state, a wave function? Now, the idea is in principle pretty simple. Let me also briefly repeat this. We just, I mean, at least in the case of qubits, we can associate to each qubit. I mean, we pick a specific basis, the canonical basis, and then we associate to each qubit like a spin in the visible layer. And we already know the wave function describes a probability amplitude, so we are already close to and then this basically the restricted Boltzmann machine can then capture this probability distribution, but we also have the phase, and for the phase we can just use another RBM or even just a simple feed-forward neural network, because it's not so necessary here to model it as a probability distribution. Now, this kind of description was, to the best of my knowledge, first introduced by Kaleo and Treuer in 2017, where they showed that this is very efficient to approximate complex, highly entangled states. And the training example that they gave was like, for example, to train the ground state of a complex Hamiltonian, for example, transverse Ising model, for as many as 80 spins, and they got very good results. Now, in that case, the training happens by using, in the sense of like an optimization, because we assume that we know the Hamiltonian. So this is not really data-driven. Yeah? Now, since then, this kind of approach has been used for many problems, like in many-body physics, but also, for example, to describe the dynamics of quantum systems. And what will be relevant here, also, for example, to do quantum state tomographies. Now, these references here are not meant to be exhaustive. This is just a few of the references of some of the early works. Yeah. Now, as we have already seen in the previous talk, we can use the neural network quantum states for pure state tomography. Yeah, I mean, and this is now really data-driven problem, in the sense that the measurement data, we use density measurements to train our RBM, our restricted Boltzmann machine. And as the cost function, we now use the Kullback-Leibler divergence, which basically can be thought of as a distance between two probability distributions. Now, this kind of approach to tomography was introduced by Toilai et al. In 2018. And they could show that this is very powerful for this job. And also an important message was that the number of measurements that's required is substantially reduced, so which reduces the experimental burden. And in that paper, for example, they successfully recovered W states for up to 20 qubits, yeah, with a fidelity close to 1. Now, this is only for pure states, but in experiments, of course, we usually encounter mixed states. And one way of approaching this problem is by purification. What we do there is we add another hidden layer, which we identify as the environment, and then we first trace over the environment and then over the hidden units to obtain the probability distribution that we want to model. Yeah. Now, this way we can, so to speak, reconstruct the full density matrix at once, but the cost here is, so to speak, that we have to introduce this additional extra layer of hidden units for the environment. And also the training becomes more complicated due to the fact that we have to trace over the environment. So now, in view of the fact that the pure state tomography is so powerful, we then were wondering if maybe we can leverage the pure state tomography to do mixed state tomography. And this is what I will talk about in the following. So our approach now is based on the idea that we can iteratively reconstruct the eigenstates. So let's first discuss how we can treat the dominant eigenstate. So let's assume we have, to understand this better, let's assume our density matrix is described by, has a spectral decomposition of pure states psi I, or eigenstates psi I, and corresponding eigenvalues pi, which are ordered by their magnitude. So psi 1 and p1 would be the dominant eigenstate and eigenvalue respectively. Now, the essential result here now is that one can show that the closest pure state to our actual mixed state is the dominant eigenstate of the mixed state. Yeah. So this means if we choose the distance measure as our cost function, then we necessarily will run into the dominant eigenstate. So this allows us to identify or to find the dominant eigenstate. But of course, we don't know the full state. We only have the measurement. So all that we can do is approximate the distance measure through the measurements. And for this, it's therefore encouraging or useful or good to know that this property that the dominant eigenstate is the closest pure state is robust under variation of different distance measures. So. Okay, this then allows us to formulate the following iterative procedure. We first use the pure state tomography to retrieve the dominant eigenstate based on our measurements, which we here model as projective measurements. Then from this dominant eigenstate, we calculate, so to speak, like another set of predicted measurements that correspond to the dominant eigenstate. And then we use this to estimate the dominant eigenvalue, and how this can be achieved, I will explain in the next slide. Now, knowing the dominant eigenvalue, we can define some sort of fictitious density matrix, which is our original density matrix, where we subtract the contribution of the dominant eigenstate. Now, using our actual measurement data and the calculated measurement data from the dominant eigenstate, we can then calculate, so to speak, again, fictitious measurement data for our auxiliary state rho prime. And then with this data, we can return to step 1 and continue to retrieve the next, the subdominant eigenstate and so forth. So in principle, this routine allows us to recover the eigenstates up to a desired rank, or if you want, to the full density matrix. Now, the dominant eigenvalue, how can we estimate it? For this, is important that we need to make sure that the measurements that the measurement remain well defined, in the sense that we get positive probabilities. Now, if we use this as, so to speak, as the basis to formulate our estimate, then we obtain this expression, and it has some nice properties. For example, this guarantees that the state remains well defined, the auxiliary state, and also in some instances it's exact, or usually you can assume if the dominant eigenstate is close, approximation is close to the exact dominant eigenstate, then it will always be bounded by the actual eigenvalue. Yeah. Let me just say a few words about the training. I mean, I just would like to mention here that this specific problem where we have the dominant, where we want to extract the dominant eigenstate, we found that the optimal choice of cost function is actually not the Kullback-Leibler function, but a modified cost function, which is based on the curious enough, the L1.5 norm, which seems to best exploit the characteristic differences between the mixed state and the dominant eigenstate. Yeah. Okay, now let's come to a real-world application. Now we applied this method to experimental data that's on the internet, and where they performed Tursday experiments with 4 to 8 qubits, and they generated an approximate W state. And they performed random informationally complete set of random Pauli measurements. Yeah. And this is what we find. This table summarizes, so to speak, our results. Now, the first, this first box here shows the properties of the actual reconstructed state from the maximum likelihood estimation, so that we assume this is the real reconstructed state, and the first dominant eigenvalue, the second eigenvalue, and the third eigenvalue. And here in this red box, we see the fidelity of our dominant eigenstate reconstruction with the actual dominant eigenstate, and we find that we obtain double-digit, so to speak, precision here. Yeah, so this eigenstate, the eigenstate extraction, dominant eigenstate extraction works very reliably. Now, about the dominant eigenvalue extraction is not so reliable, which is of course a consequence of the way of how we estimate it. So this the deviation grows with the number of qubits, yeah, and correspondingly also the estimate of the second eigenvector then starts to deteriorate. But what I still would like to highlight here is that if we look at the fidelity of the actual reconstructed state from the maximum likelihood with the desired target state, then of course we see that the fidelity, that there's a substantial offset and the fidelity rapidly drops. But if we look at the fidelity between the target state and the approximated dominated eigenstate that we obtained from the data, then we find that this the fidelity remains high, which of course tells us that the reconstructed dominant eigenstate can be seen as a very good approximation to the target state. Let me very briefly comment on the benefits and challenges. Of course, one of the main benefits is that we can reconstruct the dominant eigenstate very reliably, and that the scaling, as long as we stay at a low rank, this scaling is favorable as compared to like a full rank reconstruction, and the rank can also be chosen flexibly on the fly. The challenge, of course, is the eigenvalue estimation, which ideally should still be improved. And here we hope that this can be achieved by moving to adaptive measurements. Now, this is now my last slide before I conclude. I would just very briefly mention that the fact that the dominant eigenstate can be such a good approximation to the target state can, of course, also be taken as a means for error mitigation. Yeah? And in fact, some error mitigation schemes are indeed explicitly designed to distill the dominant eigenstate, for example, virtual distillation or derangement. But these schemes require a qubit tape overhead of typically a factor 2 to 4, which is not the case if you do the pure state tomography. But of course, the pure state tomography is computationally costly and also in terms of measurement, but it can still be significantly less costly than a full rank tomography. Yeah? And in that sense, combining the quantum process with pure state tomography can still like be advantages as compared to doing a full-fledged classical simulation. Yeah, and I think this is also similar in spirit what Roger mentioned in his talk when he presented the generative models for quantum simulation. Now, let me briefly conclude. The focus of the talk was like our scheme for eigenstate extraction, which is cost efficient as compared to the full state reconstruction and scalable. And importantly, of course, it delivers the most relevant, arguably the most relevant information about the generated quantum state, which is the dominant eigenstate and the dominant eigenvalue. And for that reason, it might also be useful for error mitigation. Now, another thing that I would like to mention is that this eigenstate extraction approach is not necessarily attached to the neural network state ansatz, but of course, this idea can also be applied to other ansatz classes, such as, for example, tensor network states. Okay, that's it. Thank you very much for your attention. And Franco asked me to show you, to advertise that there are open positions on machine learning applied to quantum computing in our group. Thank you very much, and I'm looking forward to the questions.
Okay, thanks for a very nice talk. Is there any questions from the audience? We have we are actually running out of time. So if there's no questions, I would like to go
question in the chat.
In the chat, okay, nice, thanks. So do you have an estimation of the efficiency and resource during the mixed state tomography? And does it require a low rank density matrix to have an advantage over traditional tomography? Do you have?
Okay, thank you very much for the question. I mean, it's two questions. I mean, the efficiency or the required resources are pretty much the same as for the pure state tomography, I would say. This is, I mean, generally we know that to do the maximum likelihood estimation or to have an informationally complete set of measurements, we need the number of required measurements experimentally scales exponentially. And I think this this scaling behavior probably cannot be changed, but at least for the pure state tomography, it has been shown, for example, in this paper that one can still use a substantially reduced number of measurements as compared to as one would need for full mixed state reconstruction. And also compressed sensing is also in the similar spirit, like a scheme that shows that one can have a substantially reduced number of measurements. So in that sense, there is a scaling advantage between mixed state tomography and pure state tomography. But of course, the scaling advantage between our iterative scheme and like a scheme that aims at, or that reconstructs the full mixed state at once, so to speak, is that we can do it, we can reconstruct the state eigenstate by eigenstate wise, yeah, and that way the scaling can be the scaling of our state reconstruction can be substantially advantageous as compared to the full rank reconstruction. If the rank that we want to reconstruct, like R, is much smaller than N, then this can be much smaller than the full rank reconstruction. Yeah. And the second question.
I guess we are running out of time, and Would you answer by text in the chat, maybe?
Okay, yeah, I can.
Thanks.
Thank you.
Thanks, great. Okay, now I would like to go on to the next speaker, and next speaker is Mattia from Columbia University, and he is going to talk about the classical variation simulation of the QAOA.
I can't share my
Clemens,
screen.
could you
so.
stop sharing, please? Clemens?
Yes, sorry.
Mattia, go ahead.
Yep, can you see my slides?
Perfect.
Cool. So hi, everyone. My name is Mattia. I'm a grad student at Columbia, but honestly, mostly at Flatiron Institute these days, where I work on applications of machine learning to quantum problems with Dries cells. However, this work was performed with Giuseppe Carleo some time ago while he was at Flatiron. Happy to be here. It was an exciting conference. Thank you to all of the organizers. It kind of, the best compliment I can give you is the fact that I'm awake right now and talking to you, even though it's almost 11 p.m. right here. And I've been doing that for the past week. So thank you. So yeah, in this work, we use machine learning techniques to tackle hybrid quantum algorithms, which is an important class of algorithms, which I'm sure all of you are aware of, and with prospects of being useful on near-term quantum hardware. There's a bunch of these algorithms that have been used both in the simulated environments in classical computers and on quantum hardware itself. We specifically our specific aim here was to use a classical machine learning technique to boost the classical simulation capacity of modern classical computers to do something that's useful for benchmarking quantum hardware. Specifically, QAOA has gotten a lot of attention recently from all of the papers, mainly from Google, about, So I thought being original would make this joke in the last bullet point here. So we're actually using machine learning for quantum technologies instead of quantum technologies for techniques for machine learning. But it turns out that many people have made this point over the past week. So I'm not being that original with that joke here. So yes, swap operator is being applied here. Bear that in mind. Right. So to briefly brush up on what QAOA is, it's an algorithm that what we use it for and what most people use it for when they benchmark its performance and so on is on calculating the max cut of a graph, which is just, can you find a bipartition of this graph in order to cut as many edges as possible? We focus on three regular graphs, and I'm sure most of you here know what QAOA is. It's a variational quantum algorithm that I'm about to describe in this slide. So the way you do it is you essentially build a quantum neural network, quote unquote, where you have a bunch of parameters labeled gamma and beta here. You have a cost function, which is a second degree. It's a quadratic form in Pauli operators in this case for the max cut problem specifically. And you initialize your problem with a coherent superposition of all of the basis states. All the computational basis states on the left-hand side. You apply the cost operator rotations pairwise with respect to every qubit in the underlying graph. Then you perform X rotations and so on, and you call all of these betas and gammas your variational parameters, and then you use, hopefully, given enough computational capacity, your favorite external classical gradient-based optimizer to modify these beta and gammas to find the quantum state that minimizes this cost function of yours. Okay. What we use, so for this, can you see my mouse pointer? Is this?
Yes, we can.
Okay, cool. So the idea that we had, since restricted Boltzmann machines, as I've briefly announced by showing this slide, the idea is to have a restricted Boltzmann machine instead of representing famous spin states, which is why they are these days your favorite machine learning method of every condensed matter physicist. Instead of spin states, those are pretty much equivalent to many qubit wave functions. So at each point in this quantum circuit, say along this slice, we represent the entirety of the many qubit wave function using a restricted Boltzmann machine, which you've seen quite a few times by this point in various talks. Which is basically this. Instead of summing -1s and 1s, we sum 0s and 1s, but the idea remains the same. You have your hidden units, you have your visible units, and you can use your favorite Monte Carlo technique to sample this thing. Right. So it's an entirely classical thing, playing a quantum wave function in a quantum machine learning setting. So that's how far we got so far. Right. So it's not a new thing that we're doing. Trying to make a general quantum simulator out of restricted Boltzmann machines has been done before. And the reason why we even want to use RBMs to try this is the fact that we can get away with applying some quantum gates exactly. So you can identically take some of the parameters out of your RBM, do an operation on them, like switch them, give them a shift or give them a minus sign, and that operation will correspond to a quantum gate being applied to your restricted Boltzmann machine state. An example here is the Pauli Z state, or the diagonal one, the easiest one. And you can just, shift your visible bias corresponding to the qubit you want to apply this gate to by I pi, and your new state that comes out of this operation will be the many qubit quantum states corresponding to this gate being applied, right? However, not all gates are as nice, and we cannot do all of this. We cannot do this operation for absolutely every gate. And the core idea here, the core problem, is the fact that a superposition of restricted Boltzmann machines, and you have two of these ansatzes and you try to add them together with some coefficients, those cannot be analytically rewritten as a single RBM. So any sort of gate that forms superpositions will not be amenable to this type of treatment, which is a problem for this framework. However, we only set off to optimize this thing approximately. So this is an approximate simulator, not an exact one. And as such, we can a cost function, namely the fidelity, the most obvious one, or the infidelity, since we're used to minimizing things. We can minimize the infidelity between your RBM states and any sort of target state denoted by phi here. And the way we do this is you basically write down an operator that corresponds to your target state here, and you use your usual variational Monte Carlo techniques to find the ground state of this. What we call it Hamiltonian, only in the states that your target state is encoded as the ground states or the least eigenvalue eigenvector of this effective Hamiltonian. So you want to reach that state approximately using well-established classical optimizers, and then you can get an approximation of the output state. That way, if you set your phi to be a superposition of two RBMs, given some constants alpha and beta here, you can get away with, we found out, you can get away with pretty high fidelities in approximating various superpositions of these RBMs. However, there's one important caveat which is new to this work, in the sense that other works that have tried this has been a trip up, so to speak, for them. Optimizer choice seems to matter very much. So if you just use your naive first order optimizers like stochastic gradient descent or more machine learning choices like Atom or similar, you will not have a good time, and you will only reach fidelities of order, you giving a ballpark figure of 60 to 70% per gate, which add up quickly to just destroy any sort of signal you have in your system. If you end up using a quantum natural gradient or stochastic reconfiguration, if you're from the BMC side of things, then this performs much better, and we can get fidelities north of 0.99% for some gates. So to summarize what I've just told you, there are two classes of gates. One class of gates we can do exactly, and one class of gates we have to approximate. So namely those single qubit gates and two qubit gates, which are diagonal or off diagonal, we can do exactly by manipulating RBM parameters in a clever way. And we must approximate gates that are that form superpositions, and we can do this by using well-established classical optimizers, or namely quantum natural gradient. There's one caveat that I haven't told you here. If you have a 2-qubit gate and you want to apply it exactly, and this specific gate is relevant for QAOA, the way you do it is to introduce an additional hidden unit that only couples to the 2 qubits you're applying your gate to. So you introduce an additional hidden unit, and you set the coupling constants to this new hidden unit to some specified values which you can derive. However, this turns out to be a problem, as I'll get to in a second. So just again, to reiterate this point, we have stacks of gates in QAOA. So one stack we can do exactly, the other stack we can do approximately, and these exchange until you have had enough of simulating all of this. Right. As I've noted, you need to introduce extra parameters or extra hidden units every time you want to apply a 2-qubit gate. This can be problematic when simulating deep circuits because you can have a blow up in the number of variational parameters you're trying to handle here. A solution that we cooked up is to perform a compression step. And that means at some point when you've decided that you've had enough variational parameters, what you can do is take your old large bloated RBM with a lot of hopefully redundant parameters. You can construct a new smaller one and then fit the smaller one using, again, standard techniques, and just optimize the fidelity between the smaller one and the larger one. And you optimize in a way to find optimal values of the parameters of the smaller one. So this is outlined, the way we do it is outlined in this circuit diagram. So after you've introduced the number of hidden units by the first layer, each subsequent time you apply the cost operator to your RBM, you then perform this compression step. So we found that this is almost never a problem in the sense that you can always reach fidelities, many qubit total fidelities in systems that we've tested north of 95%. And this compression step is not introducing any sort of larger errors that we've already had. This is just an example of the kind of replacement rules you can do to apply different Pauli operators. So basically, you manipulate hidden and visible units by hand, and you make these replacements in order to apply gates. No need to remember these. Just I wanted to give you a taste of what this looks like. This is for the 2-qubit gates. You introduce these weights based on the rotation you want to apply. Again, not very complicated. It's a half a page of math on. Once you decided to sit down and do it. And finally, it's time for some results. So we use this to perform, well, at least I'm trying to be modest here, but it's a pretty large quantum system. I mean, this is the test case. So the test case for 20 qubits is a test case precisely because it's fairly small within the bounds of reason, in the sense that we can do it. We can simulate it using your favorite software package for simulating quantum computers. And we find that RBMs do reproduce both error landscapes of QAOA pretty nicely, both for depth equals to 1 and depth equals to 2. So we can see that QAOA, when you add another layer to it, you can get lower values of the cost function, which is one of the predictions of the original paper. And you can see some scalings of the output fidelity of the fidelity between the RBM state and the state output by your RBM. So you can see that it scales down, but if you take a closer look at the y-axis, all of this is larger than 90%. So we're still probably good. One reason I can hand wave as to why any of this works is because your output of QAOA is essentially a classical state. You might take a very quantum walk through different very quantum states in order to reach that final classical state. But the point is that your output state for the solution of your max cut problem is just going to be hopefully going to be one single computational basis vector. That means it's going to be ones for the corresponding to vertices in one partition of your max cut and zeros for the vertices in the other partition of your max cut. So it's just one computational basis state, and there's no reason why classical methods could not be tailor-made to simulate QAOA. So onto our main results, we were able to scale this up all the way to 54 qubits, at which point most classical simulators would not give us a reference quantum state to calculate fidelities between. However, we can give you some QAOA cost function landscapes, both for p equals 1, p equals 2, and all the way up to 4. And we can still see that you can find optimal angles such that QAOA reaches lower values in its cost function as you add more and more parameters. However, on the right-hand side is a slightly more interesting point, depending on how you look at it, is this is the best we could do in terms of estimating the kind of performance we're getting out of this model, and or even just trying to make sense of the output state, since we don't have a full 54 qubits wave vector to compare this against. So as I mentioned, in the process of optimizing all of this, you explicitly calculate fidelities because that's what you're optimizing. You calculate the value of your cost function and its gradients. So, and you're forced to do this optimization for each single qubit. So when you want to apply X rotations for each qubit, you do this small optimization in order to apply this X rotation to your RBM state. And you can see that for optimal angles, right here where this dashed line is, we get pretty good fidelities. And however, for when you increase your QAOA angles, you go into higher and higher up values, you see away from the optimum, you see that your these types of intermediate fidelities get lower and lower, and your output state is not as good of a representation of the actual output of QAOA that the QAOA would have in a completely error-corrected quantum computer in this case. So again, this color bar is completely, so the lowest value on this color bar is 90%. So none of these are terrible, but when you have 54 qubits and each of them you have 90%, this is, you basically adds up to being very, very unusable. So again, 54 qubits, it's a good result, and the best we can say about these types of estimates. You can really see the statement I'm trying to make here is that the higher, the closer you are to optimal QAOA angles, the more you are, the better performance our model has. Oops, I made a noise instead of switching slides. There we go. So in a brief summary and outlook slide, I wanted to just say that we introduced a novel approximate method for simulating QAOA, and we applied it to pretty large systems of pretty large qubits. In principle, what we have here is a general purpose quantum simulator because we have recipes for simulating both easy and hard gates, but I just wanted to mention something since I have a minute or two left before people start yelling at me. I wanted to say that we did try all of this on a much harder quantum circuit than just QAOA, which is just a random circuit. You pick out of a universal set of gates and you try to see what kind of output distribution you get out of your RBM in relation to what you would expect from a perfectly unitary quantum computer. And then this just falls apart completely. So the claim here isn't we have a neural network quantum simulator, is that and instead the claim is if you have a quantum circuit that's in some sense sufficiently close to a classical circuit, this can boost the number of qubits that you have and give you an output that's that you can use to compare with large-scale NISQ hardware. And the only thing we have to compete with here is instead of saying, oh, it has some error because it's variational, well, also NISQ hardware has some sort of error because it's noisy. So the competition here is not on that level. So you can use these states to compare against NISQ outputs, and that's been the main point of this work, is saying that QAOA is interesting because we can simulate it and because we can use it to benchmark things. For the future, again, more expressive choices of variational wave functions. Again, RBMs are not the most sophisticated method of the model out there. You can use a gazillion parameters in your favorite neural network and do this do the same thing, but then you would lose the ability to apply some of the quantum gates exactly. This might be a worthwhile trade-off. I can't say right now, but it's something to explore in the future. And again, you can try and apply this to different interesting quantum circuits and try, look into the type of parameters that you have. So again, emphasizing this is a new and interesting method for simulating complete output many body wave functions in a variational fashion, storing only very few qubits. And now, since I do have 2 more minutes left, I'm going to donate one of them to the organizers. Don't worry. I noticed that in the schedule there is a industry session after me, so I couldn't resist putting in this slide. I mean, there's code available, sure, but also a slide of shameless self-promotion is that I'm currently looking for internships in industry. So if someone wants to hire me, please do. I think I do interesting research, but that's on you to say. So thank you. I'm going to leave this slide up here. Maybe someone notices my name in applications and says, yeah, I want this guy. So yeah.
Okay. Well, thanks for that very interesting talk. And if there are any questions from the audience, yeah, there is. Please go ahead, Enrico.
Oh, thank you very much for the talk. I have a question about if there is any similarity between your method and other methods based on tensor networks to do these simulations.
Yes. Similarities in the sense that we've made the comparison in the paper, and we see that our method scales much better in the number of parameters. I can give you the graph. I have some backup slides here. This is the graph.
Oh, you're right.
It's basically, so in order to reach the same performance using an MPS ansatz, you would have to have on the order of 10 to, I forget the exact number, this calculation was done a while ago, but something on the order of 10 to the 12 parameters in your MPS, and bond dimensions blow up very quickly. And the reason for this is because QAOA lives on just graphs, right? It's not a linear thing for which you can do DMRG.
Yes. So it's basically a better version of a tensor method based on the structure of the graph that QAOA has.
Exactly. So we just use a fully connected RBM that does not care about the graph structure, as opposed to which makes them bring things closer to each other.
Cool. Thank you very much.
That makes sense. Yep.
Thank you. Any other questions?
I'm gonna slowly just slide back up the slide.
That's nice. So I have a small question about this.
Sorry.
So how do you estimate the inner product between these different RBM states?
Right. So there's again, this inner product is again, backup slide. I have this.
Okay.
Right. This top line here, this is just a bunch of formulas. If anyone asks me about math here, I have this slide. But basically, this top states, the fidelity between two states, you can exactly rewrite as a product of two averages. And if you remember Roger Melko's talk from a bit like an hour ago, this is just the reparametrization trick done on the fidelity. So you can rewrite it in a way you can sample the probability distribution corresponding to the RBM via the Born rule, and you can sample RBMs and use those samples to calculate the fidelity here.
I see.
It's not a terribly sophisticated thing that you just, sometimes you need a lot of sample to get decent error bars for this.
Okay.
The Monte Carlo thing. And like any Monte Carlo thing, it's going to depend on Monte Carlo problems.
Okay, thanks. Any other questions from the audience? So if not, I would just close the session. And we'll be in lunch break for about an hour, maybe.
Yes, we will meet again less than an hour. So we meet again at 1:30 p.m. Tokyo time. So less than an hour. But thank you to all the speakers for all the wonderful talks, and thank you, Kosuke, for chairing the session. So see you again. See you all again, hopefully soon in an hour, less than an hour, 50 minutes.
Okay,
thank you. Michele,
Yes.
Michele, ci sei?
Yes. Good morning, everyone. Hello. Can you hear me?
Good morning to you.
Yeah.
How are you?
Well, fine. I hope you can see me. Let me just.
I can see you very well. I can see you very well.
Maybe it's better.
So okay, so I asked them to turn on the chat feature of YouTube actually, so we also have a chat. I asked Rinaldo and Enrico Rinaldi to actually do one monitor
Okay.
feature. Because normally actually they keep the chat features off. They keep all the comments and chat feature off, but I asked them to do it just for today. For the special session. So hi Tom. Hi Tom, how are you?
Pretty tired. It's 5:30 here. It's all right.
Oh, okay. It's very early for you, right? Yeah, it's very early in Europe. Sorry for the time difference. We have a huge time difference between Tokyo and Europe.
Yeah. I think it's just something you got to deal with and working from home with science.
So where are you now? Are you in London?
Today I'm actually based out of Munich.
Oh, okay. So we start like in about 10 minutes. Yeah, we start in 10 minutes. Here we have Michele, Joe. Hi, Joe.
Hi, how are you?
Good, how are you?
Not too bad, thanks.
So you're based in Singapore, right?
Yes.
And how's life in Singapore?
Not too bad at the moment.
So everything is back to normal?
I wouldn't say that.
No, not yet?
There's a bit of a bad COVID outbreak at the moment.
Oh, okay.
But things are starting to get a bit more back to normal.
Oh, okay. But Singapore actually has controlled it better than most countries, actually.
It had up until very recently, but it's
with the
just,
Delta variant, yeah.
Yeah, it's just kind of lost it at the end.
Yeah, actually the same for Vietnam, actually. It was doing very well, and then with the Delta variant, everything just kind of broke loose, actually. But now it's kind of like getting back on track. It's always nice and sunny in Singapore, so.
Yeah.
Every day is sunny. So Michele, how is life back in Switzerland? How's everything in Switzerland?
Well, I would say it seems to be normal since the end of the summer, but so winter has come. So I mean, it's coming. So let's see how it's going with the virus. But in general, I would say, apart from the very cold temperature, it's fine.
What is the temperature now today? What is
it's -1 or -2. Yeah.
Okay.
Yeah.
It's cold. No, it's very beautiful
yeah.
here, actually. It's like 20 degrees Celsius. It's very beautiful,
wow.
sunny outside. Yeah. Too bad you couldn't be here in person, because it's a very nice season to visit.
Yeah.
That's
a pity.
Season,
yeah.
The autumn season in Japan. It's very spectacular.
I mean, are you trying to torture the speakers indicating that here the weather is great and
Hi Franco, how are you?
Fine. Ciao Mattia, hello Michele and Joe and Tom.
Hello.
Hi.
And we can do the session in Italian because Ming Hakwan, he speaks Italian, so
No, but we have Tom. I don't know whether Tom speaks it. What Tom speaks
Italiano.
Non parlo italiano. If you wave your hands, I think people will follow you.
I often talk to Alexandra in Italian, actually, because she told me to keep on speaking, otherwise I will forget. Because I used to work in Italy, that's why I learned Italian. But I never worked in Italian, actually, because but you have to speak Italian outside. So I learned to speak Italian. But so now, you know, so she told me to keep on speaking it because otherwise, if you don't use it, you just lose it. But now I have to learn Japanese. Let me see. So we have a few more. Hi, Mattia.
I think Mattia is not here.
Mattia is there, yeah.
Can you hear us, Mattia?
I'm not quite sure whether he can hear us actually. Hi, Mattia.
Yeah, I can hear you. I can hear you.
Okay,
Hello.
okay.
Yes. Probably he's sleepy. No, what time is there now?
It's 5:30 p.m. No, for him it's even earlier. It's 4:30, I think.
Yeah, it's 4:30. Yes.
Because he's in the UK, so the UK is actually 1 hour behind.
4:30 a.m.
Yes.
AM.
Okay, so you're
Yes.
waking up a bit earlier than usual, I see.
Yeah, just slightly. Yeah.
So we actually have a lot of Italian speakers. We have Michele, we have Francesco, we have Mattia. So Tom speaks Italian. So. Joe, do you speak Italian?
I'm afraid not.
He can learn quickly, like unsupervised learning of Italian here.
So we have Mehdi and Denise, Alejandro. So it's actually it's an exciting session actually.
So we're waiting for Francesco Tacchino. Is he going to be part of the meeting?
Yeah. Maybe
yes.
Maybe we'll connect a little bit later because of the time schedule. But yeah.
Him reach up. And then also like Alejandro and Denise and Mehdi. I don't know how I have to pronounce his name. Mehdi Bozore. I don't know where he or she is based.
So Mehdi is based in Canada. So,
okay. Oh, this is like the vector, you know, something with the University of Toronto. Or...
Yeah, exactly.
Oh, okay. So for them, it's actually kind of midnight, I think.
Yeah, exactly.
So sorry for all of this time difference. So we actually had to calibrate kind of the time zone because there's no daylight saving here in Japan.
Yeah.
And so we actually we had to kind of recalibrate actually the schedule because we realized that there was a time change in Europe. It was like a week before the US and Canada. So there was some confusion. Because in Europe, actually, the clocks change on October 31st, but in the US, it's actually November 7th. So it's 1 week after. But lucky that I used to live both in the US and Europe, so I knew the difference. Yeah, it's 5:26 in Rome. 11:30, I think, on the East Coast of the US.
Good morning, everybody.
Good morning.
Good morning.
Good morning.
Hi, Alejandro. Hi. Good morning to you.
Good to see you again.
Good to see you again. Yes.
So we are waiting just for the first speaker. So that's fine.
Okay. That's Mehdi. Okay. Let me see. Also, the attendees are joining as well because actually we had a pretty short lunch break. So we have less than an hour for lunch break. It's actually a pretty intense program. Like the program is completely full.
Yeah, it's intense.
We have a lot of talks. They're all like very wonderful talks actually, but it's actually very intense.
Oh, hello, Mehdi.
Hi, good afternoon, actually.
Hi, Mehdi. Thanks for
joining. Good evening to you. Hello. Okay. So we're almost ready, actually. Okay, so I will monitor the chat on YouTube. If somebody actually asks the questions on the chat, I will relay to you.
So would you say something at the beginning, or should I, and then I share the screen?
Okay, I can say something now. Actually, welcome everyone, and we are very grateful that you are here, and thank you all for coming and for joining this exciting industry session. So Michele will chair the session, and we're looking forward to your presentations and a lot of questions from the audience. So thank you very much for joining us. I know that it's actually very difficult because of the time zone difference. So for many of you, it's actually either very late or very early in the morning. So thank you very much and welcome. Please, Michele, the floor is yours.
Yeah. Good morning, everyone. Can you hear me? Yes.
Yes, we hear you very well.
Yeah, thank you so much. So we can start. Welcome everyone. So good morning for those of you based in Europe, and good afternoon, good evening for the other people, the one that are. And thank you so much for inviting me to host this industry panel. I will start, of course, by sharing the screen. Let me just start the sharing. Okay. Okay, just 1 second. Okay. So I hear the record is in progress, so I think it's the right time to start, right?
Yes, perfect.
Okay. So again, good morning, everyone. Please let me just introduce the industry panel and this industry session for today. And thank you again for inviting us. And thank you very much for the speaker that will be part of this industry panel. So I put some pictures of you. Sorry for that. I took it from the web, but they are on your social and LinkedIn and so on. So let me introduce to you all of the speakers we have today. We have Mehdi Botsorey, Director of Business Development of Quantum Algorithm Institute. Then we have Tom Bryan, Research Scientist from Google Quantum AI. Joe Fitzsimons, Chief Executive Officer from Horizon Quantum. Francesco Tacchino, Research Staff Member from IBM. And then we have Mattia Fiorentini, the Head of Machine Learning and Quantum Algorithm from Cambridge Quantum Computing. Denise Raffner, Chief Business Officer at Atom Computing, and Alejandro Perdomo, the Associate Director of Quantum AI at Zapata Computer. So thank you very much. Please let me say something about myself. So I'm Michele Grossi. I am a fellow quantum researcher at CERN, in particular in the division of Quantum Technology Initiative. I will spend this first 10 initial minutes to introduce myself and to say something about what we are doing at CERN, and in particular, what this CERN Quantum Technology Initiative is about. So it's hard to say what we study and what we do at CERN, but I put some notes in this fancy blackboard. So there are a lot of topics that are covered. We have something related to quantum chromodynamics, and of course, a study of the standard model. And this includes study of collider physics, electroweak interaction, strong interaction, so on. But of course, we have also studied on beyond the standard model. So we want to check that the standard model is the right description of our universe. And there are a lot of open questions about that. Of course, we have string quantum field theory. We have some study of EV ion. So we have study of gluon plasma. And on the right side of the slide, we have, of course, topic of the lattice theory, which is very important for nuclear and particle physics, but not only at, let's say, a small scale, but we have also interesting study of cosmos astroparticle physics, which is very, very interesting. CERN is located in Geneva, in Switzerland, and a lot of the experiments that are part of the CERN environment are located along the Large Hadron Collider, which is this Hadron Collider where we have mainly 4 big experiments along the line where the proton and the proton collides, and we study the interaction of the particle. So this is how, let's say, the workflow of an experiment and on some research topic happens. So of course, we have the importance of the data. So we collect data from the experiment, and this can happen via collecting data from detector. We have some algorithm for reconstruction. And then we want to compare the data that we acquire with the data that we generate, the data that we simulated with our generators. And everything then fill into the data analysis process. So this is very a crucial step where we implement techniques of machine learning. And of course, I'm happy to say very recently also quantum machine learning techniques. CERN Quantum Technology Initiative is a quantum technology initiative that is organized according to this schema. So on the left side of the slide, you see 4 important ingredients. So we have the definition of the strategy for this technology initiative, of course, the definition of the coordination, so the level of the people that coordinate all of the project. In this way, we can define different research areas responsible for research areas and the people that are part of these areas. And then, of course, it's important to define the capacity and the community building. So it's a growing initiative. So we are looking for collaboration with other members and, of course, members of the CERN community and industry. We have collaboration between our management team with the other experimenter at CERN, but not only. And we have defined an advisory board that is composed of several people belonging to the different member states of the CERN community. We define 4 main research areas that are defined here in these 4 rectangles. So there are 4 pillars. The first one, and the one where I work, is quantum computing and algorithms. Then we have quantum theory and simulation, quantum sensing, metrology and materials, and quantum communication and network. So all of these 4 pillars are collaborating. We have different projects and some joint projects together. Of course, the last element of this structure is the way we interact with the academic and with the industry. Let me say that just very recently, we joined the IBM Quantum Network. That means that CERN is a CERN Quantum Hub. That means that we are able to access all of the hardware that IBM provided to premium member. This is a 3-year agreement, and we are building many experiments with this collaboration, and we are looking also for other industry or academic that want to collaborate this as. So this is an additional, let's say, tool that we provide to the people that belong to the CERN Quantum Technology Initiative. Please let me just summarize in these slides what are the main projects that are part of our R&D scenario. On the first part, we have the computing and algorithm part. So here we are trying to do many different things. In particular, we are trying to do simulation with quantum computer. Here, an example of quantum generative adversarial network with comparison with real data distribution. The important task of track reconstruction is done also with some quantum algorithm, quantum tensor network, and so on. And last but not least, of course, classification is a very important topic for high energy physics. So we want to discriminate between signal and background. And so here you can see some recent result about Higgs classification, but also we use this classification algorithm on different experimental scenario. Second topic is about sensing. So another topic related to quantum technology. We are working at low energy scale, but also at high energy scale. We are building detectors, and we are trying to exploit quantum effect within this kind of detector. And the third pillar is about communication. So here at CERN, we are working with the OpenQKD protocol, and we are building our internal network to create a cryptography channel to collaborate and to share the message. In particular, we're trying to implement within a project called Quantumacy, the cryptography of data that we analyze. So we are trying to understand how we can compress the information, how we can encrypt the information to create our first analysis workflow in an encrypted scenario. So QKD infrastructure, and of course, we are looking for quantum internet. Last but not least, theory, fundamental part of our research scenario. There is a team that is working on the theory, of course, for the standard model, beyond standard model, and they are trying to implement a quantum algorithm also from their side. And one of the most important topic is lattice QCD. So to summarize the main topics about the Quantum Technology Initiative at CERN, we have access quantum computing potential in high energy physics. So we want to develop and optimize algorithm target for realistic use case, of course. And this can be done looking for ideal quantum computers, so fault tolerant, but in particular, we are looking for NISQ configuration. We want to build expertise on the state-of-art software stack. This includes not only running on the hardware, but of course, running on simulator and doing optimization of classical computing resources for quantum computing. So the collaboration between classical and quantum computing scenario. Then we want to set up a distributed quantum computing simulation platform, of course, to provide access to the community that are working already on the analysis for different topics. And we did it with an initial investigation to set a baseline to prioritize and systemize some principal algorithms. So we started with quantum machine learning. We started with variational approach. We started to study the contribution of the noise to the simulation, and then the contribution of the error coming from running on the real hardware. And of course, we are not only interested in quantum algorithm for quantum machine learning, but in quantum computing in general. So that's an important topic. Of course, we are running not only on the IBM hardware, but we are testing different hardware and simulators. So photonic platform, ion trap platform, and so on. And that's a very interesting scenario and environment where students and researchers are actively involved. Let me conclude with just this final slide, because not only we are collaborating with the industry and the academic, but it's important education program that we set up with this Quantum Technology Initiative. So we did some lecture and seminars in the field. We have invited speaker. We created some training courses, and we have some colloquia with specialists and of course seminars. We would like to create and to do some hackathon in the near futures. And of course, we have an active program for students, which is a summer student program that has been extended since the last year to the Quantum Technology Initiative. So we are happy to construct also the education program within this organization. So with that, I would like to thank you very much. I will then stop sharing and I will give the word to Mehdi for his session. So thank you again.
Thank you very much, Michele. Let me share my screen and go full screen. Can you all see my screen?
Yes, thank you so much.
Awesome. So first, thank you so much for the opportunity given to me to talk about the Institute. So my name is Mehdi Bozore. I'm Business Development Director at the Quantum Algorithm Institute in British Columbia in Canada. So I'll talk about first who we are, what is our mission, and how do we plan to execute it, and actually what's the overall goal. So in terms of member organization, and these are the founding members, so we have players like IBM, Amazon, and Microsoft, for example, but we also have a pretty good representation of the local industry, quantum industry, from provider point of view with D-Wave and also 1QBit on the software side. The startup ecosystem is also well represented with Photonic. So not only we have industry players, and again, it's on the provider side, but we also have the main universities in British Columbia represented with University of Victoria, University of British Columbia, and Simon Fraser University. What makes us a bit unique from other not-for-profit organizations is that the founding member, like from a funding point of view, the government of British Columbia also has a seat at the board. And that makes actually my task a bit easier because then I can leverage the business development arm of the government to reach out to potential customers, for example. Now, in terms of mission, it's a bit, I would say, simple in the sense that the end goal is really all about economic development. The first idea is to leverage all the strengths that we have in British Columbia in order to establish an applied quantum computing ecosystem that is very inclusive from a core technology point of view, and also, includes large number of members. The focus then is all about building a critical mass of talent, again, to create skilled jobs, but also drive economic development. Now, if you take into account only the this education point of view, like how to actually quantum enable those grad students at the end of the day, that's just not enough because it doesn't take into account the ecosystem point of view. It's really good to have a wonderful workforce that you train in universities, but if at the end of the day, all of them cross the border south and start working for companies abroad, that's not a really good deal from a government point of view. So the idea, and actually the need, is really at the same time to give skills to grad students, the future workforce, but also to enable the local ecosystem so the industry can absorb this workforce. And it's not an easy task. It's this plan, let's put it this way, or putting all the pieces of the puzzle together, goes through three main axes. The first one is talent, and the objective is, again, to educate and grow a talent pipeline in BC. But what makes us a bit different is not only we're talking about academic programs, but there's also a big part that is related to collaboration with the industry. And that goes through like internships, for example, and internships that we partially sponsor. And we can also leverage federal programs, for example. The idea is really for the students, not only to learn the basics of quantum computing, but also to start applying their skills and enhance them in order to become like domain experts, not only in quantum information science, but also in dedicated verticals. The second piece of the puzzle, let's put it this way, is all about development. So not only we need to train those students, collaborate with the industry, but the academia also needs to get something back and gives us something at the same time. And this is all about supporting groundbreaking research via especially collaborations. So not only we have those founding members, but one key of our strategy is really collaborations and partnerships. with other entities like QAI, like not-for-profit organization. And I'm talking about mathematics-oriented organizations like PIMS in Western Canada, but also entities like other quantum institutes and AI institutes as well. And the goal is really to make sure that at the end of the day, we are able to solve major problems, not only in the private sector, but also from a public sector point of view. And then commercialization. So that's exactly where we do act like a startup, because it's nice to get funding from governments, but at the end of the day, we really want to be more independent. And independence comes through commercial productization first, and then commercialization. The idea here is, like any other startup, to build frameworks and products that will generate commercial value. So there's nothing better than trying to sell whatever you came up with in order to make sure that you are still valuable and you add value to the overall ecosystem. In terms of engagement model and projects, first we need to take into account the strategic industry verticals, so tagged as strategic by the government of British Columbia. And I mean, we're talking about the usual suspects here. Clean technologies, transportation, and logistics. So clean technologies, what we are really good at in British Columbia is, for example, the fuel cells technology with players like Ballard, for example. Transportation and logistics, we have really big port infrastructure and also airport infrastructure. So it's that's why it's strategic. And of course, we're talking about things like quantum chemistry, healthcare, and emergency management. So what it means for a vertical to be tagged as strategic, it means that any project that will add value to these verticals and industry players within these verticals, basically we will go the extra mile and help a bit more, let's put it this way, those industry players and also startups delivering value for their customers in these verticals. In terms of, let's call it an offering, it's all about quantum integration as a service. And actually, at the end of the day, we do have the same concept of quantum journey that other startups do have. And everything starts with use case identification. So that's the first part of our offering. It's we did break it into pieces, so they are more ingestible by industry. And also the big thing that we can offer to our industry partners is actually de-risk their investment in quantum technologies. So instead of talking about massive engagement that will span or like 3 years, for example, or just 1 year, then let's start small and make sure that at the end of the day, from the industry partner point of view, the investment is light enough. So, for example, we can bypass the any type of procurement process, but it's also not that risky for them to explore quantum technologies. So, of course, we do assist in building and scoping program statements. We do partner in developing research proposal, co-fund projects. One key thing, and actually lots of requests that we got from our industry partners, is making sure that there's a skills transfer, because this initial engagement, not only they will get a very good idea of what of their business cases can benefit from quantum computing technologies, but there's also the skill transfer that at the end of the day enables them to quantum technologies. So we do have things going on already. For example, we had our first call for proposal in end of August. That will, the deadline is January 31st, 2022. And again, for specific verticals, we do partner with MyTax, which is a federal program. And we go the extra mile in the sense that we top up the MyTax funding by our own funding. Then, of course, we are always looking for talents on the operations side, but also on the research side. And our partners are also looking for talent. And I'm talking especially about MyTax, who they are looking for business development specialists, because not only research talent attached to research is not that easy to find, but on the business development side, it's also not easy to find people who can handle those emerging technologies. So that would be it for me. Thank you very much again for the opportunity given to me to present the Institute. And I'll give it back to you, Michele.
Thank you, Mehdi, so much. Very interesting talk, and thank you for keeping the time. So I would like to invite our second speaker here. We have Tom Bryan from Google. Tom, are you with us? I would leave you the stage and to share the screen. Thank you again.
Let me see if this works.
Yeah, we see your screen. Tom, I think you're on mute.
This is odd. It's saying I'm sharing audio. I don't understand.
Okay.
Wait up.
So we were able to see your
this.
screen, but yeah, it's fine.
Yeah, you're able to see my screen, but then I became muted. Let me see what I can do here. Hang on, why don't I try this? Okay, and now if I try to share a Chrome, like I try to share that instead. Maybe this will. Is that okay? Can you see me and you can hear me?
Yeah.
All right, cool. I apologize. Maybe I'll just boost this up. Okay, cool. So I wanted to give you. I wanted to give you a brief overview of quantum computing at Google, and then so use the last 5 minutes of the of my introduction to just give a recent result of relevance to QML. Here's the team at Google. This is actually a photo that's taken pre-pandemic, so the team's grown a little bit since then. And here's where we're based. We like to think about, most of us are in California, but we have a small presence in Europe. We're expanding quickly. We like to think about our team distributed over like the entire quantum computing stack. We have applications research in Munich. We have some people we have a lot of theory work based out of Los Angeles. And then the majority of our quantum efforts are based in Santa Barbara, where the magic happens. Here's just a quick overview of our current quantum campus on Santa Barbara. We've expanded a little bit during the pandemic, as well as having the original GQ1 office. We also have our GQ2 office, which is the quantum data center, where we actually put our chips in the fridge these days. We have a new fabrication and faculty in GQ3. Here's a shot of GQ2, just to flash that really quickly. It's this building's been decorated out. It's been built over, like, kind of finished up during 2020 during the pandemic, which is kind of unfortunate. It didn't get like the proper opening it deserves. I'd really recommend a visit. It's got it's been decorated in true Google quantum style, and it's got a lot of the history of our journey over the last 10 years in the building. And I guess so. That's the briefest of brief introductions to the team. But now I just really want to focus a little bit on a hardware roadmap. So the plan that Google has for the next 10 years is to build out a large scale fault-tolerant quantum computer. Here's our quantum roadmap. It was introduced last year. You can see 6 milestones, the first of which was our Beyond Classical experiment in 2019. And we're currently working hard towards milestone 2. And the idea is milestone 2 is a demonstration of an unambiguous demonstration of quantum error correction below the fault-tolerant threshold. The plan over the next 10 years is to scale up then from a small demonstration of quantum error correction to a long-lived logical qubit with almost near infinite lifetime. Then to push that to a tolerable module, logical gate. And as soon as we hit that point, we think that the physics is being de-risked. This just becomes an engineering problem of how to repeat this thing a couple of hundred times to go from a module which is about 10 to the 4 qubits to something which looks like a full million qubit error-corrected quantum computer. Now, while we've been separate from the fault-tolerant push, we've also spent a lot of time over the last years running experiments on the beyond classical boundary. The dream of the last 2 and say the next 5 years is to find a useful beyond classical NISQ application. And we've approached this from 2 sides. We've probed fundamental physics. So the first side we've probed fundamental physics looking at digital quantum simulation. So here's some recent results that have been up on the archive and been accepted in various journals. And I would just want to point out that we're at the boundary of beyond classical for some of these. In particular, our OTOC experiment, if we just improved our coherence times by about a factor of 4, then this would already be a beyond classical, practical, or a beyond classical, physics experiment. But these experiments are far from industrial application at the beyond classical level. On the other hand, separately to our large-scale physics projects, we've also spent a lot of time targeting experiments in quantum chemistry. We've also spent a lot of time targeting experiments in quantum chemistry, which is still probably the most promising quantum computing application. We made significant progress there. We've pushed VQEs to around about 10 to 15 qubits. We've pushed QMC-assisted quantum computation close to about 20 qubits. We've pushed Hubbard model simulations to around about 15. All of these methods are in principle relevant to chemistry, which makes them highly industrially applicable. But to scale these experiments by about a factor 5 to 10 seems incredibly difficult. The number of measurements and the fidelity requirements scale quite badly. So I'm going to spend the last 4.5 minutes talking a little bit about, flashing some slides about some recent work that we think kind of like bridges the two fields and might be of interest to the QML field. The archive link is below, and the idea basically behind this research is to learn a Hamiltonian from experimental data by using a quantum device to simulate that data. Now, the example Hamiltonian we chose, or example experiments that we chose, were NMR experiments. The idea of an NMR experiment is pretty simple. You start with some initial state rho, which is usually like, you've got a bunch of spins, they're left at thermal equilibrium. They look like basically, some small spin inversion, or like some small spin population where you've got more qubits in the ground state than the first excited state. Then you evolve this under some external pulse sequence, which is usually like, targeting a bunch of magnetic field pulses and letting the signal also like relax under an external magnetic field. And then you measure some observable to get a signal. And the end thing is, you get a signal function, which looks like this form here, Sx of t, and this is generated by, sorry, I should say here. So the Hamiltonian you're trying to learn is this H, which I'm writing out as the sum of large matrices, Vn, and numbers, which I assume I don't know. And then this Hamiltonian generates time evolution when I add in a pulse Hamiltonian, which I assume I do know. And this time evolution is used to generate a signal. There's the math of it. And then from this, the idea of this paper is to learn the Hamiltonian given access to this experimental data, right? So now I throw away the Hamiltonian. I give you the set of data from this unknown Hamiltonian. I ask you to infer the constant terms, the HNs, which I had on the previous slide. Now, in order to do this, and for the sake of the paper and to make things relatively simple to write down, we assume the initial states, measurement operators, and the time-dependent control are all known to very high precision. All of these could in principle be relaxed. I don't think that the Hamiltonian learning field is relatively well understood, and we know how to put uncertainty into our initial states in, for example. But the rough way we took the way we took on to do this is that we took on the idea of learning this by minimizing a cost function, which is just the difference between the signal that I simulated on, say, a quantum device, right? And so there are kind of two quantum devices here. So to be particular, the SX without the tilde is the SX that I've generated from an NMR experiment. The S tilde X is something that I've, say, simulated on one of our superconducting quantum computers. Right. And the idea is I want to get the S tilde X as close as I can to the SX by tuning the HN terms in my experiment. No, sorry, in my simulation rather. And this gives me a very simple cost function I can write down, which is the log likelihood of the probability that this Hamiltonian generated this data. And I can and one of the big parts in this work was we put down quantum circuits in NISQ and fault tolerant frameworks to estimate the gradients and Hessians of this cost function. The key point I want to make with this slide is that this is our current protocol for Hamiltonian learning. There's no reason why it couldn't be done better with machine learning or quantum machine learning processes. And I think I want to put this out as a challenge to the QML community to improve our methods for doing Hamiltonian learning on experimental data, because it looks like a reasonably interesting field to jump into. And there's I guess, the thing, and I want to point out here that there is a region in which we think that will be quantum feasible, right? Where we think that there is actually like a gain to be had from the quantum device. You need to circumvent two issues. So the first issue you need to circumvent is you need to have some signal in the region. And the second issue you need to have, at least for the problem for the quantum device, is that you need to make sure that this is an experiment which is not classically feasible. We actually, and I think that one of the main results in our paper was to demonstrate a link between basically this transition as you go from classically feasible through to quantum feasible through to a completely degenerate solution space, and the onset of wave function fractality in quantum many-body physics, which is, it's kind of cool to see something come out between like a link emerge between learnability and you know, it's a very, very complicated concept in many-body physics, but that we thought was kind of cool. So there's a take-home from to try to inspire people to look more into Hamiltonian learning, applying Hamiltonian learning to learning other experiments using a quantum computer as part of your learning tools. And I will say that the methods that we demonstrated work for any time resolved quantum experimental data. We're looking to shift this also into like the Fourier realm. So, you know, to look at energy resolved quantum experimental data. And I want to point out as well that for one of the reasons why we're interested in this is because for local spin like Hamiltonians, it's relatively nisky. So I'm out of time now, but I'm just going to flash the slide. Our team's growing. Here's the link to our careers page. And if anybody is interested in careers at Google, then also please feel free to drop me a link. Thanks for the time.
Thanks a lot, Tom. Very interesting seeing how this QML is very as the intersection with many other fields. So thanks again. We will discuss maybe some details in the roundtable session. So please let me invite our third guest, so Joe from Horizon Quantum, and want to thank you again for joining the session, and I will leave the stage to you.
Thanks very much. Are you able to see my slides?
Yes, perfectly.
Okay, perfect. So actually, I'm delighted to have the chance to speak at QTML, because actually what has led to our company was initially an effort in my former research group to start trying to automate some of the techniques that are used to generate quantum machine learning algorithms. And since then, we've gone quite far beyond that. We've been looking at techniques to automatically generate quantum algorithms and compile these down into, you know, essentially down to the pulse level to signals you can send to processors. But I want to give you an overview of what we're doing and then show you a concrete example of what this actually looks like. So I think we probably all know that developing for quantum computers is hard in many respects. One of them is just that quantum mechanics is not very intuitive. So there are not very many quantum algorithms techniques that are known. Yes, there's a lot of work on variational techniques at the moment, but if you look at the more structured algorithms like Shor's algorithm and so on, there's only a handful of techniques that are known. You know, maybe 6, 7 techniques in total. You know, amplitude amplification, period finding, different things like this. And you could ask, why isn't there more? And one of the reasons I think that this is the case is because we just don't have a very good intuition for achieving things through interference between computational branches. Because, you know, the way a conventional computer works is very like the way you work with a pen and paper. But quantum computing is something different. We never try to explore calculations with a pen and paper in superposition and then try to, you know, get interference between the different results. You know, other problems that you currently have, even if you've got a good quantum algorithm, the hardware is diverse and imperfect at the moment. And that makes it difficult to write programs that work across a large range of hardware, or at least that work consistently, because, you know, a lot of the time the performance of the hardware changes depending on, you know, various conditions, the calibration drifts over time and so on. And then, you know, the other side of this is that the programming languages are also at a very primitive stage at the moment. So, you know, quantum hardware, it really is kind of like 1940s or something for us, but that's also true for our programming languages. At the moment, although we have these frameworks that you can program in Python and so on, a lot of them are really appending very low level operations to create a circuit gate by gate or something like that. What we're trying to do is get away from this. We're trying to get to a point where you don't need to think about the underlying computational model, where you can abstract away the quantum computing so that you can write code in a conventional programming language in Python or MATLAB, something like this, and automatically compile it to run on quantum hardware. Not just creating reversible circuits, but actually constructing a quantum algorithm that does what your code does, but does it in a different, more efficient way that exploits interference in the quantum hardware. And if we can do this, this is a pretty powerful tool, because if you ask, why aren't there quantum algorithms for computational fluid dynamics, for computational geophysics, for all of these other areas? I know there's been 1 or 2 papers on computational fluid dynamics, but for most of these, if you ask why there aren't algorithms, well, usually it depends on some specific domain. The problems themselves are fairly suitable for quantum computing, linear differential equations or whatever. But there's not really many people who are both experts in turbulent fluid flow and in quantum algorithms, or in the kind of inverse problems you have in computational geophysics and quantum algorithms. So if we can automate the quantum algorithm construction, then we can put these tools in the hands of domain experts to see what kinds of problems they can really apply quantum computing to. Of course, the hardware needs to get there still, and that's definitely not something I want to gloss over. But there is this software problem too. How do we make these devices really useful to users in other areas, users that are not quantum algorithms people? Okay, what we're basically building is essentially an abstraction layer so that we sit between the user and the hardware, so that we're taking in a program that's written essentially for a classical program, so written to run on a conventional computer, compiling that into something that can run on quantum hardware, deploying it to quantum hardware, and then presenting the results back to the user. Our tool chain looks like this. There's basically 3 different parts to it. The first is about algorithms construction. So how do you go from classical code to something that can run to a quantum algorithm? And for that, we need to tackle a couple of different things. So what causes code to be slow? There's a few different things, but usually you can reduce it to either the use of loops, the use of recursive function calls, or the use of operations that have, are maybe 1 line of code, but have a high implicit cost. So when turned into machine instructions, they are very many instructions, like when you multiply matrices in MATLAB. So we try to tackle these in different ways, breaking apart loops. We try to break them down into simpler and simpler parts and then classify each of these loops, say, what's it doing? And then see, can we replace it with a more efficient procedure that does the same thing, but in a better way? So we do the same kind of thing with recursive function calls. And then for operations that have high implicit cost, to get around that, it's really about thinking, are there better ways of representing this data that give you better trade-offs? Are there better data structures? Are there better quantum algorithms for manipulating those data structures? And once you do these substitutions, get your quantum algorithm out, and then you need to compile it down to something. It's something you can send to hardware. That means turning it into a concrete circuit, converting to whatever the instruction set is for your hardware, mapping to the physical constraints of the hardware, which qubits can talk to which, how good are those couplings, etc. And then understanding the noise, the imperfections in the hardware. So a lot of the time you have crosstalk and different things like this that can be mitigated if you have a good understanding of what's actually happening in the processor. So like a 2 local Hamiltonian description for the processor and its interactions with the environment, for example. And then we need to present that to the user. So what does it mean to deploy a quantum application? For us, that means taking the program, wrapping it up, and deploying it as an API. So there is somewhere in the cloud for a user to send input to and to get input back from once they've compiled and deployed their program. For us, we're not solely and exclusively focusing on people that are non-experts in quantum computing. Actually, you can jump into this tool chain at any level. We've got 4 different programming languages at different levels of abstraction, with some being, gate level, and then kind of gate level with basic like flow control. And we've been working on something more recently that you can think of as like a kind of quantum C++, where there's some support for object-oriented programming with natively quantum data structures. So I wanted to finish by showing you what this algorithm construction actually looks like, because it's one thing to say it, it's another thing to actually see it in action. So let me show you this bit of MATLAB code. What this MATLAB code does is it's basically an adaptive search. So it's a global optimization routine. It takes in a function handle f, and what it does is it tries to divide the input to f up into a grid and search over that grid. So it searches which point is the minimum one, and then it expands a grid around that minimum and searches over that to find the minimum, and so on, recursively. So you can copy and paste this into MATLAB now and run it, and it will run. So what does the procedure look like? So the first thing that happens is that we try to eliminate variables that are introduced in the middle of the function body. So in this case, lattice points is defined in terms of inputs. And so that gets substituted in first of all. Then any operations that don't affect the output get removed. Then the inner loop, so you can see there's a number of for loops here that are nested. The inner loop gets split apart into separate smaller loops. Again, we remove operations that are not affecting the output. Then we remove the redundant flow control. And then we're left with one loop. And at this point, the loop can be classified and replaced with something else. Because I guess you can see in this case, what that loop is doing, it's just defining the elements of a vector D. So we replace that with a special function. We also have this extra bit of code that has to come in order to deal with the side effects. So the fact that if the loop index if dim had been 0, it's like a special case. So we need to add in some little some code to deal with the side effect there on D. Again, we eliminate assignments that aren't affecting the output, eliminate the redundant flow control, and then we make operations independent so that the loop can be simplified. So in this case, x is going to get replaced so that we can simplify this outer loop. So at this point, we can split the outer loop to parts. So you see it gets split into 2. We can replace the loops. The first loop, in this case, you can see it's a special kind of loop in which each time through the loop, every assignment gets overwritten. So only the last time through that loop matters. So it's like a special case that we can recognize. And so we can replace that. And again, we do the same thing of removing operations that don't affect the output. And now the final loop we're left with, again, we match it and we're replacing it, in this case, with a special function. And I guess you can see what happens in this loop. It only has an effect when the if is triggered, when the condition in the if is triggered. So it turns out we can use an amplitude amplification-based algorithm to accelerate that. So it turns out it's actually kind of a general case of minimization or maximization. And once we've done that, there's a little bit of cleanup we have to do, removing, again, operations that don't affect the output. And finally, we're in a place where we can replace these special functions that we've introduced with quantum algorithms to achieve precisely what those building blocks of the algorithm do. So the bits highlighted in green now are replaced with quantum procedures. And when you do this, it turns out that you get a square root speed up on the algorithm. The algorithm overall, it has an exponential runtime, so it's actually an exponential saving. But I just wanted to show you that as a kind of concrete instantiation of what it means to automatically create a quantum algorithm. So thanks very much for taking the time to listen. You can, if you're interested in joining us, you can reach out to us at hello@horizonquantum.com or careers@horizonquantum.com, or if you want to learn more, you can see the website. Thanks very much.
Thanks again, Joe. And this demo was really interesting, and I will have a lot of questions maybe for the roundtable, but also because I mean, this give you the taste of what can be done by, let's say, replacing some code and putting some instructions. So very, very interesting. So just for your awareness, we are receiving some questions for students. So for those of the speaker, there are some students that are very excited about seeing this session, and maybe we will ask some questions at the end in terms of internship and summer student program and so on. So be prepared for that. Let me introduce to our next speaker. So Francesco from IBM, it's a pleasure to have you here, and I will leave you the stage. And thanks for the speaker to keep the time.
Yes, hello. Let me share the screen. Okay, so you should see my slides now.
Yes, perfect.
Okay, cool. So thanks a lot, Michele, and to the organizers for having me here today. My name is Francesco Tacchino, and I'm a quantum applications researcher at IBM Quantum in Zurich. And in this brief talk, I will outline some of the latest developments in IBM Quantum, and of course, with some specific focus on quantum machine learning. Now, let me start with an updated overview of our development roadmap. And as you probably know, this was released back in February and represents a rather detailed plan across multiple levels, targeting the realization of a frictionless cloud quantum computing infrastructure. Now, as you see, we go from some goals in terms of hardware, which lie at the bottom and represent the foundation of the whole scheme. And on top of this, there are several layers which are being built from kernel to more advanced and application-specific functionalities. Now, as an highlight for this year, in May, IBM launched Qiskit Runtime, and I will say a bit more on this in the following. And with this, we obtained 120 times improvements in execution speed. Now, Qiskit Runtime was a first attempt towards solving a new set of tough challenges related to quantum computing performance. And this theme, performance, is what I would like to discuss in some detail in the first part of my presentation. Now, before moving forward, let me also remark another very important novelty, which is the recent refactoring of the Qiskit application modules. This now includes some dedicated libraries and specific integrations in 4 major areas, namely optimization, natural science, finance, and of course, machine learning. Now, the mission we are all trying to accomplish, and essentially the reason why we have in a conference like QTML an industry-focused panel discussion, is that we want to bring quantum computing out of the lab and turn it into a business-relevant solution. Now, in order to reach this goal, what we need to do now is to be able to assess the performances of our system in a complete and fair way. And we have to keep in mind that now we can no longer just naively think in terms of just the number of qubits that we have, or even just their individual quality. What we have to do in reality is look at the useful work that those qubits can do. And this is what we would like to call performance. Now, defining and measuring performance is not at all a trivial challenge always, but this is particularly true in quantum computing technology because we span many different categories, design choices, hardware and software architectures, and so on. So at IBM overall, we think that performance for a quantum processing unit can be measured by 3 key metrics, and these 3 key metrics all need to keep improving together all the time. So the first one is scale, which of course essentially represents the number of qubits you have in your system. And this critically determines, for example, the size of the problems that you can compute. The second one is quality, which is a measure of how good your technology is at implementing your quantum solutions. And this takes, of course, into account, for example, the impact of external noise or hardware errors. And this is the one that can be measured by the quantum volume, which is a benchmark that IBM introduced few years ago and is keeping to constantly improve on its platforms. And I'm happy to say that now quantum volume is also a widely adopted benchmark across the whole quantum industry. And finally, we have speed. And this is a measure of how fast your system can solve a problem. And this can be measured by so-called QPU speed, which is essentially a detailed measure of how many primitive circuits you can execute per unit of time, in a way which is essentially similar to flops in classical computing, so the number of floating point operations per second. Now, improving QPU speed is key for a practical quantum computing, because only if you have a reasonable speed, you will be able to incorporate quantum computing as a practical, relevant part of a workflow in industry, for example. Of course, here is where, among many other key components, the Qiskit runtime naturally enters, for example, towards the strategy of reducing latencies and to improve speed. More specifically, Qiskit runtime does this by enabling an efficient interaction with the cloud through the Qiskit runtime API. So, as you know, in the current era of noisy quantum hardware, some of the most promising and even popular applications require usually many iterations and averaging of circuits. And this load comes from many sources, say from variational algorithms themselves, but also from error mitigation techniques, and may also be the result of some real-time interaction between quantum and classical computing. And this is what could be the case, for example, with dynamical circuits that IBM is planning to release next year. To implement this in an effective way, we must have an effective cloud infrastructure, which gives you a portable and customizable platform for the users, while at the same time reducing the latencies and optimizing the queuing times. And here is where the Qiskit runtime comes into play. So this framework provides users with a dedicated execution environment, and using new software architectures and OpenShift operators, it maximizes the time that you can spend doing the actual computing and minimizing everything else. For example, the time that you spend waiting in the queues. Now, if you're interested in learning more about QPU performance and IBM's approach to this subject, I encourage you to have a look at these resources, including a recent white paper on the archive, an IBM research blog, and a YouTube video from Jay Gambetta. Okay, let me now shift gears. And in the second part of my presentation, I'd like to focus a little bit more on quantum machine learning and activities related to quantum machine learning at IBM. So researchers and research groups at IBM have been focusing recently on both fundamental questions concerning quantum machine learning methods and some more specific applications across different areas. Speaking of fundamental results and development of new algorithms, let me mention two major classes of results. One is about quantum kernel methods, where we presented this year two major follow-ups to the seminal work on quantum support vector machines, which appeared in Nature in 2019. These two follow-ups are first a demonstration, a first rigorous proof by Liu and collaborators of a quantum speedup in supervised learning based on the hardness of the discrete logarithm problem. And second, the quantum kernel alignment, which was proposed for data with group structures and implemented on real processors by Jennifer Glick and collaborators. Now, here in this second case, the iterative component of the method naturally used the features introduced by the Qiskit runtime framework. Regarding the other class, so quantum neural networks, a team from IBM Research Zurich and with some collaborators and Amir Abbas as first author recently proposed a measure of the power of quantum neural networks through effective dimension. And in particular, they proved that they showed that quantum neural networks can have a higher effective dimension compared to classical counterparts, and that this in turn implies that quantum neural networks can train to lower losses faster. Regarding some more application-oriented results, let me mention the very interesting collaboration with the CERN Open Lab, where quantum support vector machines were employed to analyze collision data coming from the Higgs boson search at the Large Hadron Collider. Now, this is particularly interesting because it represents an important example of how quantum computing technologies can empower other possibly seemingly distant areas of science, including, like in this case, some of the most important experiments in fundamental physics. Other possible examples, this is only a very limited selection, include, for example, the design and realization of quantum Boltzmann machines, which can be employed, say, in fraud detection on credit card transaction data, and quantum implementation of feed-forward neural network architectures for some proof of principle pattern and image recognition tasks. Now, all the expertise collected by IBM researchers and the quantum machine learning community at large is now being translated by the Qiskit development team and used, funneled into a dedicated quantum machine learning module, which is part of the new Qiskit application stack that I described, that I mentioned at the beginning. Now, this machine learning module, of course, leverages the basic structure and functionalities of Qiskit, like the manipulation and the execution of quantum circuits on different backends. And on top of this, it introduces some of the most important building blocks that in particular pertain to the two major categories of quantum machine learning as we know it today. So quantum neural networks on one side and quantum kernel methods on the other. So all these functional building blocks, of course, come in very handy to build and train quantum machine learning models, while on the user side, you can keep full control on their properties. All these fundamental computational units can also be, of course, easily reused in different contexts, including regression and classification. On top of this, Qiskit machine learning also contains a torch connector, which allows integration of all these modules and specifically neural networks into PyTorch workflows. Now, once again, and here we get back again to the idea of speed as a key figure of merit, we plan to integrate this with runtime to improve the performances in the training of hybrid models where they have PyTorch and Qiskit machine learning components. Now, to conclude, I leave you with the link to the documentation if you want, if you like to learn more about Qiskit machine learning, and I thank you all very much for your attention.
Thank you again, Francesco, and thanks a lot for keeping the time. All the speakers were very on time, so thanks a lot for this. So we can have some space at the end for the roundtable, and thank you for introducing us to some very interesting topics about the clocks and the speed and the performance of the hardware together with the framework of machine learning. So thanks again. Now it's time for Mattia Fiorentini. So thank you, Mattia, for joining the conference, and I will leave you the stage.
Great, thank you, Michele, for having me, and thank you everyone for being here with us. Let me just share my screen now. Okay. All right. Okay. Zoom is being a little bit temperamental, not surprisingly.
Yes.
Okay, apologies for that. I think I'm back. Let me try to just share the screen again. Okay, seems now that hopefully is working better.
Yeah, it's always classical computer fault.
Exactly. All right. So thank you for the for having me. I am Mattia Fiorentini. I am the head of the machine learning and quantum algorithm division at Cambridge Quantum, and I'm delighted to be here to basically tell you more about what we're doing at Cambridge Quantum when it comes to quantum machine learning. So about the company itself, Cambridge Quantum is a leading independent quantum software and quantum cybersecurity solution provider. As of today, it operates globally with offices in Europe, in the US, and in Japan, with more than 165 employees. Most of us are scientists in research and development position, and most of us have PhDs. You may have heard in the news that this summer Cambridge Quantum announced the merger with Honeywell's Quantum Solution, which is a builder of quantum hardware. And this, after the merger, this will lead to the creation to the largest, let's say, vertically integrated pure play quantum computing company in the world that covers the whole spectrum from, again, building hardware to having a compiler and quantum software development kit to algorithms, and then almost out-of-the-box application for relevant industrial domain. So Cambridge Quantum has a few main areas of activity: quantum chemistry, cybersecurity, quantum natural language processing, and machine learning and quantum algorithm. They are all built on top of Ticket, which is our quantum software development kit, which also has a very advanced and high performance compiling capability, which make all our algorithm and software application portable to all the main device available today and compilers. We also benefit from strong interaction with hardware provider, IBM, Honeywell, which are also both have stakes in the company. But again, all the others are supported, Rigetti, Amazon Bracket, so on and so forth. So in this talk, I will focus on, again, machine learning and quantum algorithm, which is the branch of the company that looks at making the most of near-term hardware and looking at general purpose application of quantum computation. So that's the team and the unit I lead. So my team is structured around this vision. So we're science-led in the sense that we aim at advance the fundamental understanding about quantum computing, about sources of quantum advantage. And the way we do so is that we published peer-reviewed research, as also many other companies and many other people who are representing their companies here on this panel. And we believe that this is a good way to sharing our knowledge and to really openly contributing to this field. But we are also application focused in the sense that we want to connect with communities that are close to us and that we believe are our stakeholder or a stakeholder of quantum technology and of quantum computation. So we can think of course, about scientists, condensed matter physicists, quantum chemists, and so on and so forth, and other academics. But also we want to help practitioners to solve their practical problem when it comes to machine learning, optimization, and simulation, and also advise and inspire business leaders on how to include quantum computing in their business to stay leaders in their field. Lastly, we aim at being impactful, which basically means making the most of the hardware we have today and really try to push the current hardware to its limits by developing better and more apt algorithm that can really leverage the strength and circumvent its limit. We do so also by being hardware agnostic, thanks to Ticket. Our this vision is built around, let's say, I think the common understanding of what are the quantum computing timelines and the technology that is available today. So today, clearly, we have strong high-performance computing capability. I'm thinking particularly about what cloud computing and things like GPUs have brought to us in terms of all the advances, and that this hardware enabled by simply finally being able to support algorithms such as deep learning algorithm and so on and so forth. And on the quantum side, we have what is called noisy intermediate scale quantum hardware. So hardware that, let's say, can demonstrate all the fundamental capabilities of manipulating quantum information, but it's limited in scale and has some, has some noise in it. And in a way, let's say, it looks a little bit still like sort of a form of analog computing rather than digital because of this error accumulation and so on and so forth. So this is what we have today. What we will have in the future, and it's confirmed also in this panel by the timeline that we saw from some of the other presenter, is that we will get perhaps in a decade to fault-tolerant quantum hardware, but you're not quite there yet. So the path that many have adopted is just the one of leveraging the strength of both high-performance computing and NISQ quantum computation in what they are called hybrid quantum algorithm, variational, and which, as of today, form the basis of the basic work tools for quantum machine learning. So I'm sure many of you that are listening now, they are familiar with the hybrid workflow. But let me just briefly remind everyone about the key component. So let's say, I think a strong approach for today's quantum machine learning is this hybrid quantum classical approach by this type of algorithm, where we have basically a quantum processing unit, which embeds a parameterized quantum circuit. Parameterized quantum circuit is built of a single qubit gate that usually have some pre-parameters, so the angle of rotation, and then 2 qubit gates that allow for entanglement and for exploring the really interesting part of the Hilbert space. So what a parameterized quantum circuit does basically give us the freedom to prepare state that then will result in highly complex and non-trivial probability distribution over our bit stream, over our, let's say, qubit measurements. The other, and again, quantum computer and PQC in particular are particularly good as state preparation. That's their strong feature. Another thing that our current device offers is that they can sample from this PQC, of course, very, very naturally. So one could say that really what's interesting with this computation is this ability of preparing states and then sampling from them. So once we have prepared a state and then collect some sample, we let's say send the sample to our classical computer. The classical computer will do mainly 2 things. Using this quantum sample to evaluate an objective function, and then use an optimizer, an optimization algorithm to minimize the objective by tuning the free parameter of the parameterized quantum circuit. And this is how the loop is closed. So our updated parameter go back into the quantum computer, we prepare a new state, and we draw a sample. By just stopping at doing this, and we know that we can achieve this is a very robust computational paradigm, but most importantly, it's a universal computational paradigm. It's very popular in machine learning, and from a classical perspective, it looks a lot like training a neural network. But we can do all sorts of things and solve all sorts of mathematical problems with this sort of algorithm that are not traditionally in the domain of quantum machine learning, or let's say simply machine learning. To finish off on machine learning, what often is done is that in supervised learning, some of the free parameter of our PQC are allocated for input data. So this parameter will be not touched by our optimizer, but we use for input data. And then both for supervised and unsupervised learning, often sample data from our empirical distribution are collected and then used by the classical computer to evaluate objectives. So as I said, apart from the key feature that this is a universal way of doing quantum computation, I mentioned robustness and flexibility. So let's start with flexibility. Flexibility is achieved by crafting suitable objective functions. So if we are solving classical computer problem, we can change our objective, root mean square error, categorical cross entropy, and so on and so forth. For generative modeling, we can use F5 divergences. For optimization problem, we can use this Kubo, Hamilton, these Kubo forms, or even Hamiltonian, just to simulate the evolution of quantum system. Robustness is given by our PQC ansatses, where we can have outdoor efficient ansatses to circumvent the problem of, for example, limited connectivity. We can use IQP or even random circuit to show quantum supremacy, or use other ansatses such as MIRA and quantum convolutional neural network. They're particularly promising for scaling to large number of qubits. Lastly, let me finish off by mentioning briefly how at Cambridge Quantum we are applying this type of algorithm to solve, to do science and to solve scientific problem and to work with clients. So we work in particular in the machine learning and quantum algorithm unit across the three main technical verticals, which are machine learning, optimization, and simulation. In each of these fields, we first do research, and then we use our results and our branded algorithm and implementation, which in some cases are state of the art, to develop collaboration. So in machine learning, we're particularly focused on generative modeling and inference because of this fact that these devices are very good sampler and very good at preparing states. We published again a couple of works. Probably most notable are parameterized quantum circuit machine learning model, and our work on demonstrating variational inference with a quantum computer for the first time. And we work with this with Crown Bioscience, which is a bioscience company for discovering biomarker for cancer treatment, and AKBP for phase flow classification. In optimization, we focused on combinatorial optimization. We developed the filtering variational quantum eigensolver, which is a state-of-the-art algorithm for combinatorial optimization on quantum computing. And then we applied this in a case study for the job shop scheduling problem. And we were able to solve straight out of the box a 23 qubit problem without any hardware optimization on superconducting hardware with the filtering variational quantum eigensolver. And lastly, we work on simulation, maybe partial differential equation in Monte Carlo. We developed in collaboration with Oxford University nonlinear PDE solver that have potential of quantum advantage. We recently developed in September a NISQ version of variational quantum amplitude estimation that retains a low polynomial speedup, and then particularly frugal algorithm for time evolution and for studying quantum system. And we're working on this with the German Aerospace Center for Battery Research. So this concludes my presentation, and I'm looking forward to discussing with you all. Thank you.
Thanks a lot, Mattia. Thanks a lot. I would like to introduce the next speaker, Denise. Thank you for joining. I will ask both of the two speakers to keep the time as the other speakers so that we have time to discuss in the end. So welcome, Denise, and the stage is yours.
Thanks, Michele. It's nice to see you. Can you hear me?
Yes, very well. And we can see your slide as well.
And you can see my slides. Okay. Well, thank you, everybody. It's 5 in the morning in London, and I'm happy to join you. a little bit of a change of pace. I recently changed jobs last week, and I now work for Atom Computing, which is a company, a neutral atom company that is just emerging from stealth. So I wanted to take a couple minutes with you all and introduce you to this new and emerging technology that we feel is very promising in the world of quantum computing. So Atom Computing started in 2018. We've raised a Series A round. We are in the process of closing a B round. We have some really great investors, including Eric Schmidt's company, Innovation Endeavors, Venrock, and Prelude. And we're very lucky that we have a very experienced CEO, Rob Hayes, who has a lot of operational experience. He was VP and Chief Strategy Officer at Lenovo. And then prior to that, led to the chip roadmap at Intel. So we're lucky in that we have a CEO that can really span engineering, product development, commercialization, and team building. So I think it's a great company for you all to be aware of and watch. Now, I'm going to probably skip over the slide because everybody, I think, on this call understands the promise of quantum computing. And I'm going to just say that I think we're all in an exciting field. Now, the challenge that we're really working towards is large-scale computation with error correction. And I've heard a number of other speakers talk about error correction. Right now, it's something every company is working on, and I think will greatly help us as we move forward in quantum computing. Now, just to talk a little bit about neutral atom technologies, I call this like a newer technology just because it hasn't been talked about so much, or there's just a number of emerging companies coming through. Each of our qubits are formed from neutral atoms, and each atom is natural, so they're all identical. We use strontium-87, which is the same element used in the world's most accurate atomic clock. Our founder, one of our founders and CTOs, Ben Bloom, has worked a lot with this element, and he actually was the person that developed the world's most accurate atomic clock. So our qubits are controlled by lasers in free space. And so what's so exciting about this technology is the scalability. We can put millions of qubits in an area that is 1 cubed and at room temperature. We also have very strong coherence times, which I'll come to that. But we believe because this is a room temperature device and we can put so many qubits in this small area that we will have the lead, or we will be able to make smaller and smaller devices as we move to the future. All right, and Michaela, I'm watching time. So right now, we have announced that we have a device with 100 qubits. We believe we are the first to 100 qubits. Actually, we've done this work in less than 2 years, which is very exciting. And there's quite a bit more in our labs that we'll be announcing over the next year. So keep an eye on us and what we're doing, because I think it's going to be pretty exciting. Now, in August, we did publish a paper on arXiv that showed we had very high quality qubits. Our coherence time is long, which is greater than 40 seconds. And we're quite excited because the longer the qubit coherence, the more time we'll have to perform accurate error correction. So this is just one of the features of our system or our device or this technology that we think is going to lead to a great quantum computer. Next up, in scaling, I mentioned earlier that in this cube that's really a millimeter squared, we can literally put thousands of qubits. And so our point of view is that we're going to put as many qubits as we can in the cube and then do some interconnects as we want to scale the computer. But we're really excited that our individual units are going to hold so many qubits, unlike other modalities where, for example, a trap has a limited number of qubits it can hold. We think that our capabilities are going to help us scale much better. I wanted to show you a picture of the current device today. And I think they all look pretty much the same. But you can see that it's a big table, and we are working on bringing down the size, but wanted to just give you a picture of what it looks like. As everybody always asks me, what does it look like? So next slide. So what we're doing with this computer is this year we've announced it, and that was just recently, and we are looking for people that will do beta testing on it. So those of you that would like or be interested in trying out our computer, we are doing projects and looking for people doing beta testing. We're also looking for interns, if any of you are interested in internships. And then also this year, we are aligning our software with software and the cloud ecosystem so that we can offer a complete solution stack. So a lot of work to do this year. In the next year, we are going to launch our system as a public cloud service. And we do already have a nice sized applications team that can help guide the customers to using this hardware and kind of the ins and outs and individualization of this hardware. So I think that's an important thing to note, that each hardware modality needs a certain amount of tuning and attention in order to gain the most optimal performance that you can from it. And then in the future, we are looking at how we can scale the system, expand our use cases as we scale, and look at broader user adoption. As many of you know, I'm pretty well connected in the ecosystem, and we are going to be working with a lot of different startups and universities around the world. And these are relationships we've already been putting in place. So we're quite excited about where we're going over the next year or so. And I encourage you all, if you're interested in beta testing, or you're interested in an internship or a career with Atom, to reach out to me. Finally, our team right now, we are growing. I think this number is already wrong. We say greater than 30 employees. It's a lot more. So the team is growing very quickly. We have a number of locations around the world. So it's a great group of people and a great place to work. And so you'll hear a lot more about us as we move forward. And then let me go to the last slide, if I can. Why isn't my computer changing slides? There we are. So we have a cute campaign that we're a little bit obsessed with quantum computing. And we feel that we're very committed to winning this race. We have a lot of funding and support from the venture community. We have a lot of support from the scientific community, very high quality qubits, and we feel we have a very easy or clear path to scaling. And then finally, I want to just mention again to take a look at our website. If I can change the slide, there it is. Well, maybe not. And we're Atom Computing. Our website is atom-computing.com. And keep a watch out. And also please connect with me on LinkedIn. And if I can answer some questions or get you involved in the work that we're doing, I'm very happy to. So thank you for your time. Thank you for allowing me to rush through this. And I look forward to the discussion later.
Thanks, Denise. Very interesting topic as usual, but impressed by the result that you just obtained. I would say in general, I'm really impressed by all this talks we had so far, because we were talking about the same subject, but we have completely different talks from all of you. So I'm really incredible and interesting this topic, and you can see how fast we are evolving, and I mean, how different is this topic as well. But let me please introduce our last speaker, Alejandro. I will leave the stage to you, and then we will have our roundtable. So can't wait for it. So Alejandro, this is your time. Okay, perfect. We can see your screen, but we can't hear you.
Let me just unmute. Okay. Is that?
Yes.
Perfect.
Perfect.
Okay. Thank you, Michele. Yeah. Thanks to the organizers for the invitation. It's a pleasure to be here in QTML 2021. So my name is Alejandro Perdomo Ortiz, and I'm the Associate Director of Quantum AI at Zapata Computing. And I wanted to share with you today a little bit of a taste of what we do at Zapata Computing in terms of quantum AI research. So our mission, I mean, what we've been, in my case, in my career, what I've been always very passionate about is, and the mission of the team is to discover a path to quantum advantage. In particular, the applications that we are looking in quantum AI is machine learning and optimization problems, combinatorial optimization problems. So one of the things that we take very seriously is about the innovation, is the research, and is the innovation in quantum algorithms. I'll try to give you a couple of examples where we think of how to bring these algorithms closer to the applications, to the key applications. Another thing that we've been actually working inside the team is leading the software development, because we realized that actually for these applications and this deployment of these quantum computers to match the complexity of the applications, it requires actually very powerful software platforms. And finally, something that is actually at the very core of the foundation of the team and also the foundation of Zapata is we really take very seriously understanding what is actually the limitations and the opportunities in these quantum enhanced models. As we know, through this conference, this is still an early field. It's been, for the most part, for many years now, almost a decade, but I would say it's still actually, there's a lot of unknowns, and that's basically where we spent a significant amount of time in the quantum AI team. So let me just give you a quick overview of some of the ideas of these principles, or how we go around these principles. So like in terms of actually going for a near-term strategy for quantum advantage, our main approach is to focus on hybrid quantum classical algorithms. And this is just a realization that most likely we know that quantum models by itself in the next 5 years or so, they're not going to be standalone. And this is actually a talk, you can listen to the full presentation by Manuel that he presented, I think, on Wednesday, yesterday. And the idea essentially is that by adapting state-of-the-art deep learning algorithms and inserting the quantum component where it makes sense, you might be able to boost the performance of a state-of-the-art machine learning algorithm. So it's this hybridization that we believe it could actually lead to some quantum advantage in the near term. And this is just a realization that was an experiment that was done with IonQ in the IonQ hardware. So I mean, with this type of innovations and with this type of algorithms, we can take kind of like the state-of-the-art implementation and generating handwritten digits from, I mean, what you see here on the left is the panels is the zeros and ones from the previous work. And now actually we can enhance the resolution to pretty much take this hybrid approach where the digits are generating from samples from the quantum device, pretty much at the end of the day. So after post-processing with the neural network. So there is really this tight connection between the quantum and the classical device. So another work in our mentality of how to take to achieve near-term quantum advantage is we're putting the bet in quantum-inspired algorithms. So this is something that is at the core of another talk at QTML that was done that was presented on Monday by Javier Alcázar. This work is about the quantum enhanced optimization. So without walking you through this diagram, you can look at you can listen to the talk by Javier. But basically, this work is the first, to the best of my knowledge, is the first work at the intersection of quantum computation. So we're introducing quantum models at the intersection of quantum computation, machine learning, for solving combinatorial optimization problems. So basically what we came up is with a family of optimizers that we call this family XQEO, and the X is because it could be, as you can see at the middle, at the heart of this algorithm, is that you can insert either a quantum generative model, like in the case of quantum circuit. You can insert a hybrid strategy, as the one that I described before. You can insert a quantum-inspired algorithm, or you can insert an entirely classical neural network, or again, or any type of generative model. So, and the idea of this algorithm is that it will boost the performance of any of your classical optimizers by leveraging the data that is coming from that solver and then proposing new candidates. So that's where the generative model part of it come, and it could be a quantum component. And that's actually what we tested. So we tested in particular the quantum inspired component, and this is what we call TNQEO, just because it's based on tensor networks. So what you see in this plot is actually is something very exciting that we found, is that even this algorithm that is completely new is competitive and is even outperforming state-of-the-art methods for these particular applications. And this particular for this particular application in portfolio optimization, like Bayesian optimization, like GPyOpt, or even off-the-shelf solvers like simulated annealing, we are outperforming this type of algorithms. So just to point something that actually, this is not just actually a toy model, and it's not just as I presented here, we have 100 assets. And in this particular case, it would represent a tensor network of about 100 qubits. And this is the case also with the SP500. So we can even load the entire market, like the SP500 market index. We can load it and still obtain a relative quantum enhancement with our TNQEO compared, for example, to other solvers like simulated annealing, just by introducing this, this quantum-inspired strategy. One of the highlights is that it also overcome many of the bottlenecks of quantum optimization. And is that, for example, when you think of QAOA and other quantum heuristics, you're not only limited by the number of qubits that you can simulate or that you can achieve in hardware, but also by the type of cost function that you are dealing with. So usually we think of a polynomial. In QEO, the beautiful thing is that it's an entirely black box solver. So I can work with any type of cost function in the same way that Bayesian optimization works. So it's a very flexible platform, and we're testing this in many other with customer applications. So in my mind, and I think that's the maybe what we're putting to bet, I think this could be actually maybe the closest path that could lead us to a practical quantum advantage. That's something that could impact industry and business with this type of technology. As I mentioned, at Zapata, we also care about the foundations, because I mean, we're still understanding where is actually the power of these quantum algorithms, where is actually where this speed up coming from. And one of the questions that is very close to my heart is this question of generalization. That's actually the foundation of machine learning. If your machine learning model does not generalize, basically it's not doing anything. So generalization is this concept that you're not just trying to memorize the data, you're trying to really perform well in data that you haven't seen. And what you see here is that, again, this is with QEO. At the core of QEO working correctly, it needed to generalize. Why? Because what QEO is doing is absorbing data. That's the blue histogram that you see here. And then it's coming up with a generative model that is supposed to generate new candidates. So the orange histogram here is all the portfolio optimization generated by the quantum-inspired model. And what you see is that the candidates that is generating is not only generating new candidates, as you can see in the inset, is not only generating candidates beyond the classical regime, but it's also beyond what was obtained with the classical model, but at the same time is generating candidates with a better value, like a lower cost, in this particular case, the portfolio risk, than actually was obtained with the classical training, with the classical data set. So just to mention, I mean, I just wanted to point that at the core of QEO is this concept of this tensor network ball machine. And this was work that actually was done in the group of Lei-Wan. And this is actually the type of generative model that we use at the heart of QEO. But you can swap this easily by a quantum circuit. And this is something that is that we're testing as well. So finally, my final slide on this topic is generalization as well. We have observed generalization also in another type of quantum model that we introduced a few years ago, is the quantum circuit ball machine, the QCBM. And it's a circuit-based model to load probability distributions. So what you can find here in this paper that we just released a couple of days ago in OrgVis, that is a platform to study and understand the landscape of parameterized quantum circuits. what you see here is that in this particular histograms, this is the true distribution that you would like to learn. This is the finite sampling distribution that you would get by sampling from the true distribution, just only 500 samples. And then as you can see, there are some gaps. But actually, if you zoom into these areas where you see that the model obtained from the QCVM is filling in the gaps. Basically, this is an indication that the quantum model, the quantum circuit-based model, is generalizing. So of course, I mean, this is just a pictorial representation of what's going on, but if you want to look at the numbers and look quantitatively how this is being measured, I invite you to take a look at the paper and also to take a look at some follow-up work that we are doing also on generalization in this particular quantum models. So with that, I would like to wrap up. This is the summary. So I hope, I mean, you got a little bit of a taste of what we do in the different areas. So in the part of quantum algorithms, I gave you a couple of examples with QEO and QCN. And just to mention that actually, we're very much interested as well in looking into post-NICs and fault-tolerant quantum computation. That's actually looking for quantum advantage in quantum machine learning in that domain. In the libraries that we're building, so OrgVis is just an example of something that we made for the researchers because we needed that tool. And that's something that we put available to the community. But also we will be releasing next year QML Suite, that is actually an integration of how to do these applications in a scalable way. And that's something that we're working on that we will be releasing next year. And just finally, as I mentioned, we're really much looking also into the deep research questions of what it takes to actually to have these quantum models to generalize, to avoid trainability challenges, and what is actually this expressive power of these quantum models coming from. So with that, I conclude, and I just wanted to thank, I mean, the Quantum AI team at Zapata. It's been an intense period the last year, just growing the team. Now we're ready for prime time, and we're excited to release a few papers in the coming months. And yeah, so stay tuned for some of the research coming out from our team. And we're growing, so please please keep an eye on some job postings that we're going to have on research as QML research scientists, ML engineers, and quantum AI interns for our summer program. So thank you, and I'm open for questions. I'm giving it back to you, Michele.
Yeah, thanks a lot, Alejandro. Very interesting talk. And of course, I see a common point in every speech. So everyone seems to look for new collaborators and new people joining the team. So that's very interesting because of all the people that are listening to us. So it's an important step in the evolution of the training we do in the academics in the university, but also the way the industry are adapting their strategy and the way they are skilling the people. So maybe one of the questions that I'd like to ask to all of you, and maybe we can start again from Mehdi that start the panel here, is how you see the evolution of the requirement from the industry in terms of people to acquire. So which kind of skill we are looking for? Because looking for a quantum algorithm in general is, it's very interesting, but maybe it's not making sense because it's a very wide topic, as you can see here in the round. In the speech we got, we had 7 speakers and everyone talked about completely different things, even if there are some overlap, of course. So how the demand from company has changed during the year, and how the team building is changed, because I would say that from the beginning we have just very foundational research, but now we have also deep learning contribution, machine learning contribution. So what is the evolution in that?
So actually, yes, the ecosystem is evolving, and the demand from the industry, from what I'm getting when talking to potential partners, is evolving. But the main thing that everybody wants today is, first, everybody's looking for interns and talent, so that's a given. And also on the industry side, everybody's looking at not only getting quantum enabled from an algorithm point of view and use case validation point of view, but also the big trend right now is how do you enable, let's call them standard developers, how do you enable them to quantum computing? So not the people who are going to build new algorithms like researchers, not people who are going to take existing algorithms and do modifications so those algorithms, modified algorithms, can handle specific use case from the industry, but people who can actually implement stuff and leverage existing libraries and things like that. So that's really a big trend right now.
Yeah, thanks a lot. I would say that one of the topics that was also discussed during some of the talk was about essentially the way we build algorithm. In particular, the talk from Joe was about the abstraction of the code. So how the input from the industry is important in this field. How do you see the contribution from their knowledge can help us to understand the way to develop new algorithm or the way to improve those algorithms? Because then we should, let's say, define very specific recipe for every industry sector, which is something very important from their side, but sometimes it's different to match from the research point of view, because maybe we tend to generalize the things because we want the best generalization algorithm and so on.
So, I mean, I guess I can take a stab at this. You know, the way I see it, the task of building applications that are relevant to industry is a tricky one. But we, you know, in general, in our field, we have this danger to charge forth, assume we know best about all aspects of the problem, and try to insert ourselves as the solution provider. That's why we focus on trying to abstract away quantum computing so that it can really be the domain experts that are generating their own tools. I think realistically, if you think about it, like, how do you come up with a quantum algorithm for simulating turbulent fluid flow, for example? Like, there's just, I don't think any of us in the room at the moment are experts in that. There may be experts in quantum computing for sure. I would imagine most people here are, but you know, on quantum algorithms and so on. But like, actually, for the specific problems, you need domain expertise as well. And you know, once you have this issue, you need to kind of bring those expertise together: the quantum computing expertise and the expertise for the particular problem domain. And you know, there's ways you can do that. I think a lot of the companies have different models for approaching this, whether that be libraries, whether that be consulting, or for us, it's abstraction. But you know, we're all about trying to remove that friction, to have use cases driven by users.
Thanks a lot. I don't know if some of the other panelists want to say something about this topic.
Yeah, maybe if I can add, I agree 100% with Joe, in particular that example of the fluid dynamics. We had several cases in our team, for example, as I presented in the team. If you look at that picture, actually, for example, we had to bring someone actually who worked at a bank for 12 years and doing actually trading and in finance. And I mean, with a background in physics at some point, in string theory, but at some point interested in quantum. And we actually needed to retrain this person in some way to get it. I mean, he was interested in quantum computation, and that's how the collaboration started. So this, I mean, it's really hard to find out these unicorns, people who know very well the application, who have worked in industry, who maybe, in the case of engineers, sometimes it's even more difficult, like people who have done extensive coding and has the right engineering skills for building these platforms. So like all this integration is a difficult task. And I guess that's one of the challenges. And that's why in part building that pool of talent is so important. And in particular, of course, I mean, we have a lot of people that come mainstream with the quantum computation background, straight from the PhD in quantum physics. But that's actually, so for example, in my team, there is still kind of like a portion of what really makes the team. And for example, we had someone straight from ML, like just ML background, working 10 years, so in the industry. So that's kind of like the differences, I would say, of how maybe academia is done. I think in industry, the need for this expertise requires also the search for this talent that is quite different from, for example, if I were doing this in academic setting.
Yeah, that's perfectly clear, and I completely agree as well. I would like to talk about another point that were somehow discussed during some of the talk. So to make an impact in the industry, it's important not only to have an algorithm and so on, but also we want to make a real quantum computation. So we want to translate the algorithm that we have on real hardware, and we had the opportunity to listen from different companies that were introducing different technology. We have some superconducting qubits, we have the atoms, and so on. So maybe one question, maybe for Denise, for Francesco, that we're talking also on the hardware side, how to make an impact in the industry with the hardware. So now that we have some algorithm, people want to run it on the real hardware. So of course, we are looking for quantum advantage. So what are the main ingredients that are very important to run those algorithms on the hardware? So Francesco mentioned something about the time we need to execute it, because now the industry want to test them. And of course, they have very strict parameters in terms of efficiency and in terms of time for execution. So how do you see this contribution from algorithm to the hardware execution?
Yeah, thanks, Michele. This is indeed a key message that we have to give, particularly in industry panels like the ones that we are having now. So indeed, it's not enough anymore to just say we have quantum hardware somewhere. It's also now becoming a matter of making this hardware accessible, but accessible in a useful way. So this is why the key performance indicators for any quantum computing technology provider must, from now on, also focus on how consumable these devices and platforms are from an industry perspective.
I would rally a little bit against this. I think the key performance indicator for quantum hardware is the performance of your device. Until you go beyond classical, until you're generating something that we can't do on a simulator, there's no value for industry. You have to, you really want to focus on generating top quality qubits, and you really want to focus on generating, on learning things from the device so that we can build better devices. I think it's important to focus on stability so that we can eventually offer something, but we shouldn't let the push to try to publish, so many, we shouldn't let the push to try to get everyone on the devices that we have now. We shouldn't let that distract us from building bigger and building better and trying to achieve all of the roadmaps that we've seen today. These have to be the priority, because if we don't eventually deliver on our promise to build, future fault-tolerant devices that can achieve the goals that we're aiming for, then we will really hit a quantum winter, and we're going to hit it hard.
Yeah, I agree. I agree with you on. Oh, sorry. Is anyone else?
Go ahead.
I agree with you on.
Yeah, Francesco, go ahead. Then we have the news.
I agree with you on the fact that we need to keep pushing to not lose the final objective. What I disagree partly is it's not a matter of selectivity in a way. So it's also good to expand your network and your capabilities, particularly also related to what we were discussing before, which is none of us is actually usually an expert in some of the fields that industry considers relevant. So this is something we value, I think. And on the other hand, I agree with you that we should continue pushing, improving on the hardware side, and by no means I'm dismissing the crucial focus of the field, which should be on hardware technology and hard tech and software and so on. What I wanted to make the point about is that we need to establish a holistic view of the field and of the performance metrics that we want. So not only more qubits, not only better qubits, but all the full stack towards application. Then, of course, we need to get to the point where we can do something that cannot be simulated classically. And for this, my hope and what I'm working for is hopefully to get there before we go to the fault-tolerant regime. We already know that in the fault-tolerant regime, if that can be achieved, there are algorithms that can provide useful speedups. Of course, we can discuss and debate about what's the threshold for that and what are the prefactors that matter in that case for world-relevant applications and so on. But I think we should really push to get to something, to quantum advantage in a way before we get to the realm of full fault tolerance. At least try.
I think it's I think at least trying is something I can definitely get on board with. And I also want to stress, I don't mean to dissuade us to engage with that. I agree with you 100% that we need to engage with industrial partners. I guess I just want to stress that I think that a lot of the research that we do is on, like, a lot of the research that we do in quantum still remains very, very fundamental. And I think if you want to look for quantum advantage in industry, the thing that we need to focus on is on the proof, right? We need to focus on having something which we can demonstrate and which we can be sure about in all of these different areas, in fluid dynamics, in chemistry, and materials science, in every application that we go for. We can demonstrate that we can be sure that when we do eventually move to a future fault tolerant device, it will be achievable, right? I mean, the obvious case here is, which is the noticeable thing that that the Google team has worked on in the last couple of years is to give a serious look to the cost of doing, say, algorithms with quadratic speedups on a fault tolerant device, and you just can't beat the constant factor, is what we found. And so this is why we're shifting away from algorithms that don't have anything beyond a quadratic speedup. You really need to go beyond quadratic to get a quantum advantage somewhere. And I think that like algorithm, and I guess the thing I just want to push back on is just to stress that this is the thing that we need to focus on with industrial partners. This is where we need domain experts to come in and learn about quantum and understand what makes quantum problems hard, and try to understand and try to find those areas in their fields where quantum hard problems might lie. Because if we don't have the proofs for this, if we don't have like the ability to say that, like, that we think that this quantum algorithm can do something not just that the classical algorithms we have now can't do, but also the classical algorithms that people develop in the next year can't do. If we don't have that, then we won't, then it won't become it won't become a useful application in the end. But again, I agree with you 100% that that we should be looking towards each and every application that we can possibly find, and that includes trying to push towards a potential NISC application, even if we don't do or don't have so much hope that they might actually exist.
Yeah, thank you. And to give you back, yes, I also agree with you that we should not forget and actually focus even more on fundamental research. And I mean, I'm a physicist by training, and I love seeing quantum simulations and the Hubbard model simulated on quantum processors. What I'm pushing myself to do is also to see how all of this, that it's fascinating for a scientist, could also be an approvable and solid manner being translated into something which is useful for the industry.
Comment something super quick. Just to reply quickly, or maybe just a comment, because my view from my experience working with applications, maybe I differ a little bit with Tom. So although I agree it's extremely important for us in the community, and in particular, this is a quantum machine learning conference, to come up with such a proofs, algorithmic proofs, because that's what usually is driving the developments and the growth of quantum computation. I don't think actually that's the only way. And just as an example of that, I mean, machine learning would have not existed, or even AI, if it were not because of all the heuristics. I mean, in reality, when we look at the AI and the developments, how actually all the industry, all the different applications that we see today in machine learning, none of them actually claim even a proof of even differentiation with other algorithms. They just works. I mean, actually, there is a foundation of why it works, but in reality, there is no like a proof of speed up. So I think I would like to distinguish between understanding where the speed up and where the advantage is coming from, to actually require, like, as maybe theoretical computer scientists tend to think, that actually you need an exponential gap or a quadratic speed up. Sometimes, I mean, when we talk to customers, even if you give me a factor of 2, and actually this is even talking to Harmut Neven back in the past, if a customer comes and they give you, and if we obtain an algorithm where even you can do things twice as fast or four times as fast, then that's enough. So I think that there should be a compromise in that there is an opportunity for both, for the quantum heuristics and also for the foundational work. And I think it's important to balance those ones.
I'll put a challenge out to you there then. I mean, you know, the thing there is that if you want to learn how your model is performing on a quantum device, you can put it on a simulator and run it on a small scale. And I guess one of the things that I'm interested in from the quantum machine learning field, and I don't believe I've seen this, although I will admit, you know, if someone can present me a paper right now or later where they actually do this, I'd be very excited. I'd like to see a presentation where someone finds a quantum machine learning agent that beats classical machine learning agents so thoroughly that we start using the simulation of the quantum machine learning agent in place while we don't have a quantum computer that can go beyond classical. We start using the simulations of quantum machine learning agent for application. I mean, that should be a good target, right? Because if we can't, if you find that the QML agent or the simulation of the QML agent is not already like doing significantly better than all classical counterparts, then it would be then maybe the cost of putting on the quantum device is going to be quite large. So I'd be very interested to see that. I think that would be an interesting example of, I would say that's also still, you know, fundamental research.
I agree 100%, and that's a challenge that doesn't require the proof, but I agree that's an excellent challenge.
Can I make a comment at this point in relation to this? I think to some extent people are speaking at odds here. It is definitely clear that there is fundamental research to be done, that there's a lot of progress that's still required on hardware. It is also true that on the software side, on the computer science side, you know, we maybe need to fit 70 years of computer science research into 7 years. But when we get to problems like quantum machine learning, there's different kinds of things. You can prove advantage for HHL-based algorithms if you have QRAM and things like that, but that's hard to build. If you go to the heuristic algorithms, you can't prove anything, but that's true in the classical domain as well. So you can't prove anything because you know, once you start trying to axiomatize everything, you get learning theory, and then you just prove that nothing can be learned. And I think it's, you know, important that we be exploring both options as we go forward, because if we focus purely on the hardware, we're going to get to a point where we have hardware and that hardware has no applications. And that's a danger as well. That's as much a danger of causing quantum winter as us not getting the hardware.
I would like just to comment briefly. I agree with what Joe said. Also with the fact of building a community of people that in some capacity are able to use tool, open source library. This is really important to avoid, you know, this not favorable scenario for the industry. But going back to quantum advantage, you focused a lot on speed ups, and those are clearly great and very interesting. But I think that in the NISQ era, especially for machine learning, other concepts such as learnability or sampling efficiently or hardness when it comes to sampling and state preparation, these are also concepts which we should explore and consider when looking, let's say, at quantum advantage. There are a few people I can see here among the panelists that know this topic very well and have contributed into putting forward this argument. So they may want to add something to this. But I think that, you know, beyond speed up in the NISQ era, there are also other angles, especially the quantum machine learning can explore to prove an advantage.
This is true.
Yeah, so
this I completely agree with.
We have Denise that were saying something, and then we can maybe close, even if this roundtable is lots of interesting. So I hope we can meet again sooner or later. But I'm pretty sure Denise was saying something before.
Well, I think Tom said it very well. So I'm gonna just agree with Tom and thank him for his comment.
Okay, thanks a lot. I would like to thank the organizer for inviting me and to give us the opportunity to have all of our panelists. It was very interesting talk. Of course, thanks a lot for your effort to be here in such a diverse time zone, which is somehow funny, but also not very easy. So thanks again, and I hope to see you next time.
Well, thank you very much again for all the inspiring, very inspiring, fascinating presentations. I'm very sorry that the time is very short. So I really appreciate that you spending the time actually talking and presenting to us. And thank you, Michele, for chairing the session. So thank you very much all again.
Such a pleasure.
We have some people asking questions in the chat. Maybe you can answer them directly in the chat. Actually, there are some questions in the chat that are as well from the audience. I'm sorry, the time is just too short. Otherwise, we can actually just carry on the discussion for a long time, I think. But thank you very much all again, and hope to see you again soon. Thanks a lot.
Bye. Thank you.
Thank you. Bye-bye.
Now we move on to the next session of the conference. Franco.
Well, thank you for all the panelists. That was great. Great. Yeah.
Yeah, we're just too short. Yeah, the time is just too short. Be Yosuke Nomura. Excellent.
So do you see my slide?
Yes.
Okay, let me do the following. Yusuke, can you raise the volume of your microphone because it sounds like you're far away.
Yeah, okay, I will speak loud. Is it okay?
A little bit louder would be good.
Yeah, a little bit louder because the voice sounds like very distant. So you need to perhaps get the microphone closer to you, perhaps.
Yeah. So if you have problem, please let me know. I will try to speak louder.
It's still too low. Can you increase the volume, perhaps? You go to the audio settings.
Yuri? Strange. Too small? Too small?
Because the volume is too low.
I see. Actually, I have never experienced such.
Yeah, I think the audio is fine. Franco, try to raise your volume.
Okay, fine. Okay, if other people can hear it, it's okay. Okay, great. So therefore, welcome everybody for this afternoon session. There are about 45 people in the participants, actually 46 now, so there are quite a few. So the first speaker is Yusuke Nomura from RIKEN, and he's going to talk about artificial neural networks for representing quantum many-body states. Please go ahead.
So thank you for the introduction. First, I'd like to thank the organizers for inviting me to this very nice conference. So today I will talk about the artificial neural networks for representing quantum states. And the collaborators are listed here, including the next speaker and the chair. So the quantum many-body wave functions are key quantities in understanding the quantum many-body phenomena. And if we have good answers for the wave function, and actually it promotes our understanding of the physics. And for example, the BCS wave function explain the conventional superconductivity. So the problem is how to approximate the quantum many-body problem, quantum many-body wave functions. And the difficulty comes from the fact that the quantum state is represented by the superposition of infinitely many number of interdependent configurations. So the dimension of the Hilbert space grows exponentially with respect to the system size. So in general, it is not possible to obtain the exact eigenfunction. So in this sense, the accurate representation of quantum state is a great challenge in physics, as well as in other fields like quantum chemistry. And thanks to the recent development in the numerical method, we can have the sophisticated wave function. In particular, recently, the artificial neural networks are gathering a lot of attentions. So let me introduce such neural network wave functions. So let me start from the simplest neural network, the restricted Boltzmann machine. So here we show the structure of the RBM. So here we have sigma spins, and this is called visible spins, and it corresponds to the physical or degrees of freedom. On top of that, we have auxiliary degrees of freedom or hidden unit. Then we have this extended Ising type system. Then using this extended Ising type system, we define the Boltzmann weight using the energy of the RBM defined by the magnetic field A and B and the classical interaction W. Then if we trace out h degrees of freedom, we obtain the wave function. And if the variational parameters A, W, B are real, this wave function becomes positive, right? But in the general case, the wave function can take negative value or even complex. So in that case, we need to extend the definition of Boltzmann weight to the complex weight. And then we need to extend the definition of variational parameters to be the complex variable. Okay. Then the good point of the RBM is that it has the property of the universal approximation, meaning that if we introduce infinitely large number of hidden units, then we can represent any kind of wave function. Also in this RBM, because we do not have the interaction among h spins, we can analytically trace out h degrees of freedom. Then we can obtain this analytical formula for the ansatz. So we can use this as a new variational ansatz in the physics field. Okay, so the RBM is a kind of shallow network, but we can also go to the deep neural network. So this is the structure of the deep Boltzmann machine with additional or hidden layer. Right? So now we have two hidden layers, but to distinguish between these two, we call these spins H and these spins D. Then again, for this extended Ising type spin systems, we define the Boltzmann weight like this. And then if we trace out the auxiliary degrees of freedom, H and D, then we obtain the wave function. So this is the DBM wave function. And then as we see, the form of the wave function depends on the variational parameter A, W, B, and so on. So the problem is how to optimize these parameters to approximate the quantum state. So let me take an example for the ground state. So the ground state is the lowest eigenstate of the Hamiltonian. So in this case, we can take the energy as a loss function. Then by minimizing the energy, we can approximate the ground state. Then the problem is how to stably minimize this loss function or the energy. Then from the physics point of view, we know that if we perform the imaginary time evolution by the Hamiltonian, we can reach the ground state. So namely, if we start from some initial state, which is not orthogonal to the ground state, then if we perform the imaginary time evolution, then in the limit of infinitely large time, we can obtain the ground state. Right? Then we know how to reach the ground state. Then the problem is how to numerically reproduce this imaginary time evolution. Then in this talk, actually, I will present two different approaches. One is the analytical method by the deep Boltzmann machine. And the second one is the numerical method using the RBM. So this second method is a more kind of usual approach. We stochastically optimize the neural network. But let me start from this analytical method, which is different from the numerical or optimization. So again, let me introduce the DBM wave function. So here, this is the structure of the DBM. And if we, by defining the Boltzmann weight, then if we trace out H and D degrees of freedom, then we obtain the wave function. And the good point of the DBM wave function is that compared to the RBM, because we have additional hidden layer, DBM has much more flexible representability. But in this case, unfortunately, we cannot trace out H and D degrees of freedom simultaneously in an analytical manner. Then to obtain the wave function, we need to sample all the hidden spins. Of course, we can think of optimizing the DBM parameters numerically, but we know that the deep neural network is much more difficult to optimize compared to the shallow or neural network. Then it is good if we can somehow avoid the cumbersome numerical optimization. Then the key idea of the method is that first we introduce the Suzuki-Torotta decomposition to the imaginary time evolution. Then actually with this decomposed short time propagators can be reproduced by the DBM. This can be done analytically and exactly. Then by successfully applying the short time propagators, we eventually get some DBM structure which represent the ground state. Then the physical quantities can be measured by the Monte Carlo sampling over the hidden spins and the visible spins. Then in this method, we map the quantum state to the classical or DBM system analytically. And then actually this method provides Nobel class of quantum to classical mapping. Okay, let me show an example using the transverse field Ising model. So in the case of transverse field Ising model, the Hamiltonian can be divided into the classical interaction part and the transverse field part. Then the problem is how to satisfy the short time propagators from the interaction and the transverse field. So namely, starting from some DBM structure, applying the short time propagator, then we want to reproduce this evolved state by modifying the DBM. So let me show an example, show a solution. So first, let me start from the classical interaction propagator case. So this is the initial DBM state. Then if we want to satisfy this classical propagator, the solution is to add one hidden unit. Then the new coupling is given by this analytical formula. Then we reproduce this propagator. And the interesting point here is that to satisfy the classical propagator, actually we do not need the deep unit. The shallow network is enough. So in this sense, to reproduce, to approximate the classical or quantum state, the shallow neural network is enough. But on the other hand, in the case of quantum propagator, like a transverse field case, to exactly reproduce this propagator, the deep unit play an important role. So our solution is to add one deep unit and one hidden unit. Then if we modify the coupling like this, then we can satisfy this propagator. Okay, then we can also do the same thing for the Heisenberg model case. So again, starting from some DBM state, what we want to do is to satisfy the short time propagator by the Heisenberg type interactions. Then for this, actually, we find at least 3 different solutions. First one is called 1D3H because we add 1 deep and 3 hidden unit to satisfy the propagator. And the second one is 2D6H. And finally, we have 2D4H solutions. And this is the DBM structure after the propagation. And it looks like a completely different DBM structure. So you may think that these DBM represent completely different quantum state, right? But this is not the case. So remember that the quantum state is given by tracing out h and d degrees of freedom. So the total weight after summation is the quantum state. So let me consider the case where the total sum is 10, 1, 0. Then we can divide 10 into, for example, 5 plus 5, or 4 plus 4 plus 3. So we have some arbitrariness to divide how to divide the total sum. So these three solutions correspond to the different way of dividing the total sum. So again, the quantum state is given by the summation over after tracing out h and d degrees of freedom. In this sense, these three structures represent completely the same state. Okay. Then now we have a recipe to satisfy the short-time propagators. Then by successfully applying the quantum short-time propagators, then we eventually get the ground state. Then to satisfy the propagators, we add hidden unit at each propagator. So the number of hidden unit or deep unit becomes proportional to the system size and also the imaginary time. Okay, then here, let me show a numerical example for the transverse field Ising model. Here we take a small system size, like 20 spins. So in this case, we can perform the exact diagonalization. So compared to the exact result, the DBM result reproduce the exact evolution. So this is just a numerical check whether our method works or not. Okay. We can also apply to the one-dimensional Heisenberg model case. Now, in this case, actually, we try two different initial guess cases. So first one is we start the evolution from the empty network. So in this case, we need a large time propagator to converge to the ground state. On the other hand, in this method, we can also take the initial state as a pre-optimized or numerically optimized RBM. Then in this case, we can quickly reach the ground state. Okay, so to summarize the first part, we show that using the DBM, we can analytically construct the DBM structure which correspond to the ground state. And actually, this DBM representation gives a method for the quantum to classical mapping. And actually, we can say that this mapping incorporates the path integral or formalism. For example, in the case of Heisenberg model case, the second solution, 2D6H case, actually, we can show that the way of dividing the weight is completely equivalent to the conventional path integral or formalism. So it has some correspond to the conventional quantum to classical mapping. And we can say that DBM indeed has very flexible representability to enable the quantum to classical mapping. We can also have a nice correspondence to the statistical mechanics. So in the case of DBM, to satisfy the quantum propagator, the additional hidden layer or the deep unit play an important role. So in this sense, the deep layer plays a role as a kind of additional dimension or the imaginary time dimension in the statistical mechanics. But unfortunately, if we want to apply this method to the frustrated spin system, so I show the application to the spin system without frustration. But if we want to apply this method to the frustrated spin systems, unfortunately, we suffer from the negative sign problem. So even in the case of frustrated spin system, we can somehow construct the DBM structure. But to measure the physical observable, we need to perform the Monte Carlo sampling. And in this Monte Carlo sampling, the weight becomes negative, and then we cannot accurately estimate the physical observable in the case of frustrated spin systems. Okay, So although this method is nice, but it has some problem in the frustrated spin cases. But we want to apply the neural network method to such challenging problem, right? And then in this case, we propose that we should numerically optimize the RBM. So here in this case, to satisfy the imaginary time evolution, we numerically optimize the RBM. And in this case, we can reproduce the imaginary time evolution as accurate as possible within the representability of the variational answers. Yeah. So again, let me show the structure of the RBM. So if by defining the Boltzmann weight, which is extended to the complex weight, and then if we trace out h degrees of freedom, this gives the wave function. Then to approximate the imaginary time evolutions, what we want to do is to minimize the distance between the exact evolution from the approximate evolution by changing the variational parameters. Then the update of the variational parameters is given by modifying the gradient of the energy by the geometry of the wave function space, or the quantum version of the Fisher information matrix. And this update scheme is called stochastic reconfiguration method in physics. But in the machine learning community, it is called natural gradient. And these two methods are independently developed in the two different fields. But now we understand these schemes are equivalent. Then to update the variational parameters, we need to estimate these, for example, gradient or the S matrix. Then this can be done stochastically or by the Monte Carlo sampling. For example, in the case of energy case, we can sample the energy by using the square of the amplitude of the wave function as the weight. So in this sense, because this weight is always positive, we can avoid the explicit sign problem in this case. Okay, let me show a demonstration in the case of Heisenberg model case. So here we take 8 spins. In the case of 8 spin cases, the relevant dimension of the Hilbert space is just 70. So we can easily diagonalize the Hamiltonian. But just for demonstration, we take this very small system size. Okay, so this is the Hamiltonian of the Heisenberg model. From this, we perform the gauge transformation like this. Then we move on to this equivalent Hamiltonian. The reason why we perform the gauge transformation is that after this transformation, we can show that the ground state wave function becomes positive definite like this. So if this wave function is positive definite, we can take the variational parameter to be real. So for demonstration, it is simple and easy to demonstrate. So we perform the gauge transformation. So in this method, first we put random initial parameters to this coupling. Then the initial RBM wave function looks like this. So it does not have a feature at all. So it is kind of flat. But by minimizing the energy, the optimized weight looks like this. And also the optimized RBM wave function reproduce the exact wave function like this. Now, if we look at this optimized weight, we have the sign change between here and here. This means that the machine learns the anti-ferromagnetic correlation in this system. So actually, this kind of neural network wave function is first introduced by Giuseppe and Matthias in 2017. And they applied this method for the spin systems without frustrations. And already at this level, actually it achieves the state-of-the-art accuracy compared to the other variational ansatz like tensor network. But for the quantum spin system without frustration, actually we can perform the, for example, the path integral type quantum Monte Carlo simulation without any sign problem. So indeed, in this paper, they use the QMC energy, quantum Monte Carlo energy as a reference for the energy. So in this sense, for the quantum spin system without frustration, the quantum Monte Carlo type approach would be the best. So the main target of such variational method would be, for example, the frustrated spin systems or the fermion systems in which the quantum Monte Carlo method suffer from the severe sign problem. So keeping this in mind, actually we extend the method for example, the fermion systems or the frustrated spin systems. So let me first start from the extension to the fermion systems. Okay, let me show an example for the Hubbard model. Okay, the crucial difference from the bosonic wave function and the fermion wave function is that in the case of fermion wave function, the sign of the wave function changes with respect to the exchange of the particles. But if we look at the neural network wave function, it looks like a bosonic type wave function. So to apply to the fermion systems, actually we need a clever way to do that. So one strategy would be using the Jordan-Wigner transformation. We map the fermion systems to the interacting spin systems. And this kind of approach would be introduced by the next speaker, Nobu. So please see the next talk. But in our case, actually, we take a different approach. So we combine the RBM wave function or bosonic wave function with the fermion wave function. Then if we combine the bosonic and the fermionic wave function, then in total, the wave function has a symmetry of the fermions. Okay, then for the fermion wave function, we take the pair product state. Or in the quantum chemistry, it is geminal. Okay. And actually, this pair product wave function is already a very powerful variational ansatz, which can represent, for example, the BCS wave function or the resonating valence bond wave function if we map onto the spin systems. So we can expect that not only satisfying the fermion symmetry, but also we can help the RBM by this introduction of pair product state. So again, our wave function called RBM plus PP is defined by the combination of bosonic RBM part and fermion part from the pair product state. Then in total, the wave function becomes fermionic. And in this case, the role of the RBM is to approximate the exact wave function divided by this pair product wave function, right? So if the pair product wave function is already a very good ansatz for the exact wave function, then this function becomes smooth and much more easy to represent. So in this sense, it will help the RBM, right? And also, if we want to apply to the fermion systems, we need to consider the mapping, one-to-one mapping between the visible unit configuration and the physical configuration, right? So one of the most natural mapping would be to take the number of visible spins to be the 2 times number of site. Then the even spin represent the presence or absence of the upspin electrons. And the odd spins correspond to the presence or absence of the downspin electrons. And then we can have the one-to-one correspondence. Then we can define this neural network part. And then we apply this combination to the two-dimensional Hubbard model. So here we take 8x8 square lattice, and we consider the special case, namely the half-fitting case. The reason why we take the half-fitting is that for this specific fitting, we can apply the quantum Monte Carlo method without sign problem. Then we can take the quantum Monte Carlo result as a reference energy. Then here, this shows the relative error of the ground state energy with respect to this exact, numerically exact QMC difference. So here we show the result for different Hubbard interactions. And we also try 3 different variational answers. So in the first case, we combine the neural network with the Fermi state. So in this wave function, the Fermi state is fixed, and we only optimize this RBM part. But in this RBM plus PP case, we also optimize this pair product part. And in this red one, on top of the PP state, we impose the symmetry in the PP part, then we can improve the performance. And actually, from the comparison between these 3, we indeed find that if we combine RBM with more sophisticated wave function, we can drastically improve the performance. And actually, this combination is in practice very good because we can somehow save the number of variational parameters. It is good when we want to apply our method to the large system size. Because if the number of variational parameters increases, then the optimization becomes harder and harder. So it is good that if we can save the variational parameters. Okay. Then let's move on to the finally move on to the frustrated spin system case. So far, we only show the benchmark result, namely by applying this method to the small system size, or the special case where the QMC is, can be applied. Of course, this benchmark is very important to check the accuracy of the RBM wave function. But now we start to understand that the neural network wave function is powerful. So we want to go beyond the benchmark, and we want to understand the physics of the challenging problem. So let me show such example. So here we take the J1, J2 Heisenberg model on the 2D scale lattice as a representative of the frustrated spin system. So here the Hamiltonian looks like this. Here J1 is the nearest neighbor spin-spin interactions, and the J2 is the second neighbor spin-spin interactions. And this model is a very fundamental model, and it is very important because, for example, it is an effective model for the cuprate parent compound, which is a Mott insulator. Yeah. So when we consider the anti-ferromagnetic J1 and J2 cases, then we know that J1 and J2 compete with each other. Then if we fix J1 and change J2, in the region where J1 is dominant at 0 temperature, this kind of nail type anti-ferromagnetic state is realized. On the other hand, when J2 becomes large, this stripe phase is realized. And in between these two phases, where J1 and J2 compete, we may have an intermediate phase. And interestingly, we may have so-called exotic liquid state called quantum spin liquid. So in this ordered state, the spins are aligned regularly. So in this sense, it is a solid phase of the spins. But in the liquid phase of the quantum spins, the spins are fluctuating even at 0 temperature because of the quantum fluctuations. So such exotic state might appear in such frustrated spin systems. So although this system, this Hamiltonian has very simple form, and it is and also a very fundamental model, because the quantum Monte Carlo method suffers from the negative sign problem. Until today, the ground state phase diagram is not settled yet. And indeed, so far, many people have tried to review the phase diagram of this fundamental model. Okay. Then we apply the RBM, again, the RBM plus PP method for this challenging system. So the difference from the fermion case is that in this case, we put the Gutzwiller factor here to map onto the spin system. So by prohibiting the double occupancy of the electrons. Then we also have a very important tip. So the important tip is to improve the performance by symmetry. So if we have the symmetry in the Hamiltonian, like a translational symmetry, then we know that the quantum state at finite system sizes can be labeled by the quantum numbers. Then we can actually impose, for example, the total momentum or total spin into the Hamiltonian, into the wave function. Of course, the ideal case would be the RBM learn the symmetry by itself. But we know that in practice, imposing symmetry helps a lot, and it improves the performance a lot, actually. Then the ground state is given by minimizing the energy for the singlet and the total momentum zero sector. Also, the good point of this method is that we can also calculate the excited state. So if we compute the, if we minimize the energy in other quantum sectors, then it corresponds to the excited states. Then using this method, we can calculate both the ground state and also the excited states. Okay, first let me show the benchmark of the accuracy of RBM plus PP method. So first, let me show the ground state energy comparison for the frustrated regime for the 10 by 10 lattice case. So in this system size, the exact diagonalization cannot be applied, but we can still compare with other variational ansatz, right? Then among the compared variational method, actually our RBM plus PP gives the best energy like this. We can also check the accuracy of the excited state. So here we take the 6 by 6 lattice because this is the maximum size where the exact diagonalization can be applied. Then compared to the exact diagonalization result, the RBM plus PP result gives a very good excitation energy like this. For example, this is the triplet excitation, and this is the singlet excitation. So now we understand that RBM plus PP gives good accuracy both for the ground state and the excited states. Then to obtain the zero temperature phase diagram, we can take two different approaches, namely one from the ground state and one from the excited state. Actually, this is the two sides of the same physics because if the ground state property changes, we expect that the property of the excitation structure also changes. So it means that if the excitation structure changes, we can indirectly detect the phase transition. Right? We can also calculate the ground state. Then from the analysis of the order parameter, we can obtain the phase diagram. Then actually these two analyses agree very well. Then we obtain this zero temperature phase diagram. As I already said, when J2 is small, the nail type ordered state is realized. And when J2 is large, a stripe phase is realized. And in between these two phases, actually we have two intermediate phases. One is the quantum spin liquid, and one is the valence bond solid. And in this valence bond solid case, the spin singlet breaks the symmetry of the lattice. So it is the symmetry broken state. But in the case of quantum spin liquid, there is no explicit symmetry breaking. So this quantum spin liquid is much more exotic state. Then we study the excitation spectra in this quantum spin liquid phase. And we review unconventional excitation structure. So in the usual anti-ferromagnet, like Nail anti-ferromagnetic case, we have the Namb-Goldstone mode. Then at the ordering vector, in this case, this is pi pi, this mode becomes gapless. Right? But in this quantum spin liquid phase, both in the singlet and triplet excitation, not only 0, 0 and pi pi, but also pi 0 and 0 pi becomes gapless. And the dispersion becomes the Dirac type dispersion. So let me show a schematic figure for the this spin dispersion. So it has a Dirac type gapless excitation at high symmetry point in the quantum spin liquid phase. Actually, this is unusual. And this unusual excitation spectra can be understood by the scenario of fractionalization. Namely, in this quantum spin liquid phase, these spin excitations are deconfined or fractionalized into the spin-on excitation. And if we consider that spin-on also has this Dirac type dispersion, then we can naturally explain this exotic spin excitation. So this excitation spectra suggests that in behind, we have this fractionalization. And actually, the emergence of fractionalized particle is important because such fractionalized particle might have different quantum entanglement property from the usual particle. Then it might be useful for the quantum computing. Okay, to summarize this part, so far, most of the neural network study are focused on the benchmark study. But in this study, actually, we go beyond such benchmark, and we try to understand the physics of this J1, J2 model. Then actually, we indeed find a very interesting physics in this J1, J2 model. Okay, so to summarize, as I already said, the neural network wave function are now extended to various systems. Of course, we need to continue the development of the method, but now we start to understand that the neural network wave function is powerful. So I think it would be interesting to apply the neural network wave function to study the challenging problem in physics. And also, we note that this kind of extension is done at zero temperature calculations. And maybe in the next talk by Nobu, actually we he will introduce the extension to the finite temperature simulations. So with that, I'd like to thank all of you for your kind attention, and I'm happy to take questions.
Well, thank you very much for a very nice talk. And then we're a bit tight of time, but if there is a question that somebody would like to raise your hand, and then or send it via the chat.
Franco, I have a question. This is Enrico.
Okay, go ahead.
So my question is, what, how big of a system can you do, and can you go beyond 2-dimension lattices, for example?
Yeah, for example, I'm not involved, but the group of Giuseppe apply the neural network wave function, the three-dimensional pyrochloride spin systems. And the maximum number of spins is several hundred to 1,000.
Okay.
So in the case of three-dimensional case, of course, we have the limitation in the linear system size, but still we can simulate a few hundred, at least few hundreds of spins within this method.
And what about bosonic variables?
Bosonic variable, you mean in the general boson case where the occupation number can be infinite? Yeah, in this case, yeah, using kind of Ising bit, for example, in this RBM, if we take 3 spins, then we can represent the occupation from 0 to 7, right?
Yes.
So the maximum number grows exponentially with respect to this spin system. So in principle, we can we can also apply to bosonic system.
Okay. Yeah, you should stick around for my talk tomorrow.
Yeah. Looking forward to your talk. Yes, thanks.
Okay, well, great. Thanks the speaker for a great talk. So right now is 4:18, so it's time to go to the next.
Thank you very much.
Oh, for the next speaker. Next speaker is Dr. Nobuyuki Yoshioka at the University of Tokyo, and the title is Advancing Classical and Quantum Variational Algorithms for Many-Body Problems. Please go ahead.
Yeah, thank you. Okay, thank you, Franco, for introducing. I'm Nobuyuki Yoshioka, and we would like to talk on both variational algorithms run on classical and quantum devices. Okay, so for the classical algorithms, I list up my collaborators in this slide. And for the classical algorithms, the work is done in collaboration with Wataru Mizukami and Yusuke, who was presenting in the last slot, and also Franco, who is now chairing the session. And for the second part, it is in collaboration with Suguru Endo, Hideaki Hakoshima, Yuichiro Matsuzaki, Yuki Tokunaga, and Yasunari Suzuki. Okay, so when we want to say we want to solve quantum many-body problems, what we usually have in our mind is some interesting materials or some phenomena that we want to look in depth with, but is prohibited by some, let's say, the impurity in the material or something like that. So what we want to do is to extract the essence of this exotic phenomena into some model that would hopefully describe the system and numerically or theoretically investigate it into this Hamiltonian or some modelizing or anything. The best thing, or ideally, we can extract this model in ab initio way and run exact simulation. But as we know that this is not a very tractable way, and in both classical or quantum devices, which we have right now. So obviously in classical simulators, this would require exponential scaling. And also in quantum devices, for example, in quantum simulators, the realizable models are still limited. And even though if we can resort to quantum computing, such as the phase estimation or something, then it would require full implementation of fault tolerance, which would not be realized in the coming, let's say, 1 or 2 years. It's going to take 10 or 20 or more decades. So the alternative is to consider some variational calculation, which would encode the information of quantum state into some ansatz, meaning that we would run simulation of this parameterization instead of the full Hilbert space. And hopefully, if this ansatz captures the physics enough, then we would end up running simulations using only polynomial number of parameters, which is considered to, in usual sense, to be tractable by the classical simulations. I mean, it can be like n to the power of tens or tens, but hopefully, in many cases, we would construct algorithms that would scale in lower powers of qubit numbers or electronic numbers. Okay. So the questions we need to ask is, what are the common roadblocks to run these variational methods? One of the most important thing is to find good variational ansatz to simulate the physics or quantum many-body phenomena. We need to keep asking if the ansatz captures the involved Hilbert space in the system, or is there any figure of merit that describes the representability of the state. Another thing we need to ask is how to update these variational parameters that is present in the system. So we have to ask, is there any variation principle for the starting phenomena, and how to compute according to this variational principle, or so on. The third roadblock, and so this optimization itself is not very big problem in classical simulations, but can be big problem people have found out that it can be a big roadblock in quantum simulations or quantum devices. And another common roadblock that is unique to quantum devices is the presence of the hardware noise, meaning that even each bitwise operations would be under some unwanted noise, such that we cannot realize the actual quantum operations we want to consider. So in this talk, I would consider the first point, how to looking for good ansatz for the classical simulations, and how to deal with this hardware noise without implementing the error corrections for quantum devices. Okay, so let's go further into the classical variational methods. So as Yusuke has already introduced in his talk, people have already considered some quantum wave function ansatz. For example, the Jastrow factor or Geminov product, which has been proved to be very good to describe the physical phenomena in Lattice-Hubbard model. So these factors are heavily used in simulation for condensed matter physics, because in condensed matter physics, people are obsessed with simulating Lattice-Hubbard models, and it's not only because it's Hubbard, simply we are obsessed. We know that this model encompasses a very rich exotic phenomena. For example, people have simulated the ground state of 2D square model, Fermi-Hubbard model, using combination of this Jastrow factor, a Geminov product, and also Gutzwiller factors, and have shown that we can actually numerically find out that the D-wave type of unconventional superconducting correlations are present in this model. Okay. On the other hand, beyond these condensed matter inclined model, for example, the quantum chemists have also employed this type of ansatz. And there are some works that show these kind of ansatz are not good enough to look into the electronic correlations in ab initio calculation for molecules or solid systems or so on. Another representative of quantum ansatz is the tensor network, which are now heavily used in simulations for quantum spin lattice models. For example, for 1D systems, people are now mainly using ansatz named matrix product states that is mainly designed to capture the weakly entangled quantum state. And also there are some generalizations into higher dimensions named project entangled pair states or PEPs to simulate ground state or real-time dynamics or finite temperature studies or so on. Okay, but the problem here is that we know that tensor network, the mainly used type of tensor networks are very good at like 1D ground state or maybe 2D, but it is inclined to capture weakly entangled system. And people are now getting interested in using neural network as variational methods because it is not, there's pros and cons. We do not know what is the figure of merit corresponding to neural network ansatz, but on the other hand, it may give us possibility to simulate, to do some simulations without explicitly encoding physical knowledge of ourselves. For example, the paper by Carlillo and Troyer showed that even the simplest structure of neural network, or namely the restricted Boltzmann machine, would be can successfully capture the ground state structure of lattice quantum spin models. So here they are comparing the energy with the exact value in a model where we can actually run the classical simulations up to very large size. In other words, they have done some demonstrations in model where we can run the path integral Monte Carlo or QMC. And they have shown that for a 1D with periodic boundary conditions, they can systematically improve the simulation accuracy by adding up more and more hidden neurons or making the neural network structures richer and richer. And they have shown that not only in 1D, but also in 2D, and have seen that the best known energy accuracy by the tensor network in 2D can be outperformed using the RBM neural networks. So this has been very much encouraging result for variational simulation researchers, and people have also applied this to, for example, fermionic models with Hubbard models. So here in the work by Yusuke, they have shown that the combination between RBMs in the Gemini product, which I introduced in the previous slide, would allow us to go beyond the best variational methods, which is only restricted to condensed matter knowledges. Okay, so as Yusuke has mentioned, people have done a lots of demonstrations and benchmarks on abstract models. And now I believe that we are in a stage where we can go beyond this. We can further proceed towards the grand challenge of simulating real materials under realistic environments. So there are some works, for example, in isolating lattice model, considering the ground state or quench dynamics. But what we want to do is to, for example, let's simulate real solids, the ground state structure of real solids, or more quantum spin models or fermionic models under realistic environments, which are under finite temperature effects or dissipations or so forth. So here I would like to introduce our work on real solids in finite temperature programs. Okay. So we were looking whether these neural network type variational ansatz is suited to describe the ground state property in solid systems. As an example, we have done all simulations involve 1, 2, and 3D, but let's start with 1D systems. So here we have a hydrogen chain, which is separated by by distance dh. So this model, bunch of hydrogen atoms, are showing metallic behavior which corresponds to weak electronic correlations in the hydrogen atoms in dH corresponding to 1 and 2 and so on. But if we separate these dH more and more, it would correspond to strong U region in Hubbard model language. And then we observe that these orange lines corresponding to the golden standard methods of quantum chemistry would start to deviate from the exact diagonalization simulation and even yield lower energy compared to the possible energy. So these yellow lines and black lines here are corresponding to the methods named coupled cluster theory used in quantum chemistry. And we see that in this regime, these orange and black lines are very close to the exact red lines, but start to yield unphysical result if we separate this dH more and more. On the other hand, the simulation denoted by this green triangle or the neural network ansatz would stick along this red line, which shows that this neural network ansatz would be able to capture both weak and strong correlations in any regime. So there is some criteria in quantum chemistry named chemical accuracy. And this chemical accuracy is the absolute difference between the exact diagonalization and the calculation result. And this chemical accuracy, 1.6 millihartry, is considered to be precise enough to predict chemical reactions or any material properties up in quantitative level. So we have seen that in this 1D system, a neural network states are precise enough to produce the chemical accurate reactions that is happening by stretching and these atomic distances. So we have done these simulations not only in 1D, but also in 2D and 3D, and confirmed that in any cases, we can simulate the ground state property up to chemical accuracy as well. But not only the ground state energy, we have also simulated the bound structure from excited state simulations. So this excited state simulation is different from what Yusuke was mentioning in his talk, in a sense that we are calculating the excited state within the identical symmetry sector right now. So let's say, and for example, we can see that we are now calculating 6 excited state in the identical symmetry sector and have seen that, for example, this first valence band can be simulated within chemical accuracy again. The other bands beyond this valence bond or beyond a Fermi surface is slightly worse than this band, but we have confirmed that this can be improved systematically by increasing the excitation state calculation method. Okay. So for real solids, we have confirmed that neural networks are working very well. And now let us proceed to simulating the finite temperature problems. Here, what we do is to encode the Gibbs state of some given quantum Hamiltonian into the neural networks. here we use the idea of purification. And the parameters within these neural network states are optimized in a sense, via the variational principle that describes the imaginary time evolution. And what we wanted to see is to demonstrate that our neural network ansatz is not only capable of ground state, but also finite state, capable of finite temperature system in one of the most challenging 2D frustrated systems. Okay, so what I mean by purification is the following. So in addition to the physical spins or physical degrees of freedom that actually exist in your system, we would add some ancillary degrees of freedom and extend the Hilbert space. And within this extended Hilbert space, we would define some neural network ansatz so that after tracing out this ancillary degrees of freedom, we would obtain a density matrix that would describe the quantum state you want to know about. So this is the idea of purification. So what we do is to, and furthermore, what we want to do is to construct a method or some protocol that updates the parameters in this neural network so that this quantum state rho obtained from purification would describe the Gibbs state of the target Hamiltonian. We would do that in the following steps. First, we would prepare an infinite temperature state by generating a maximally entangled state between each physical degrees of freedom and ancillary degrees of freedom. So let's say for each qubit, we would attach another qubit and consider some Bell pairs between them. If we trace out one of the qubit, then what we would have is a maximally entangled state. And that is what we want to consider here. Luckily, it is very easy to show that this kind of Bell pair can be represented very compactly using neural networks. In our case, we are using the deep Boltzmann machine structure right now. And once we have this infinite temperature state, then we would consider, we would employ some variational principle so that the parameters of this neural network would be updated to follow imaginary time evolution of the system. So here, to be precise, we propose two methods that would construct exact representation of the Gibbs state and another within approximation. And this method number one I show here is very in parallel to what Yusuke has explained in his talk, and it was correspond to constructing some DBM so that the DBM would correspond to each charter steps. Okay, so for that one, I would skip and let me go into the variational one. So here, what we would do is to employ an update rule named stochastic reconfiguration. The stochastic reconfiguration is a rule that determines how we should update the network parameter. And this tells us that in order to minimize the Fubini study metric between the actual imaginary time evolution and approximate one given by updating this the parameter as delta W, we shall update the network parameter in this way, meaning that this small change of parameter can be given by product between the quantum Fisher matrix, inverse of quantum Fisher matrix, and the generalized force, which basically corresponds to the derivative with respect to the energy. And each of these terms are estimated using Monte Carlo sampling. By devising this approximate imaginary time evolution, we have shown in the 2D J1, J2 Heisenberg model, which was also studied for the ground state in Yusuke's talk, that the neural networks can capture the physical quantities in any temperature regime. So here, our simulation is done on 6x6 lattice with the total spin restricted to 0 sector. And for all energy, the specific heat, and also the spin correlations, we confirmed that from the TPQ calculations, which is close to Lanczos method with some stochasticity within it, that the points given which corresponds to neural network are in very good accordance with this nearly exact method. And as a scaling, we observe that the computational costs for this neural network variational simulation would scale as the following, with meaning, so here the n of h means the number of hidden spins, and n represents the actual number of spin sites, or the number of qubits here. So here we have demonstrated that the calculation based on neural networks can be used not only for ground states, but also for finite temperature problems in one of the most challenging regimes. Okay, so now we are going beyond the ground state simulations or some simple benchmark systems. But let me ask, what would have to be done next for this neural network variational calculation? One is, of course, to proceed doing the real application in condensed matter physics or so on. But I would like to cast a question whether using deep neural network is really good for this kind of simulations. Meaning that in ordinary machine learning, people knows that by making the network deeper and deeper, we would end up having tons of local minima. And it is fine in machine learning where the generalization is important, because compared to the actual global minima, these local minima would perform better in terms of predicting the generalized property of the problem. But on the other hand, in variational calculations, what we actually want is a global minima. So it could be possible that actually using very shallow and wide networks are more favorable in terms of these kind of calculations. And another related question is there any way to find out what is actual figure merit corresponding to the representability of neural networks? At least we know that it is not restricted by entanglement entropy, as in the tensor network, but we actually have no clue what would be the figure of merit for these networks. Okay. All right, so that is a short summary for classical algorithms. And let me proceed to running variational algorithms on quantum devices now. Okay, and when I say variational algorithms in quantum devices, I would have the quantum classical hybrid algorithms in my mind. So for example, we would consider VQE or QAOA or such kind of problems. And the roadblocks for these kind of quantum algorithms are also in common with what I have shown in the beginning of my slide. So we need to ask what kind of answer structure would be feasible to capture the involved Hilbert space. Is the optimization really possible? But here I would like to focus on the third point of concerning the hardware noise present in quantum devices. And by meaning getting over the problem of hardware noise, I mean that what would be the good strategy to mitigate the effect of quantum the hardware noise on the system? So in other ways, what would be nice error mitigation algorithms to implement for these variational calculations? So here I classify these error mitigation techniques into two types, naming error-aware mitigation and error-agnostic mitigation. And error-aware mitigation simply means that we assume that we already have the full noise property in the quantum system. Let's say we are operating some unitary operator U, and we know that there is some Krauss map corresponding that describe the noise epsilon as this. Let's say we know that in a quantum device we have, there is depolarizing noise present. For one qubit system, it would look like this. And in this error-aware mitigation technique named probabilistic error cancellation, they would consider constructing the inverse map of each noise map via quasi-probability sampling. And of course, this is very powerful because we assume that we have full knowledge of the noise, but the weak point of this method is that it requires to perform the full gate state tomography with perfect accuracy. So obviously this is the cost for this scales exponentially and is not very scalable. Also, if we are mistaken, we have mistaken information about noise, then we would not be able to mitigate the effect of error and sometimes end up boosting the effect of errors, which is not really not what we want. On the other hand, there's some error agnostic mitigation technique, for example, subspace expansion, virtual distillation, or error extrapolations. I would mention what these techniques are in the later slides, but let me briefly summarize that all these techniques has pros and cons. For example, the first quantum subspace expansion methods are very good at eliminating or mitigating coherent errors, but not for stochastic errors, for example, depolarizing or those stuffs. The second method, virtual distillations, are very good at eliminating stochastic errors on the other hand, but it is very prone to coherent errors. And extrapolation methods can handle quite well with both of them, but to start with, it is not yielding physically condition. So it may end up yielding some irrelevant values or something. So what we wanted to do here is to propose a new method which corresponds to the generalization of the subspace expansion so that all these drawbacks can be remedied. Okay. So let me proceed to the framework of our proposal, the generalized subspace expansion. To do that, let me start with the ordinary quantum subspace expansion technique. What we do here is to expand the representability of the quantum circuit via post-processing. So let's say we have a quantum circuit that is parameterized, and here I show a pictorial illustration that we can prepare some quantum state corresponding to this parabola. the aim of quantum subspace expand is to expand the representability of the quantum circuit by considering some terms like some general act that can be expanded by acting operators pi on the prepared state. So, and actually what we do is not to actually operate these terms on the quantum circuit, but to realize this state effectively such that all the physical quantities can be simulated using post-processing. So expression of this effective ansatz is identically given as this if we move into density matrix language like this. So let's say that using this effective ansatz that would expand the representability, we want to simulate the ground state of Hamiltonian better than what is achievable on the quantum circuit. What we do is to optimize these coefficients alphas such that the expectation values given by this effective ansatz would be minimized. So we can, of course, do some optimization in a usual like gradient way, but we can find out that this alpha can be optimized by solving the following generalized eigenvalue problem. Each matrix elements of this newly generated truncated Hamiltonian, and the metric S is given by these terms. Why with this PIs corresponding to the operators that is intended to expand the representability of the system. So if we can measure these matrix elements on quantum circuits, then we can consider this generalized eigenvalue problem, and then we can enhance the simulation accuracy by the quantum devices. So the point is, what kind of operators PIs can be measured efficiently on quantum circuits? And people have considered using, for example, simple Pauli operators or Clifford operators, and have seen that the accuracy can be improved not only theoretically but also experimentally as well. So here in this paper by Collis et al., they were performing ground state simulations for 2 qubits as a demonstration, and showed that this purple line given by raw measurement results by quantum devices can be improved up to 2 orders using this quantum subspace expansion technique. Okay, but as I have mentioned, this is very good at, we know that this is very good at eliminating coherent errors, but not for stochastic errors. Let's say that, for example, let's say we have coherent errors and that the realized quantum state is drifted into this form with unitary, with delta corresponding to some noise level. To eliminate this effect by this noise, we need to construct a projector P such that this P would correspond to the inverse map of this unitary operations, which should be very close to identity. So the dominant contribution is also close to identity, from which we can see that the measurement cost or additional cost for the post-processing is very much related with the noise level itself. On the other hand, when we have stochastic errors, for example, we would have this kind of situations where the quantum state rho GS would be mapped into this form, where this rho PERT, of course, would be some orthogonal state in terms of this trace. Okay, in this case, we can see that we shall construct a projector which entirely does not depend on the error rate. In any cases, for this subspace expansion method, we need to construct some projector P that would entirely correspond to the exact ground state, meaning that this projection operation does not depend on noise level itself. So this shows a qualitative difficulty compared to the coherent errors. Okay, so the key question is, can we extend or generalize this subspace expansion to include more excitation operators PIs to eliminate the stochastic errors? And we have shown that by considering this type of projectors PIs can be implemented efficiently on quantum circuits and also be able to eliminate the stochastic errors and coherent errors and so forth. Okay, so this type of PI I show here is a very generic form, but here what I want to show is a subclass of this generalized subspace expansion. So here we would proceed to employ some concrete type of excitation operators and see that coherent errors are indeed suppressed using our technique. As a subroutine, we use the technique named, which introduced in the previous slide, named the virtual distillation. So the idea of this virtual distillation is very simple, and it is to realize the power with respect to the given noisy quantum state role. Let's say we have a quantum state role which can be diagonalized in this form. If we can realize power of state as rho of n, then what we would see is that the subdominant contribution to this noisy state would decrease exponentially with respect to the power n here. We can show that this kind of operations can be realized using, for example, entangled measurement between copies or extension of swap test. And the nice point of this routine virtual distillation is that we can, of course, we can exponentially suppress the effect of errors, but on the contrary, there would be some exponential sampling overhead that roots from the denominator trace rho n. And also, since this is simply extracting the dominant contribution of the quantum state, it has no ability to mitigate the coherent error at all. Okay, so what we want to do is to suppress the number of this power n and also increase the ability to mitigate the coherent error. We have shown that by simply considering the power series of this rho m, we can deal with both coherent and stochastic errors. Oh, okay, so let's say we have some ground state under some noisy quantum circuit, and this x-axis is corresponding to the number of the copies or the power of rho n. So this m equals 1 here corresponds to the energy given by the noisy state. We can see that by increasing the power, that energy error can be decreased exponentially, both in our generalized subspace expansion technique and this virtual distillation. And since our subspace expansion is kind of extending the Hilbert space, we can assure that the result coming from subspace expansion is formally strictly always better than the virtual distillation. We can also improve the result by allowing further subspace, which can be product between the power states and the Hamiltonian itself. So this would correspond to the combination of virtual distillation and the Lange's method or something like that. Okay, as time is running out, I would also mention that from this figure right here, we can see that this blue plots given by the virtual distillation would be bounded by the actual simulation accuracy of the VQE. But using our method, we can go beyond this bound and eliminate the effect of the coherent errors. Okay, so that was one subclass of our subspace expansion. And let me proceed to another subclass, which is kind of generalization of the error extrapolation. So error extrapolation would consider is simply extrapolating the observable into zero noise limit. So let's say you can change the value of the errors so that you can have the value of physical quantities in different error rates. What we would do is to extrapolate, maybe using exponential functions or polynomial functions to estimate the value on when the error is not present at all. But the weak point of this method is that if we have mistaken knowledge about the error, then this extrapolation itself would not work enough. And let's say there's some Gaussian errors in the knowledge of this error, then we can see that the final result would fluctuate and even go below the actual ground state energy. Okay. What we proposed is not affected by such type of fluctuations in error, and can actually we can actually show that by constructing subspace, we can always assure that the result from this our method would always follow the physical constraint.
Sorry, okay. No, we need to finish soon.
Right. Okay. Yeah, thank you. So yeah. So we were proposing two subclass of our algorithms, and would like to finish my talk here and start to take questions.
Oh, thank you very, very much for a very nice talk. And then if you want to go through the summary, you can do it, no?
Oh, no, it's okay. I mean, I can just show this summary here. Yeah. And I see that.
Okay, so therefore there is one question in the chat. It's how do you suggest to treat the case of large D sub H where it breaks down? So I think it's referring to the 1D hydrogen chain, because when the large DH grows, there is a breakdown of other methods, but in the case of the neural network one, there is no breakdown. It works pretty well, actually.
Right.
Exactly. Yeah. So therefore, the green dots, the green triangles, indicate that the restricted Boltzmann machine works pretty well, because it compares well with the exact diagonalization. So.
Right. Yeah. Okay. So the question was.
No, I already answered the question. Essentially, if you look at DH, when DH grows, how do you suggest to treat the case of large DH where it breaks down? But in the case of restricted Boltzmann machine, it doesn't break down. What breaks down are the older models, the traditional models.
Oh, okay. Yeah. So as Franco said, so this is a benchmark test in where exact diagonalizations are available. And we were comparing with methods that would break down in this regime. Yeah, right. Thanks.
This is a question where I knew the answer. Okay, any more questions? You can raise your hand and then use the microphone or use the chat. Also, we're going to have soon like a coffee break or tea break. So therefore, you're welcome to send a message or a question to the chat to either one, I mean, to the previous speakers, and then they could reply via the chat, or you could just continue afterwards via email. So therefore, if there are no more announcements from Ming, who's then we can start at 5:30 p.m. Japan time. The talk by Jens Eisert, somebody asked the question when the talk starts, will be 5:30 Japan time, on rigorous approaches to quantum-assisted machine learning. And afterwards, there will be several contributor talks. So any additional comments from Ming?
No, everything is fine. So we take a break and we be back in 20 minutes.
Okay, well, thank to both speakers for the great talks, and thanks everybody for being here. The sessions were very well attended, and that was great.
Thank you, Nobuyuki and Yusuke, for the great talks, and thank you, Franco, for chairing the session.
Oh, thank
you.
you.
Thank you. Let's have a coffee break.
Thank you very much.
Break.
Okay. Bye-bye. Okay. So I'm going to close this here.
No, let's try the latest.
Hi, Jens.
Hello. Hi.
Can you hear me well?
The most spoken sentence of the year.
Okay, okay.
Can you see my slides? Yes?
Yes, I can see very well.
Hear you and I
it looks
can see you
perfect.
and I
It looks
can
perfect. Yes.
even see my own slides.
Yes, it looks perfect.
Good. Yeah, I've been listening to most of the program today already, although the beginning was difficult.
Right. It was actually pretty early in the morning for you.
Yeah,
even now
fiercely
it's still early, I think.
No, now it's like 9 something.
Okay, okay. Yeah, for the industry session, it was actually quite early. So I'm actually very impressed that everybody actually showed up. It was amazing.
Hello, Jens. Nice seeing you, Jens.
Hi. Wonderful. Yeah, the pleasure's on my side. Thanks for the invitation.
It was great having you here.
Good. Yeah, it's been a fun program so far. I really like it. It's great.
How do you pronounce your name? Is it Jens or is it Jens? Jens.
It's funny that you say that because when we picked a name for my daughter, we thought it should be like Starbucks compatible. Because when I go to Starbucks and you write your name on the cup,
yes.
I have like a wide range of names like Jens, Jans, Jeans, Jens. So I listen to a wide range of variations thereof.
So the correct one is Jens.
The correct that's right. The correct one is Jens.
Okay, good.
That was
good to know.
I don't know. I can't be offended in this way. So
yeah, but people in Germany will know how to pronounce it, no? Even in Starbucks.
Yeah, no, in Germany, yes. I mean, I'm half Swedish, half German, so it's kind of a Danish name. That's kind of the average.
Oh,
between and Germany. But yeah, of course, it's also a common name in Germany, so they would know. But it's not internationally. It's apparently not so common. So yeah, it is what it is. Now it's too late to change, I guess.
So we are waiting for your session chair. Ihui? No.
Oh. Yes.
How do you pronounce your name?
Ihui.
Ihui. Okay.
Ihui.
Nice to meet you, Ihui.
It gets worse. We have like two bad names. It gets worse. There's I mean, the next speaker also has a difficult name.
Well, we are all from like everywhere in the world, so it's fun actually. It's a fun exercise.
Yeah. Wow. I mean, yours is not that easy either, for that matter.
Well, mine is easy. Mine just Ming, so it's easy. Just call me Ming. It's easy.
That's fine.
Actually, but Ming is a very easy name to pronounce. I mean, like it's a very easy Vietnamese name to pronounce because actually there are a lot of Vietnamese names which are not so easy, I think, for foreigners to pronounce. But Ming is actually, I think, one of the easiest Vietnamese names to pronounce.
Oh,
so
right.
we have, I think we have all the speakers here, right? We have you, and then we have, I think it's Ellie. No, Elias.
See, I told you, Elias.
Elias.
Ellie. Okay, sorry, Ellie.
No, perfect.
Oh no, have I been pronouncing your name wrong all this time, Elliot?
It's fine.
Let's have speaker 1, 2, and 3, okay?
Yeah.
Okay, so say your name again, please.
Elias.
Elie.
With an S at the end. Elias.
Yeah. Elias.
Yep.
And then Matthias. And then Matthias.
Yep, that's right.
And the last one is, who's the last one? I forgot.
Julian, yeah, that's good. I also go through, it's French, so I also go to a wide variety of Starbucks names. But
Julian Gacon? No.
Yes,
Julian
no, that's pretty good, yeah. Gacon. It's like a K. Yeah.
Perfect.
Yeah, we should be more Starbucks compatible, but never mind.
So I think we should start pretty soon. Like we should start in 1 minute. Yeah.
Yeah, that sounds good.
Yeah.
Good, I'm all set.
Yeah, perfect timing.
Okay, then Welcome to QTML session. Oh, okay. Welcome to QTML session 4.4. We are delighted to have with us Professor Jens Eisert, who will give the invited talk. So, yeah, it's your turn, Jens.
Yeah, thanks so much. Indeed, thanks for this overly kind invitation and introduction. Thanks for pronouncing my name properly. And thanks to the organizers for all the efforts of setting up QTML. I've been enjoying it tremendously so far, even though the program has been pretty early in the morning hours, even by my standards for that matter. So there have been lots of exciting and cool talks so far at this big meeting on quantum machine learning, a field that's moving a lot into the focus of attention. And this makes perfect sense, as notions of machine learning could indeed be tasks where quantum computers, even comparably early, like warm and noisy ones for that matter, could give rise to advantages in sample complexity, in the computational effort or generalization, you name it. And this is why we're here this week. And indeed, this field has been creating a lot of interest, mostly for good reasons, I'm tempted to say. And there's lots of evidence that provides fuel to be excited about in this field. And yet, it may be a good moment to pause a bit, to hesitate, to reflect what could be really in store in quantum-assisted machine learning at the end of the day, and ask what can be said in rigorous terms about notions of quantum learning away from showing plots and pure heuristics. This is made complicated, of course, by the fact that even in classical machine learning, lots of insights have been established more on the heuristical level, which renders the analog in the quantum world quite challenging. And yet, in this talk, we will be trying precisely that when we have a look at what could be called a rigorous approach to quantum machine learning. That said, it will not be a comprehensive talk, I wish, but it will provide 3 serious steps, baby steps if you want, into this direction. But I would like to insist that this is really a healthy and rather worthwhile approach to looking at the field, a vision that I share with these wonderful people here, including the chairwoman for that matter, here with this is joint work. And I would like to give Ryan, Marcel, and Matthias specific credit here. And it also has a lot to do with practical implementations as well. But let's start at the very beginning of all this. So there can be little denying that machine learning has changed the world we live in. It's ubiquitous in any process involving pattern, image, or handwriting recognition. Say any postal service or your mobile phone's features heavily rely on this. Now, most talks on machine learning, and this is not an exception, if they refer to tasks of classification, would early on show some pictures of some handwriting, paintings, or even of pictures of animals such as cats, dogs, or horses. Even though, as a side remark, there are sometimes surprises in that when you ask what a machine is actually learning when it sees horses, it turns out that this is actually the copyright logo that is legally required for pictures of horses, as my colleague Klaus Robert Möller points out, but never mind. Or we can think of tasks such as playing games such as chess or Go. Either way, the overwhelming success of machine learning is beyond any doubt, it seems quite fair to say. Now, roughly speaking, most, if not almost all tasks can be crudely categorized into one of the following 3 settings. The first one is supervised learning, where one would formulate the learning task based on labeled data. So here the learner gets loads of data, say in the form of images together with a bit of information, whether the picture shows a cat or a dog or a horse. And then the task is to classify pictures of cats, dogs, or horses on unseen data. So we get prior information about what pictures show cats and what dogs and what horses. In unsupervised learning, the learner would get unlabeled data. Say this learner would get loads of images of cats and is supposed to create new images of cats. So reinforcement learning is slightly off in that it takes a more like game-like strategic note in that one thinks of an agent interacting with some environment aimed at maximizing a future expected reward. Interestingly, either way, all those tasks can be ultimately be cast into the form of a distribution learning problem where the task is to learn an unknown probability distribution from data, a point we come back to in a minute in the context of unsupervised learning later in the talk. Now, of course, the heart of the matter for this conference is that recent years have seen a growing evidence that quantum computers may offer advantages in learning tasks, in basically either of the above readings. So for now, these are primarily parameterized quantum circuits with some knobs and trainable gates in some lab, say of a superconducting circuit type, or maybe soon also in the optical realm, as shown on the right-hand side. Now, this is great, but how precisely? I mean, can we identify a setting in which this is provably true? And this will be the guiding question for the rest of the talk. We will ask, can we sit down and prove a quantum advantage of quantum computers in distribution learning? And then, very briefly and specific to concrete hands-on models, and as a teaser for the next talk by Elias, can we formulate and prove encoding-aware generalization bounds for quantum machine learning? And in the end, can output distributions of quantum circuits be actually learned? And so is there kind of some kind of self-learning? So can quantum computers learn the outputs of other quantum computers if you want? This will be the theme, the guiding questions for the rest of the talk. Which brings me to the...
Just to interrupt, the meta question, do you want to take questions during your talk or after the talk?
Let's have the questions at the end of the talk.
Okay, good.
So, which brings me to the first part of the talk, in which we ask whether there's a kind of a proven quantum advantage in Pak distribution learning, which makes a lot of sense when thinking how many learning tasks can be seen as distribution learning tasks, as hinted at earlier. So let's dig a little bit deeper what this all really means and what we mean by all this. So basically, we want to compare how well classical and quantum learners or algorithms fare in notions of unsupervised learning. So specifically in distribution learning, we have some generator of a distribution D. And that generator is in one way or the other an algorithm that uses, there's a bit of a technical problem here, never mind, that has access to classical randomness. So this generator can call a dice, get some X, the random X, and spits out some sample from the distribution based on that X. We will call this Gen DX. So this could be images of the type mentioned earlier. So these images, or these guys are fed into the learner. We do this actually many times. So for the given distribution D, we feed many samples to the learner. And then we can think of very many natural readings of learning of that distribution. The first one would be density learning or density modeling. So here the task of the learner is to really learn the description of the probability distribution itself, and that it obtains samples from the generator. So it would really kind of model or evaluate the probabilities at the end of the day, and we come back to later in the talk. Another meaningful task is to output a new generator. So given samples from the generator, the task is to basically output a description of that generator, at least to a good approximation. So for most of what follows, we will have a look at this task. So the task is, given samples from a generator, learn a generator of that distribution, at least to a good approximation that's basically largely indistinguishable. And so that's the task, learn a generator gen D of a distribution. And specifically, we ask the key question that's kind of related to our guiding question throughout our talk is whether there can be a quantum advantage in the sense that there are distributions that are not efficiently classically generator learnable, but which at the same time are efficiently quantum generator learnable. Now, this task still comes in various fine prints and readings. And I recommend this beautiful review article below concerning these fine prints. There's different settings of learning, such as exact, PAC, or agnostic learning. There are different queries to the oracles. And in particular, sample oracles that would take the raw plain vanilla data from the machine, from the experiment, or statistical query oracles that we come back to later, or we can think of like quantum oracles that would generate superpositions and so on, but we will not really go there in this time. Then we can think of different figures of merit for having an advantage. So think in terms of sample complexity, we can think of query complexity or computational complexity, meaning the computational effort it takes to perform the learning. And all of that could lead to speedups of various types of the quantum over the classical setting. And indeed, the study of quantum computational advantages is basically almost as old as the field of quantum computing itself. It's kind of funny to see that the early papers, even from 95 or something, like around the same time as Shor's paper, it's like really literally as old as the field of quantum computing. Okay, so what we consider are classes of distributions. So subsets of distributions over our sample space. Let's be a bit more concrete here. So what distributions do we expect the learners to work? So surely there's some sample space omega n. So we think of binary strings there, and we have some distribution over that sample space. Now we assume that we can actually efficiently create instances of these distributions. So this must be possible, that to kind of spit out samples from that distribution, say in unit notation, to efficiently prepare instances. So as we scale up our problem, it must be possible to efficiently create instances from these distributions, so generate distributions from this concept class in this jargon. And that's of course important because we are going to compare quantum and classical settings. So the scaling of the effort in n, like in the system size, if you want, is the key here. So again, we're considering classes of distributions, and we are asked, can quantum learners fare better than classical learners? Now, having specified the distribution concept classes, we have to ask how we want to learn it. And there's a wealth of settings, again, in all the way we feed in the data, the oracle access, and so on, as we have said. Now, for what we have in mind in this first part, we will stick to the sample oracle, where again we are just presented classical data, not in a superposition or so, but really the classically describable, basically raw data from the experiment, and the output is a classical sample from that distribution. Now, before we come to the heart of the matter, which is there a quantum generator learning advantage? Some additional fine print is needed, but that's the last fine print, and then we come to the heart of the matter. So then we are through. So here's the fine print. That's this notion of probably approximately correct or PAC learning of distribution classes, because at the end of the day, the new generator will not be perfect and doesn't have to be. So a setting in which this can be nicely and mathematically precisely phrased is that of probably approximately correct or PAC learning, where a distribution class is efficiently PAC learnable with respect to some distance, for example, the Kullback-Leibler or the relative entropy distance, if there's an algorithm A for which every distribution in the concept class and every epsilon and delta given access to an oracle, which here's the sample oracle, outputs with probability at least 1 minus delta, so probably a generator of a new distribution D prime that's close to the original distribution, so that D and D prime are close. This is PAC learning. So again, we have a learning algorithm. So we have a learner, and that algorithm can query samples from some efficient classical generator. And this generator has access to some classical randomness. That's the kind of the dice coming in, and outputs samples depending on this this randomness coming in. And we repeat this many times. And the question is whether the algorithm is efficient in outputting a generator of a distribution that is practically indistinguishable from D in the sense as mentioned here. So again, can we efficiently PAC learn? And what we mean by time complexity is like polynomial in the input size, of course, but also in 1 over epsilon and 1 over delta in this, which are the error parameters in the definition of PAC learning. Okay, so that's our lengthy preparation. So the question is there a quantum generator learning advantage? So more precisely, is there a class of discrete distributions which is not efficiently classical PAC generator learnable, but is efficiently quantum PAC generator learnable with respect to the relative entropy divergence and the plain vanilla sample oracle? This is the make or break question here. And the answer is very simple. It is yes, indeed. There is, under a mild complexity theoretic assumption. So this is wonderful. So there is, this may be a bit of an abstract, but a somewhat proof of principle statement with a fine-tuned distribution class, but there is a proven exponential separation between quantum and classical learning. So this is to be appreciated. One has a classically generated distribution, no superposition, no QRAM, no funny encoding, or so, no cheating, but efficiently preparable data and a separation between quantum and classical learning in an exponential fashion in terms of sample complexity, computation complexity. So there's no time to go deeply into the proof of this theorem, but I will present some hints at this to see where this is going, because I want to stay in time to leave time for questions. So on the highest level, there's 2 things we need to show. First, clearly, we have to show it's classically hard, so we need to construct some distribution concept class for which we can show, on the one hand, that the classical hardness of learning, and on the other hand, quantum easiness. So we start with the classical hardness, and here we can resort to we sit on the shoulders of giants and resort to a literature in classical learning theory, and then comes the quantum part. So much of the heavy lifting goes back to seminal work of Kearns that basically shows that there are distributions that are hard to learn classically. That's, of course, what we need, and the basis of this idea is that of so-called pseudo-randomness. So this is a concept that actually constitutes the basis of many crypto schemes, and our friend Jean-Pierre Seifert was very helpful here. And the flavor in which we need pseudo-randomness is that of a so-called pseudo-random function. So what's this? This is actually not a function, but rather a collection of functions, and which is like teeny weeny. It's tiny compared to the set of all functions. And on the right, we have all functions from the domain D to the codomain D prime. So what does it mean to be pseudo-random? Say if one draws uniformly from that tiny set of keyed functions, basically drawing a random label K, and now I give the imagined distinguishing algorithm membership oracle access to this FK. So this algorithm can query FK, and it gets results, and it can process those results. And then the task is to distinguish such a function from the uniform random function. So it would output 1 if it's uniform, and 0 otherwise. And it's pseudo-random if that doesn't really work. So in jargon, it's called classical secure pseudo-random function if one has such a membership oracle, but that's rather a detail. So we say that this cannot be distinguished if the probability over the problem size and this randomly drawn function that the algorithm with oracle access to those keyed functions outputs 1 minus the probability that the algorithm with access to the uniformly random functions outputs 1 is small, is negligibly small. So if we have such a pseudo-random function, then Kearns and others have shown that there is a certain distribution class constructed from it, cannot be efficiently classically generator learned. So what is this? There are distributions from the Kearns generator, and one takes here the input as the seed randomness that any generator takes as the input, the random seed, and we just append the function value fk of x afterwards. So in one way, we amplify the randomness at the beginning of the seed to get a longer string in this fashion. And the argument is basically one by contradiction, as if you could learn this distribution efficiently, one could construct an adversary A for this pseudo-random function, which cannot work from construction or by construction. So one cannot learn this distribution class classically efficiently. So far, so good. So the argument actually goes deeper, and there's an entire chain of reasoning of how to construct those distribution classes. We have just seen that if we have a pseudo-random function, we can construct the hard-to-be-learned classical distribution classes using the work going back to Kearns, but this can be traced back to the existence of a so-called one-way function. Now, one-way functions, we know, of course, in quantum computing. I mean, Shor's famous algorithm breaks certain one-way functions in polynomial time, problems as factoring or discrete logarithms and other hidden subgroup problems quite famously. And this is the idea of the easiness proof for quantum, to use Shor's algorithm to kind of break the one-way function and then to break the chain of reductions and to construct an adversary for the hard-to-learn distribution. This is the technical meat, and I have no time to go into detail here, but it uses basically Shor's algorithm to break what is called this Goldreich, this kind of tree-like structure, this Goldreich, Goldwasser-Mikali construction for pseudo-random functions based on the discrete logarithms. So this interestingly gives rise to the situation that the distribution can be exactly quantum generator learned from a single sample, which is interesting in its own way. So this is great. So the upshot is there is a gap. There is a proven quantum generator learning advantage. Quantum computers can learn more efficiently if you want. This is a case, therefore, for quantum distribution learning. A natural setting is not yet NISQI. It's important to stress, because deep in the machine room of the argument is like a discrete log, like a Shor-like setting. But as a proof of principle, it seems like a valuable and important step. So there is quantum machine learning if you want. So there can be exponential separations for learning tasks in a proven and precise and rigorous fashion of the quantum computer over the classical setting, which is extremely motivating. So let's come to the short teaser on encoding dependent generalization bounds for parameterized quantum circuits. So this is more hands-on. So we do not think so much of the potential of quantum assisted machine learning as such in principle, but look at the actual quantum circuits that are defined or designed for this aim, as a teaser for the following talk by Elias. In fact, almost all concrete quantum assisted learning models are in one way or the other conceived as parameterized quantum circuits, as hybrid schemes, if you want, although with quantum error correction, probably any scheme is hybrid after all, but you know what I mean. So we think of a hybrid quantum classical scheme, so where there's the quantum circuit having all kinds of classical knobs, and there's quantum gates that serve as the data input. They don't have to be at the beginning as such, but they can be all over the place. That's kind of this idea of data re-uploading and giving rise to the encoding strategy after all. So, and other gates give rise to trainable unitaries. And at the end of the day, there are measurements that produce outcomes that can be used for choosing these variational parameters in some clever way. And the point of the learning is to fix the trainable unitaries appropriately given the data and the measurement outcomes that have been obtained in this fashion. Good, that's great. But the question that we've asked here and that Elias will explain in much more detail is, and also Matthias for that matter, because he was the key figure in this work and he will also speak just afterwards. So how well can this work? Can one formulate rigorous performance guarantees for quantum assisted machine learning models based on such hands-on parameterized quantum circuits in terms of the data encoding strategies? This is important as this gives actionable advice, if you want, like valuable advice for encoding strategies. So such performance guarantees are usually formulated in what is called a generalization bound. So these are statements about the predictive performance of a class of algorithms as bounds to the so-called generalization error that's ubiquitous in classical machine learning, as the difference between the true risk on the one hand and the empirical risk on the other over training data of size m, where the loss function punishes bad predictions, basically saying how well the ansatz will perform on unseen data. Now, there's a couple of generalization bounds out there on the market, which are known, but none of that exploit how the data is actually put into the machine, being fed in, so the encoding strategy. So how would one, as this can be complicated, as there are gates all over the place in the encoding and so on. But there's a cute insight coming to rescue, namely that the class of functions that a parameterized quantum circuit model with a fixed encoding can implement is like a Fourier series. So like it's like Fourier-like functions. They are the admissible frequencies, and one can basically parameterize the functions in Fourier terms. And that's the teaser for the next talk. In fact, the next talk will show how this works and how one can give meaningful and good advice on how to do structural risk minimization for encoding strategies, as the upshot is that the choice of data encoding or encoding strategy heavily influences the performance or the generalization ability of such parameterized quantum circuits. Good. 28 minutes into the talk. So let me come to the final bit on learning output distributions of quantum circuits as a kind of a coda of the theme on the learnability of output distributions of quantum circuits. So we've seen that quantum learning algorithms can offer concrete advantages for probabilistic modeling tasks, at least in principle, which is great. However, the class of distributions that have been set up have been rather fine-tuned, to be fair, and the algorithms have not been very NISQI, but require something pretty close to a full fault-tolerant quantum computer. So a natural next question is, great, but can we set up some probabilistic modeling problem for which a general purpose and better NISQI quantum learning algorithm can obtain a concrete formal advantage over classical learning algorithms? This is surely an interesting question, but it's not so easy to get a grip at, a handle at. So after all, the above discussed advantages are rather fine-tuned, while practical hands-on learning problems involving, I don't know, pictures of cats, horses, or dogs for that matter, we started from do not admit a precise mathematical description of that kind and are addressed with algorithmic methods such as restricted Boltzmann machines, generative adversarial networks of GANs, and so on. So we need a framework, a tool, a vehicle to address this question. And us being quantum scientists, what could be more natural than looking at short quantum circuits in the first place? Or rather at distributions that are obtained by performing measurements in the computational basis on states generated by short quantum circuits. To be clear, this could be really of the variational type mentioned earlier, like practical quantum circuits with knobs that we've discussed earlier just a minute ago. So such settings are referred to quantum circuit Born machines, are hinting at the Born rule that is applied when computing probabilities in quantum measurement. So in this sense, we can interpret a quantum circuit, a short quantum circuit, as a generator of the associated output distribution that is obtained upon measurement. So actually in what follows, which will not be so much because I'm almost at the end of the talk, we have nearest neighbor quantum circuits in mind. But again, for rather practical reasons, they're anyway by far the most common architectures, to say the least, because you don't want to jump all over the architectures. Most reasonable platforms are nearest neighbor implementations anyway. And clearly the type of random circuits used in universal random sampling or quantum random sampling experiments that to show a quantum advantage over classical computers as pursued in the famous experiment by our friends, the Google AI team, are precisely of this type. We have a circuit and then you sample at the end of the day to get to basically have a generator of a class of distributions. So equipped with this vehicle, let us refine our question a bit. Are the output distributions of local quantum circuits PUC-learnable by both quantum and classical general purpose probabilistic modeling algorithms? So indeed, recent work has conjectured that learning the output distribution of local quantum circuits might be hard for classical learning algorithms. And this is maybe not so implausible after all, given that it can be hard to classically sample from such distributions. I mean, that's the whole point of the quantum advantage or quantum supremacy experiments, that you cannot sample from these output distributions up to a constant error in the total variation distance on a classical computer under meaningful assumptions, or even to black box verify the correctness of the distribution in a kind of big membership framework. And for this, we have a pretty comprehensive answer. Although I will not have the time to go into detail of this comprehensive answer, but in fact, on the highest level, we have two results and a lot of small results, namely a positive and a negative result. Let's have the negative result first. So a class of distributions arising from computational basis measurements of super log depth nearest neighbor Clifford circuits is not efficiently PUC generator or evaluator learnable. So remember, that means spitting out new samples or learning the probability distributions by any learning algorithm with access to inverse polynomially accurate statistical queries. So what's this? So in this statistical query model, learning algorithms are given access to some oracle, which when queried with a function, respond with some number, which is guaranteed to be at most some tau from the expectation value of the function with respect to the target distribution. That's actually quite natural in this context, as expectation values are readily accessible, and also many standard learning algorithms for generative modeling, including those for training quantum circuit Boltzmann machines of this type can be implemented in the SQ model. But then, well, our point is this does not work. So it's not generator or evaluator learnable. And this sets in already for super short or super log depth Clifford circuits. So Cliffords that are as efficiently classically simulatable if you want, so in the sense that expectation values can be efficiently computed. So this is quite surprising, in that it shows quite drastically how distinct simulation on the one hand and learnability on the other can be different. The positive result is that for any circuit depth, the class of distributions obtained from measurements of the local Clifford circuits is classically efficiently Puck generator and evaluator learnable in the sample oracle model, where one really gets plain vanilla samples or the raw data of the experiments. So these are two main results, but we also take this as an excuse to basically walk the entire diagram and landscape of learning quantum states, distribution testing and sampling verification and so on, and see how these things are connected, also to tackle some of the conjectures that have been sitting around here. So as proof tools, so it kind of relates things to identity testing with a promise. Then that is related to the distribution decision problem using work like similar work by Feldman, then lower bounding the randomized statistical dimension that enters this argument of distribution learning problem. And then of course, notions of Clifford circuits and problems of Clifford circuits at the end of the day. So the lesson is that this is a nice vehicle. It's like an insight onto the learnability of meaningful near-term distributions coming out of short quantum circuits, which constitutes a first rigorous insight into the learnability of outputs of local quantum circuits after all, where there's many lessons to draw. One being that in some ways it constitutes a strong obstruction to proving a quantum advantage via quantum generative models trained by generic learning algorithms. So if there's not enough structure, it will be difficult to have a quantum advantage of quantum machines over classical learners. So some of the conjectures we tackled have been actually proposed in a paper with a cute title, the Born supremacy, hinting at the Born rule that's being applied here, and us really sitting down and looking at the precise identity of this topic at hand and proving theorems about the conjectures at hand and kind of finding out the identity of what's going on here. We were tempted to call our paper the Born identity, but then we, in the end, opted for a more technical title, to my greatest regret. So 37 minutes into the talk. To leave time for questions, I should come to the end of the talk. So this talk was around one theme: in what way we can hope to have a rigorously proven quantum advantage of quantum machines over classical algorithms in a kind of rigorous framework, where we started out from what could be called a proven quantum advantage concerning computational complexity in Puck distribution learning. This is not yet NISQI. It makes use of a rather fine-tuned concept class, to be fair, but it's nice that one can really show an exponential separation between the quantum and the classical performance in computational complexity. As a teaser for the following talk by Elias, we briefly looked at encoding dependent generalization bounds, giving advice to encoding strategies concerning generalization and the performance of learning problems to unseen data, to in the end then have a first look at rigorous insights into the learnability of distributions, the kind of distributions that are obtained when going to the lab and getting data from short circuits, with a couple of surprises and strange insights on how simulatability and learnability are related or not. And in fact, the relations are much weaker than one might have thought initially. So all this is extremely exciting, at least for us. I mean, and kind of the beginning of a bigger program. It also leaves lots of questions for us, because at the end of the day, the motivating question for this for us is and has been whether there exists a quantum learning advantage when learning quantum distributions. And this seems to be way more subtle than one or we might have thought, because the provable answer is yes, it is true for delicately fine-tuned problems or distributions, but no, if you don't take advantage of the problem structure in one way or the other. So somehow structure seems to be needed, but how and when and why? So how much structure is needed at the end of the day? I don't know, but I would love to know. So with this, I would like to thank you very much for your attention, and I'm looking forward to questions you might possibly have. Thanks for your attention.
Okay, great. So thanks for that wonderful talk. There have been a couple of questions. So I'll ask some of the ones that have been typed out in the Q&A in the course of.
I see. Sorry. Okay, I just see them now. Yeah.
Okay. So I think Elias answered the first of the questions by Youssef Achari Barada. So the second question is, can these circuits be adapted to other generative models like QGANs? And I believe this refers to the third project that you talked about.
Meaning whether one can kind of make statements about like quantum advantages in QGANs over classical analogs. Is this the question?
I think
yeah, I mean, presumably yes. I mean, possibly yes, but I mean, a kind of meta lesson from this is that the answers are commonly rather fine-tuned to the problem at hand. And we saw this in all ramifications, so in the first part of the talk and also the latter part of the talk, that well, I mean that one really has to kind of reverse engineer the kind of reasoning and kind of set up the argument for the problem at hand. So while the answer is plausibly yes, the devil will be in the detail to really find out whether this is the case. So that kind of links also to the big question at the end. So how much structure is needed at the end of the day? We have these couple of results relating to quantum advantages, also the work by IBM that I cited, but yeah, the race is still open, and yeah, that's a good question, but I don't know.
Okay, then so there has been another question in the chat. How does the measurement affect the learnability of the outputs of local quantum circuits?
I mean, in some way, the measurement is just seen as a vehicle to produce a distribution concept class. So the whole thing, I mean, it's just a machine that spits out probability distributions, and the task at hand involves measurement, like as such. I mean, that's really similar to the like quantum advantage experiments, where the task is not to have a circuit, but really to have like to look at an output distribution and be able to like sample classically from a distribution that's close to the distribution generated by the quantum setting. So in this sense, the measurement is kind of part of the prescription, and so that's kind of part of the problem specification. Now you say, in what way does the measurement change the learnability? So parsing that question, you seem to be asking in what way we could kind of learn properties of it's more like a tomographic question, right? Whether we could kind of learn properties of a quantum circuit by performing different types of measurement, and then like learning what the circuit as such is. It's a bit of like a shadow estimation problem. That makes sense. That's an interesting question. Yeah, but it's kind of a different one. So here, our emphasis has been like on distribution learning, which kind of by definition is on classical distribution. So the kind of the measurement is part of the prescription, if you want.
Right. Maybe I say you kind of did consider, which is something that you could adaptive or entangled measurements, nothing fancy like that. So we just considered kind of like measuring the computational basis and not transferring information between different measurements. So that's just kind of like the simplest case. So the question about whether you can actually obtain a quantum advantage by like adapting your measurements, that is still open.
Oh yeah. Okay, sorry. You. It's interesting because you're also in Berlin, and the connection was like very bad. So the first part of the sentence I didn't hear. But yes, that makes perfect sense to think of other types of measurements. That's right. But I mean, for us, I mean, the simplest measurement is kind of a good thing, right? I mean, like it's the most plain vanilla setting and the most transparent thing. But of course, you could also think of other questions of like adaptive schemes or other complicated measurements, which seem interesting. That's right. Our German telecom strikes again. That's right. Yeah, Germany is famous for many things, but not for the internet.
So we have time for one more question, if anyone would like to ask it.
Alejandro wants.
Yes, good question. Hi, Jens, good to see you. Thanks for the beautiful talk. I agree 100%. Yeah, these results are certainly beacons for us looking for quantum advantage. They're really taking us looking in the right direction. So I have a question. I'm super curious about your insights on maybe, so in this last slide, about maybe some intuition about how to build kind of like hierarchically towards actually that result of adding that structure. Maybe this last question that you posed. Maybe that question is, and the other question is about the going beyond the Clifford circuits, like how complicated or what was your intuition there of what the results will look like when you go to beyond the Clifford circuits in the generative model?
Okay, this is too much of a question to answer in like 50 seconds, but I try to be short. The first thing is, I mean, there's surprisingly little known on that question, and that the structure that is known and used in the known settings, like for example, the IBM work, our work, and so on, is like that's enormously structured. Also, like Jonas Kübler has done wonderful work in this direction. So the known results make use of enormous structure, and like in our reduction is complicated, but in the machine room down there, it's like a discrete log. So really a short type algorithm that's a fully fledged quantum algorithm, and all the known settings, including the kernel work of the IBM team that show quantum advantages, are basically translating a non-learning algorithm to the learning world. And that's great for showing proof of principle things, but it's not really not kind of your type of structure you want to see. You want to look at cats and dogs and see, does the cat has the structure or the dog have that structure? And that's difficult. And I wouldn't know. And the last bit shows that if there's too little structure, then you might not have a quantum advantage after all. So the room in the middle is wide open. In some way, the talk can be seen as an invitation to tackle the interesting room in the middle we have know very little about. Cliffords, they're just fun and easy. I mean, of course, you can go beyond that. We looked a bit at match gate circuits, like free fermions with some ups and downs, I can tell you in private. But yeah, that was just the easiest thing to look at.
Wonderful. Thank you. Thank you very much.
Thanks.
Okay. Yeah. Thanks for the great talk, Jens.
Yeah, thank you.
So now we will move on to the next talk, which is by Elias. So Elias, the floor is yours.
Thank you very much. Let me share. Okay, can we see this? And I can try to move the slides.
It's perfect.
Okay, and also using my cool laser pointer, hopefully. Okay, hello everyone. Hi, Yuki, thanks for the kind introduction. It's really a pleasure to be here. It's been an awesome program so far. And yeah, it's really an honor. Today I want to talk about some recent work we did together with Jens, Matthias Caro, and two other colleagues from Berlin on generalization bounds for parameterized quantum circuits. The work, you can find it on the archive and soon on Quantum. This is a long array of words, and my goal for today is to make sense of them. As I said, this was a collaboration between people in Berlin and people in a very nice person in Munich. You just heard Jens. If you stick after this talk, you also hear more generalization bounds from Matthias together with some people overseas. Now, my goal for today is really to explain you why we wanted to do what we ended up doing, more than giving you too much technical detail that would be hard to follow. And in particular, I hope to infect you my interest in this field of generalization bounds and how it can be very important for us on the long run. I'll start by specifying what flavor of quantum machine learning we're performing here, like what do we call quantum machine learning. Then we'll see what quantum objects we want to study in the form of a hypothesis graph. Then I'll wrap up the theory with some notions from statistical learning theory that revolve around this notion of generalization, which is what we're most interested in. At the end, a very brief literature summary that will motivate why the specific kind of bounds we're going for was worth to pursue. And then the highlight will be to make sense of all of this array of words that I color-coded as to from where they come. Yeah, hopefully in 20 minutes, you'll be convinced that it's important to find explicitly encoding dependent uniform generalization bounds for data reuploading PQCs. Let's start with what quantum machine learning or what flavor of quantum machine learning we do. In particular, we do supervised learning. That is the study of three big, namely a data domain, X cross Y. X is the points, Y is the labels, a class of functions called the hypothesis class or concept class, and a very structured searching algorithm called the learning algorithm. The way we can think about these things in practice is X could be some images and Y some discrete set of labels of these images as like cats, dogs, cars, trains, you name it. Then the way to think about the hypothesis class is, for example, considering some fixed architecture for neural networks, like convolutional neural networks or more complex things if you like. And then the epitomal example of learning algorithms is like the stochastic gradient descent that you've all probably heard about. In Jens's talk, we heard a lot about the structure of the problem. And usually for supervised learning tasks, we consider that we have some promise on the structure of the data, but this promise is somewhat hard to capture mathematically. So it's fairly easy to define what a half space is, but it's not so easy to write down a formula that says, okay, this is a cat or this is a dog. And this is important for like the spirit of how we tackle these things. Now, you've heard the story before. We assume that we have an unknown probability distribution over a data space and we don't have access to it. Instead, we have access to an oracle that we can query to produce point label pairs. But querying this oracle is expensive, so we can only do it a finite number of times, and this produces a training set for us. We feed this training set to the learning algorithm, which usually iteratively searches throughout the hypothesis class to produce a hypothesis. Hypothesis is just a fancy name for a function that takes inputs and produces labels. We expect that this learned hypothesis will perform well on the training set, meaning that once we feed it the points, it will produce the right labels. But that's hardly enough for us. Our ultimate goal is to find a hypothesis which performs successfully on new data it has never seen before. So we query the oracle again. We put the point through the hypothesis, and then we compare whether the predicted label matches the true label. And this is like the true goal of supervised learning. Now, what we today call quantum machine learning is we keep the data classical, keep the oracle classical, keep the learning algorithm classical, but consider a quantum hypothesis class. In particular, we consider quantum hypothesis class defined on parameterized quantum circuits, or in short, PQCs. We consider functions which are defined as the expectation value of measuring some given observable after applying a parameterized unitary in a quantum computer. And this is a real valued function, which means that we can perform not only finite class classification tasks, but also regression tasks. So it's a bit more general. But let's take a closer look at which class of PQCs we're actually interested in, because I gave you this black box picture, which is not very telling, since in practice there is a lot of structure in the problem. The most popular choice that people made when starting to study this kind of functions were this encoding first PQCs. In this family of circuits, the data comes first into the circuit, usually as a collection of 1 qubit Pauli rotations, where the parameter of the rotation is taken to one of the components of your data. And afterwards, there's a variational form with some parameters we want to tune to fulfill the task at hand, and finally measure the fixed measurement, the fixed observable. This problem has a few limitations, and especially two. And those are that if we keep everything to be unitary, this physical separation between the encoding and the variational form makes it very hard for us to introduce nonlinearities or nonlinear contributions for the data processing. And from neural networks, we know that this linearities are very important. So not having them is a liability. And also the scaling in number of qubits of these problems usually grows linearly with the dimension of our input data. So for near-term devices, it very quickly gets a bit out of hand. Also, from a practical point of view, when people started studying formally this class of functions, usually all the attention was paid to the variational form. People started asking questions like, how many qubits should we use? How many trainable gates should we have? How much entanglement? Can we find good layer ansatz that we can repeat several times? And if yes, how many layers should we have? And all very important questions, but which in comparison paid almost no attention to the encoding. Like no one was asking the same questions regarding how many encoding gates one should use. And that ended up amounting to so much that a new model emerged, the so-called data reuploading family of parameterized quantum circuits. If you follow the color coding, this image is quite telling in the sense that now we don't have first one big box where all the encoding happens, and then one big box where all the trainable part happens, but rather we have many gates which encode data and many gates which are parameterized and we can train, and they are mixed within the circuit. Important to note is that each gate does not need to be linked to only one data coordinate. Like different gates can encode the same coordinate. Like in every combination you may want. This image is the same Jens showed before. This was proposed in an early, like a couple of years ago, reference by Pérez Salinas and others, including myself back in Barcelona. And in this paper, we showed that using only one qubit with this scheme was already enough to overcome both limitations of the encoding first circuits. Namely, in this paper, we proved that we could perform successfully non-linear classification with even more than 2 tasks on data of up to 4 or 6 dimensions, I believe. So this data reuploading circuits, in a way, happen to be more general than the encoding first ones. And then later on, in this other very nice paper by Maria Schuld, Ryan Zwick, and Johannes Meyer, also co-authors of this paper, they showed that actually the encoding strategy you follow in a PQC is crucial for the expressive power of the functions you get at the end. So regardless how much time you spend thinking how the trainable part should go, if you don't have a good encoding strategy, the functions that come out will not really reflect the expressivity that you invested into the trainable part. And for these reasons, we believed that studying data reuploading circuits with a specific focus on the encoding part was important. And this is the first point. We want to study the effect of the encoding strategy on generalization. That is, like, what effect does it play, how many times we encode the data, which encoding gates we use, and so on, specifically for the generalization. But what exactly is generalization and how do we study it are questions which belong in the field of statistical learning theory. And for that, we need to define this notion of generalization gap, which builds on notions we've heard and are all familiar to us, such as this data domain, including the unknown probability distribution, which we don't have access to. What we have access to is a finite data set of points sampled according to the distribution. Then we have hypotheses, which map points to labels, and which we consider to be contained in a restricted hypothesis class. Then with a learning algorithm, we hope to find a good hypothesis, and the notion of a loss function characterizes what hypotheses are good by giving us a source of distance on the label space. Then what we would really like to know is how good or bad our hypothesis performs over the entire training set. And this is what we call the expected risk, but we cannot hope to compute that because we have said that this D distribution is unknown. What we can use is the average over the training set we have. And we use this empirical risk, which is the average, as a proxy for the expected risk. But of course, this proxy sometimes is not very good because we've all heard about the notion of overfitting. But then we define the generalization gap as the difference between the two. So with a low generalization gap, we know that our hypothesis performs similarly on the training data and on the data it has never seen before. So for a good hypothesis, it's important we have a small generalization gap, but that is not necessarily sufficient. There are also bad hypotheses which can achieve vanishing these small gaps, but still, it's not sufficient, but it's a necessary condition to have a small generalization gap. So we still need to study it. Now, how do we study the generalization gap? Is by placing probabilistic upper bounds on it. And from statistical learning theory, one approach to follow this is by using uniform generalization bounds. Now I'll give a template for how a uniform generalization bound looks like. We want something that works for any given data domain and hypothesis class. And we want to find bounds that hold for all of the following ones: for every probability distribution over the data, for every data set sampled randomly from the distribution, for every tolerance parameter that we can tune ourselves, and for every hypothesis within the class. Then we want to find a bound that looks like this: the expected risk minus the empirical risk is smaller or equal to something, with probability at least 1 minus delta. Now we call this bounds uniform because if you notice, the right-hand side of the bound does not depend on which specific hypothesis we have, but rather on the hypothesis class the function belongs to. So that means it's uniform over the class, and it also means that it's a worst case bound, because if only one hypothesis in the class already has very severe overfitting phenomena, then this right-hand side must show that. So sometimes these bounds are not the tightest for the hypothesis of interest, but still they're a very good first step towards understanding the general behavior of parameterized quantum circuits regarding generalization. And also they give us meaningful statements on the asymptotics towards, like, if we grow our system to very many qubits or very many gates. Good news for us is that there's an entire zoo of such bounds that we can use to study our circuits. And even better news for us is that this can help us in solving a decades-old problem. And this decades-old problem is the problem of model selection. Assume we're given some machine learning task with some data, and we consider ourselves two different data loading architectures. That means two parameterized quantum circuits with somewhat decoding strategies. Now, we assume that for both of them, we run stochastic gradient descent, and we, for both of them, find relatively good hypotheses which achieve a similarly low empirical risk. So we have the data, two different hypothesis classes, and for both, we find a hypothesis which performs nicely on the training set. Now, question. In real life, which of the two should we keep? And according to the statistical learning theory bounds, we should always keep the one that generalizes better, and that's the one that achieves the lowest right-hand side for this bound. In the literature, these generalization bounds always come in terms of some intermediate quantities called complexity bounds, which I wrote as C. The name is that they're called complexity bounds for historic reasons, and they are properties of the hypothesis class only. If you've ever looked into learning theory, probably some of these already sound familiar to you, but the bottom line is that there's an entire zoo of such complexity measures, and it's very good for us that a lot of people have been studying them, and we have known generalization bounds for all of them. So if we can find a complexity bound for one of the complexity measures of our function class, then we immediately inherit a generalization bound. Usually, you'll maybe agree with me that we characterize our hypothesis classes, like the families of functions we use, in terms of some set of structural hyperparameters that I called K. This could be, if you're doing neural networks, how many hidden layers you use, how many neurons are in your hidden layers, what activation function you want to use, what initialization protocol for your weights you use. Or for parameterized quantum circuits, that could be number of qubits, number of gates. For us, like the ones that are important for us would be number of encoding gates, type of gates that you use for encoding. But in any case, we often can express f as a function of this set of structural hyperparameters. In some sweet spot cases, we can also write c as a function of these structural hyperparameters, although this does not always happen. But in the cases where it does happen, in the cases where we use a complexity measure that depends explicitly on the structural hyperparameters, then we inherit the explicit dependence on the generalization bound. And keeping in mind the idea of structural risk minimization, which is what tells us how to select our models, having such generalization bounds, it gives us a much clearer way to decide how to design the parameterized quantum circuits we want to use. And this is what we're aiming for, a generalization bound that depends explicitly on some structural hyperparameters, which in turn depend on the encoding strategy of the circuit. Now, let's take a quick look at the literature. This is a very rapidly evolving field. In the last year or year and a half, a lot of references have come out on it, and I'll list you some of them here. So first we have this, probably the first one on the field, also by Matthias Caro, who will just speak now. And they bounded something called like the pseudo dimension of quantum circuits in terms of the number of trainable two local gates. Then we have another bound on the VC dimension, which is like the most typical complexity measure in terms of the rank of the parameterized observable. Then we have a bound on the covering number in terms of something called the effective dimension of the models. Then bounds on the Rademacher complexity, both on the mutual information between the input data and the output quantum states and in the amount of magic in the circuit channels. And there are a few others. As you see, most of them have been published during the year 2021. And it must be said, almost all of them considered only encoding first PQCs and not data reuploading PQCs. And none of them consider slightly different models, but in spirit, they're all the same. And at the end of the day, fair to compare to one another. Now, last slide was basically this: some reference bound, some complexity measure in terms of some parameter. But for us, we said that the encoding is very important. So question, which of the bounds actually depend on how data is encoded? For that, I give you two examples. One, the one that gave a bound that depends on the rank of a parameterized observable, and one that gave a bound based on the mutual information, and a simple test. If in the circuit we do not encode the data at all, would these bounds change? We can argue that the rank of the observable it doesn't care about what happens before it's. So the first one would be encoding independent, whereas the second one, the mutual information, would capture the lack of correlation between input and output. So the second one is encoding dependent. What we're going for is an encoding dependent bound. Similarly, we said that the structural hyperparameters are important. So question, which of the bounds depend explicitly on the experimentally tunable parameters? Again, two examples. The bound by Matthias was written in terms of the number of trainable two local gates, whereas this other bound by people over at IBM bounded something called effective dimension. Again, a simple test. Can we write Z explicitly in terms of K? For the first bound, Z is already a subset of K because the number of trainable two local gates is one of these natural design parameters. Whereas the effective dimension is a more or less involved quantity that can only be estimated numerically, which already hints at only implicit dependence. What we want for the sake of model selection is that Z depends explicitly on K. I gave some bounds that are dependent, some bounds that are independent, some bounds whose dependent was explicit, some bounds whose dependent was only implicit, but there was in the literature no bound that was both dependent on the encoding and explicitly depending on the structural hyperparameters. And this is where our bound comes from. We wanted it to be explicitly encoding dependent so that the model selection problem could be solved using the bound. Because we used complexity measures, it ended up being a uniform generalization bound, which is a good start. And we derived it for the very interesting class of data reuploading PQCs. And I hope by now, all of these words make a bit more sense to you and you share the belief that this is an important problem. Very briefly, our bound, we gave bounds for the Rademacher complexity and the metric entropy in terms of the parameters we mentioned, like the number and type of encoding gates. And one short application is we want to encode data of dimension D and use n encoding gates, which we restrict to be any tensor product of Pauli operators. Then the generalization bound we find is this one, which for fixed D, which D is usually a fixed of the problem, we have that the generalization gap for data reuploading PQCs grows polynomially in the number of times we encode. That means the least number of times we encode, the better generalization. Although careful, because if we don't encode enough times, we'll be underfitting the data, which is also something we don't want. So we need to find the sweet spot between underfitting and overfitting. Now, I'm not sure if we have time for Outlook, but you can ask me about this now or later. I'm very open to discussing this because I could talk about generalization bounds for days. These are some of the references I talked about, including our paper. And yeah, thank you very much for having me and your questions.
Okay, so we have time for maybe one question.
Yeah, sorry about that.
Actually, so there was already this question in the chat. So Yusuf asked again, can you introduce activation functions for nonlinearity?
You don't have to. So you don't have, the nonlinearities here don't come with activation functions. They come naturally when like you intercalate trainable and non-trainable gates.
Okay, so actually I had another question. If you go back a couple of slides in your, oh no, I just wanted to look at who was BPP21.
Leonardo Monkey.
I see.
This is the one we talked about last week.
Okay, anyway.
Sorry, may I just make a very quick comment? I would like to
Yes.
know like how tight these bounds are, because if you want to use these bounds as a kind of a guide for kind of desired applications, for example, it depends on how tight they are, actually, because you need more than just like the upper bound, you need the lower bound as well. So I think the lower bounds are probably harder to get, I think.
Yeah.
Right?
Lower bounds are hard to get, and this is one of the Outlook like next research directions. If you've been following research in classical machine learning, you'll probably have heard that uniform bounds are a bit shunned on nowadays. And there's a quest for like better bounds which have to be necessarily non-uniform. So that's what I'm saying. Like these generalization bounds are a good first step, but they're not going to break all the problems we have.
Yeah.
Oh, okay, so there's another question from Ekaterini Grazia, which is, do you restrict the number of qubits for these generalization bounds?
That's the cool thing. For our bounds, like the bounds hold irrespective of the number of qubits. Because you only look at how many times we encode, and for that, it doesn't matter if you have 1 qubit or 10 billion. Like the functional class is the same for us.
Okay, great. Well, I think we should move on to Matthias's talk. Well, thank you very much, Alice. That was a fantastic talk. I really enjoyed it. Okay, so Matthias, would you like to start sharing your screen?
Yeah, I'll be happy to. So let's see. Can you see the slides? Can you see the slides moving?
Yes.
Okay, perfect. Should I start?
Please.
Right. Okay. Thank you very much. So my name is Matthias, and I'm very happy about the opportunity to tell you about generalization in quantum machine learning from few training data. You can find more information about this on the archive. There's a paper with the same title that appeared yesterday. Now, before talking about the content of this work, I want to tell you shortly about the people behind this work, because I had the joy of working together with an amazing group of collaborators. So here you see Robert, Marco, Kunal, Andrew, Lukash, and Patrick. And I'm grateful to all of them for making this collaboration possible. I want to start with a very short motivation on why you should care about generalization in quantum machine learning. You might already care now that you've heard Elias's talk, but still let me try and remind you of the most important aspects. If you think about machine learning, be it classical or quantum, there's at least 2 aspects you should worry about. The first is, I would argue, optimization. So here you should ask the question, how or when can I successfully train my model to fit the training data? But even if you manage to do that, you still have to worry about generalization. So this is the question, how or when do you avoid overfitting? Or in other words, when can you ensure that good performance on the data actually implies good performance on new data that you haven't seen yet? And this is also the focus of this work. So we want to understand how much training data is needed or sufficient for good generalization in variational quantum machine learning models. this is what's going to happen in the rest of the talk. I'll first recap some notions from classical learning theory. True, you've heard about them in the previous talks already, but I think it's good to see them again. Then I'll tell you about the models that we looked at. And with this, I'm then able to formulate our results, which are generalization bounds for quantum machine learning models. To show you that these are actually interesting bounds, I'll demonstrate two applications, namely quantum phase recognition and unitary compiling. And then I'll summarize and send you off with some open questions. So let's first recap a little bit of classical learning theory. Here's an intuitive description of PAC learning. So in PAC learning, you might have a learner, and then you have some distribution mu over inputs and some unknown function f star. And the only thing you know is that f star lies in some class calligraphic f. But other than that, these objects are unknown to you. Now you as learner get access to training data. And we're working in a supervised learning regime. So the training data are like examples, xi with corresponding labels f star of xi. And the xi are drawn randomly from this distribution mu. Your task now is to output a hypothesis in your class f, where f describes your model. Now you shouldn't just output any hypothesis, but your hypothesis should be a good approximation to the unknown function with respect to this unknown distribution. So that's a picture you can have in mind. But how could we actually succeed at learning? One of the most basic routines in classical learning theory is called empirical risk minimization. And here's the informal idea of this principle. It rests on the implicit assumption that the model you're using has, in some sense, low complexity. And here my F is the model class, so the class of functions your machine learning model can implement. Under this assumption, what you're going to try is to this can be hard, but you're going to try to find some hypothesis in your class that fits the training data well. And then you hope that this also will work on data that you haven't seen yet. Now, how and when does this actually work, right? We want to understand this a little bit better. And as you've already heard in the previous talk, one way of formalizing this is in terms of so-called probably approximately correct generalization bounds. And I'll abbreviate probably approximately correct by PAC. Now, if a uniform PAC generalization bound for a class F with respect to some loss function that measures your performance looks roughly as follows. First, you say for any unknown probability distribution and for any unknown function, if you're given training data of size m, where the instances are drawn randomly from this unknown distribution, and then you get the corresponding labels from the unknown function. With high success probability over the choice of such training data, you have that for all functions in your class, the following inequality holds. Let me unpack this a bit. So on the left-hand side, you see the expected loss of the hypothesis h. In the integrand, you see the loss function comparing the prediction h of x to the true label f star of x, and then you take an expectation of this. That's what we call the true risk or the prediction error. And now this is what we want to control. Unfortunately, we cannot evaluate it because we don't know mu. But what we can do is upper bound it. And the generalization bound tells you that you can upper bound it in terms of the training error, so the average loss on your training data, plus some error term. Notice that the training error is actually something you can evaluate. And a piece of nomenclature, the difference between the true risk and the training error is often called the generalization error. And this is what we bound in generalization bounds. So a generalization bound tells you we can bound the true risk, the quantity we care about, in terms of the training error, which we can evaluate, but we're paying a little bit for this, right? We're paying this function g, which describes your generalization error. So the crucial question becomes, how can we understand this function? And in particular, how can we understand how this function depends on the machine learning model we're using, which is described by this class F? And the standard answer in classical learning theory are complexity measures for function classes. There's many of those in classical learning theory. I'm just flashing them at you in case you recognize some. I want to focus on empirical covering numbers and metric entropies. I'm not going to give you the formal definition, but I'll try to explain pictorially what these are. So let's suppose that this calligraphic F is the class of functions our model can implement. Now, what you're going to look at are balls around elements of the function class, and think of the balls as having a small radius. And now what you try is to take many of these balls and cover your whole function class with them. That's why it's called the covering number. And the smallest number of epsilon balls that you can use to cover your function class completely is the epsilon covering number of your class. So that explains covering number. Where does the empirical come from? Well, if you draw a ball, then you need to know the distance to measure the radius, right? And in empirical covering numbers, the distance is training data dependent. So that's where the empirical in the empirical covering number comes from. Now, the intuition is the smaller the empirical covering number, the less complex your function class is with respect to the training data you're looking at. And one can, in fact, show that this measures complexity in the right way for proving generalization bounds. Now, I've been talking a lot about classical learning theory. Let's make it quantum. First, I want to tell you about the models that we looked at. So these variational quantum machine learning models. In fact, we look at a variety of models, as you can see in this figure. Unfortunately, in this talk, I don't have time to go into all of them. So let's zoom in into the first panel of this figure. So this is a basic quantum machine learning model where it works in terms of a parameterized quantum circuit. And it works as follows. You get an input state. Then you perform local trainable gates. So colored gates here are the things you can train. That you might interleave this with some fixed global gates that you cannot train. Some more trainable gates that are local, some more potentially non-local fixed gates, and in the end you measure. Now, if you ignore the measurement for now, then you can think of this as taking an input state to an output state. So in the language of quantum information, it's either unitary or more generally, it's a completely positive and trace preserving map. And crucially, it's a parameterized map because you can change the parameters in these gates and therefore change the parameters in the map. Since you've just heard Elias's talk, let me just mention that for simplicity here, we draw the input state first and then act on it. You might now wonder about, well, can I place encoding gates also throughout the circuit? And indeed you can, and our bounds will basically stay the same. So keep this picture of a quantum machine learning model in mind. Now, how do we measure the performance of such a quantum machine learning model? What we're going to do is to look at loss functions of the following form. To evaluate the loss of the parameter setting alpha on the training data point xi, yi, where xi is like the input and yi is the label, we do the following. We first take the input state rho of xi. Now, if xi is classical, you should think of this as the quantum state that xi is encoded in. But we could also work with quantum data directly, and then rho of xi would just be the input state. Then we apply a parameterized quantum machine learning model on the input state, or maybe only on a subsystem of it. And then we perform a measurement according to some loss observable, which is allowed to depend on the training data point. Now, this loss observable is problem dependent, right? You have to choose this depending on what performance you want to award or penalize. But this is quite a general class of loss functions that we can deal with, and it's also physically motivated, right? You perform measurements at the end of your circuit. Once you have the loss function, defining the training error and the prediction error is easy. So the empirical risk is really the average of the loss function over your training data set. So here the training data set is S, and it consists of points xi and labels f star of xi. And the true or the expected risk is not a sample average, but a true average. So it's an expectation value of your loss with respect to the underlying distribution. And now, by what I've shown you before, the generalization error in this case is the difference between the two, right? It's the true risk minus the empirical risk. With this, I now have all the notions and notations in place to tell you about our results, which are generalization bounds for quantum machine learning models. So before going into that, let's first think about where in such a quantum machine learning model could complexity actually come from, because we already know that complexity is important for generalization. Well, the first aspect that you just heard about is it can come from the data encoding. And there we now know some generalization bounds that take the data encoding into account. Second, it could come from the measurement that you choose. And if you followed the conference, you might have heard a talk by Casper earlier in the week about this. The third part that can lead to complexity is the trainable part in the circuit. So the number of trainable gates, where you place them, how you parameterize them, and things like that. This has been studied in several prior works, and it's also our focus. And we believe that our bounds apply to more general models and are also stronger than previous bounds. I want to emphasize, however, that all of these aspects are important, and I think it's important to keep all of them in mind, and hopefully in the future we'll find a unifying picture on all of those. All right, so let me show you one of our results. So this is the theorem for this basic quantum machine learning model that we looked at before. Suppose you have such a quantum machine learning model in which you have capital T trainable local gates. And by that, I mean you have like local unitaries, either 2 local or let's say K local, where K is independent of N. And you can in principle train those unitaries arbitrarily. So they're just some trainable 2-qubit unitaries. Then we can show a bound on the covering numbers for the corresponding model class. Namely, we show that if you take a logarithm of the covering numbers, this grows at worst roughly linearly in the number of trainable gates. And now, using the machinery from classical learning theory, we can show that this implies a generalization error bound. Namely, the generalization error will grow at worst roughly like the square root of number of trainable gates divided by the training data size. Why should you care? One reason why I think you should care and why I care is that we can look at a special case of this. Namely, if you want to implement your quantum machine learning model in practice, it's probably efficiently implementable. So it has polynomial size. Now, if you have polynomial size quantum machine learning models, so polynomially many trainable gates, then our bound tells you that you can generalize well from polynomial size training data. So that means efficiently implementable quantum machine learning models generalize well from efficiently large training data sets. We have a variety of extensions of this theorem for all the scenarios that I showed you in this figure before. I unfortunately don't have time to go into this here, but I invite you to either ask me questions about it or take a look at our paper. So I've showed you this bound, and I hope that some of you already consider it interesting. I want to persuade the rest of you that it's interesting by showing you 2 applications. The first is quantum phase recognition. So what is this task? A typical quantum phase recognition task would be that as input, you get the ground state psi of some Hamiltonian. In our case, we looked at the so-called generalized cluster Hamiltonian. It's not important that you know what this Hamiltonian is. The only thing you need to know is that this Hamiltonian has a ground state phase diagram with 4 different phases. And given a ground state, you should now tell me which of these 4 phases in the ground state phase diagram does the state belong to. So output a label from 1 to 4. We now suggest to phrase a machine learning version of this problem in the following way. So the quantum machine learning problem here would be, your input is training data consisting of ground states psi and the corresponding phase labels. So telling you what phase does this ground state belong to. And your goal now is to output a quantum machine learning model that, given a new ground state, correctly predicts the phase label of that state. So let me show you a little bit what we did in our numerical experiments. I want to say that here we use what's called a quantum convolutional neural network. This goes back to work by the group of Michael Lukin. So we're not the first to use this architecture, and we're also not the first to use it for quantum phase recognition. But we're the first to provide rigorous guarantees for this. So let me shortly explain to you what the 2 panels say here. In panel A, you see first the phase diagram of this Hamiltonian. So you see it cuts the plane into 5 regions, but only 4 of them, only 4 different phases. Everything that's blue is correctly classified by the quantum convolutional neural network, and everything that's red is incorrectly classified. This is, by the way, for 16 qubits. So you see that here the quantum convolutional neural network performs reasonably well, and interestingly, it does so using only 30 training data points, even though we have 16 qubits, and 2 to the 16 is pretty large. And on the right, you see that as the training data size increases, so green is lowest training data size, red is the largest training data size. If you plot the test accuracy versus the training accuracy, this becomes more and more linear with slope 1. So that means that the training accuracy is a really, really good predictor for the testing accuracy as the training data size grows. Why does this happen? The cool thing about QCNNs is that they use only logarithmically many independently trainable local gates. So that means you can go to our generalization bounds and they will tell you that the training data size you need to guarantee good generalization grows at worst polylogarithmically with the system size. And that's why these quantum convolutional neural networks can really succeed at quantum phase recognition if you manage to train them well, even for low training data sizes. I want to shortly tell you about a second application, which is called unitary compiling. Again, let me first tell you what this problem is. So a general unitary compiling task would be you're given a big n-qubit unitary U, and now you want basically an algorithm for computing it. So you want to decompose that unitary U into a quantum circuit consisting of 2-qubit unitaries, because that would be what you can implement. Sometimes in unitary compilation, you impose additional restrictions to make it hardware implementable, so something like connectivity issues, but we focus on this here. Again, let's try to make a QML version of this problem. So now your input would be training data consisting of input states psi I and the corresponding output states when applying this unknown unitary. And your goal is to output a 2-local quantum machine learning model that, given a new input state, produces a good approximation for the correct output state. And also here, we did some numerical experiments. So what we tried was to compile the quantum Fourier transform, which you probably know, into a 2-local quantum circuit. And here we actually used a quantum machine learning model with variable structure. So it could grow or shrink by adding more trainable gates or removing trainable gates. And this turns out to work pretty well. So on the left, you see how the training data size needed for good generalization grows as the system size grows. And let's first focus at these 2 lines. These grow roughly linearly. And actually, if you take, so here we took computational basis states for training. If you take hard random states, it's even better. So it's basically constant. Now, our theory predicts that at worst, your training data size will grow quadratically. So this is in agreement with our theory, but it paints an even more optimistic picture. And on the right, you again see that as the training error decreases, so does the testing error. And this correspondence gets much better as the training data size grows. Now, let me wrap up. First, let me summarize. So I told you again about how you can use parameterized quantum circuits, which you train using classical optimization, as a hybrid approach to variational quantum machine learning. Our results in this work are extremely general, mathematically rigorous generalization guarantees for these models. And one crucial message is efficient quantum machine learning models generalize well from poly-sized training data. Also, we showed you 2 applications for quantum phase recognition and unitary compiling. I want to send you off with some open questions. In the unitary compiling numerics, we saw that our bounds can be a bit pessimistic. And that's actually inherent because they're worst case bounds over all possible distributions. So basically, like Elias said, it would be interesting to understand whether when quantum machine learning models can outperform our bounds and whether we can tighten them. A second aspect that I personally find interesting is whether we combine the perspective here, where we focus on the trainable part, with the perspective that focuses more on the encoding. And finally, we believe that this should have more applications than the 2 we showed you, for example, in dynamical simulation and quantum error correction. And I'm excited to see what can come out of this there. So this brings me to the end of my talk. I thank you very much for your attention. And now I'm looking forward to your questions.
Okay, any questions?
Oh,
okay, Koichi asks.
I think things have been happening in the chat, right?
Yeah, there has been one question in the chat. So Koichi asks, compared with classical models such as neural network, the number of training data needed for generalization is smaller or larger in QML?
Mm-hmm. So this is, oops, apologies. This is, of course, a very good question. And I personally think we're not yet in a place where we can answer this. What we can say is, if you think about a quantum machine learning model that's like practically interesting, then it will have polynomially many gates, I would argue. And then you can get good generalization from polynomial sized training data. So that's actually pretty nice. For neural networks, especially for the modern ones, the classical theory of generalization doesn't quite work anymore. So a lot of new theoretical tools have been developed there in recent years. And I think this machinery is not yet in place in the quantum world. So I personally believe we cannot yet convincingly answer this question. And I think it's interesting to try and explore this a bit further. So to really explore for different problems, how well neural networks generalize in comparison to the quantum world.
Yeah, I think that's also a super interesting question. So Elias asks, is there any hope in finding lower bounds here?
That's very fair. Before you said finding lower bounds is hard, right? So given the two talks we just heard, I believe that separately for these two scenarios, it's not possible. Because in what Elias told us about, we focus only on the encoding, but we ignore basically the trainable part. So effectively, if we have no trainable part, of course it generalizes well, but that's not so easy to see. Or that's not so easy to see in our bounds. And similarly here, we ignore the encoding, and if you don't encode at all, it obviously generalizes well. So I believe that using some tools from classical learning theory, there is some hope for proving lower bounds, but you really have to make sure that you have reasonable architectural assumption. For example, that the encoding is non-trivial and that the trainable part is non-trivial, but I don't yet know what non-trivial means.
Okay, so yes, I think we might want to move on to the last speaker. So thanks very much, Matthias. So you. Julian, would you like to share your screen?
Yeah, we'll do that. All right. Thanks, Julian, for the introduction, and thanks for all the previous speakers for the great presentations. So I would like to talk to you about the recent work that we did called the simultaneous perturbation stochastic approximation of the quantum fish information, which is published in Quantum. And we did this work with Krista and Stefan from IBM Quantum and with Giuseppe Calleo from EPFL. And since that's quite a long title, usually we call this work just Quantum Natural SPSA. And I hope that by the end of the talk, all of these words make sense to you. So to motivate this work, let's look at the simple task. We're given a loss function, f, and a parameters model p, which depends on parameters theta. We want to find the optimal parameters theta so that we minimize the loss of our function. Now, this is a very broad class of problems, and in the classical community, this often appears in machine learning tasks, where, for instance, your model is a neural network, and the loss could be the cross entropy loss, or more in a quantum setting, your model can be a parameterized quantum circuit, and your loss is the expectation value. So the second part would cover variational algorithms, like, for instance, the variational quantum eigensolver, or VQE. Now, to solve this problem one efficient way, if your loss function is sufficiently nice, is our gradient descent algorithms. And here, given some initial parameters theta 0, we follow the direction of the negative gradient. So for these parameters that you have, you'll compute the gradient of the function and then multiply it with some small learning rate eta, and then follow it in the negative direction. And ideally, you'll just walk down the slope of your function and find the minimum of your loss. Now, this works nicely if your loss landscape is very, very easy to optimize. So here on the left, we have a simple example of a loss landscape, where in green you have the maxima and in pink you have the minima. We're starting at this point here, 2, 2. And you can see that the gradient descent function nicely follows the gradient, which is orthogonal to these lines of equal value, and you end up in the minimum, and then your optimizer stops. However, the loss landscapes can be a bit tricky. And if we take this exact same model, but we multiply all the parameters by a value of 5, then you see that the same algorithm that just worked very nicely starts here at this point 2, 2 again, but then starts to oscillate at the sides of the loss landscape and will never converge. Now, there are some heuristics how you could solve that by, for instance, modulating the learning rate and realizing, oh, okay, I'm oscillating here probably, so maybe I should make the learning rate smaller or larger. But I want to talk to you about a much more elegant solution to this problem. And to see how that works, let's first change perspective a little bit. So we can rewrite the gradient descent update rule, as you can see here on in this equation, as the minimum of this function here. If we solve this minimum, which we can do exactly, we just get back our gradient descent formula. But what's interesting now is that we get a better understanding of what the update step actually is doing. So on the left side here, we have this dot product, and you can see that this ensures that our update step, which is this theta without an index, will be anti-parallel to the gradient. And this is the idea of the gradient descent. We want to walk into the negative direction of the gradient. But you also see the second term here on the right side, which contains the learning rate eta. And this penalizes the update step in the sense that it controls how large we can make the update step. But you can see that this penalty that we have here on the right side, this is completely independent of the model. So no matter whether our loss is very sensitive to the parameters or it's not sensitive to the parameters, this doesn't change. And therefore, before we multiplied all our parameters by this constant factor of 5, this update step didn't change, and we still did the same steps as before, and these were way too large. What we can do now to resolve this problem is we simply change this metric. So we want a metric that, not like the Euclidean metric that we use here, is independent of the model. We want some metric that includes the model sensitivity. And this is what we usually refer to as a change from the parameters into the model space. And we can just do that by replacing the metric here from the Euclidean metric to this metric induced by the matrix G, which I'll talk to you about in a second. And we can solve this again exactly. And what we get is almost the same update rule, except that we now multiply the gradient with the inverse of this matrix G. Now, what is this matrix G exactly? Assume that we have 2 points in our loss landscape called theta 0 and theta 1. And from now on, we'll assume that our model is a parameterized quantum circuit. So the model is this state function psi of theta, which is prepared by a quantum circuit, which we call U, on the parameters theta. Now, before in the gradient descent rule, we just said, okay, theta 0 and theta 1, their distance is the Euclidean distance of the parameter values. However, we know that we have a model underlying our optimization. So what we can do now is we can replace this Euclidean distance by something which takes into account this model. And one very convenient metric is the fidelity. So instead of using the Euclidean distance, we now say, prepare my model once with the parameters theta 0, prepare it once with the parameters theta 1, and then the closeness of these 2 points is given by the fidelity. So if I take the overlap of these 2 quantum states, if the overlap is very small, so the model changes a lot, then the distance is large. If the model doesn't change a lot, so the fidelity is large, then my model does not change a lot. I hope I said that correctly now. Right, and with this, we include the sensitivity of our model in our distance measure, so that our update step, if the measure of closeness does not change a lot, we can make larger steps, and if it does change a lot, we can make smaller steps. And if we use this measure of closeness, the induced metric tensor is given by the formula that you can see below here, and this is also known as the quantum Fisher information matrix. And if we use this metric tensor as a precondition of our gradient, then this update rule is known as the quantum natural gradient, which was introduced by Stokes in 2019, reference here below. So now let's have a look at how this new quantum natural gradient and our plain old vanilla gradient descent, they compare. In the simple model that we've seen before already, both behave almost the same, but you can see already that quantum natural gradient takes a slightly different path. However, now if we multiply again our parameters by a factor of 5, then you can see that natural gradient descent takes quite a different path. And if we zoom in, you can see that actually the curve is almost the same as before. So it seems that natural gradient is indeed unaffected by this reparameterization, by this scaling of the parameters. And this indeed reflects a very important feature of the quantum natural gradient, namely that it is invariant under rescaling of the parameters. And also it takes into account the sensitivity of the parameters in different dimensions. So say, for instance, I have a parameter vector, and in one dimension, my model is very, very sensitive. So maybe I have a very narrow loss landscape. And in the other dimension, it is not sensitive at all. The natural gradient will take this into account, while the gradient descent won't be able to do that. And even if you modulate the learning rate, this won't work, because it's always a global learning rate on all the parameters. We can make this a bit more, we can tune this a bit more crazily and multiply the parameters not by a factor of 5, but now by a factor of 20. And you can really see here that the gradient descent goes completely crazy, while if we zoom in, the natural gradient still works like a charm. So why am I talking to you about that? If the natural gradient descent works so well, and that's already been done and introduced, what's interesting about it? So there's a catch. Namely, if we look at the definition of the quantum Fisher information, which we need to evaluate in each iteration of this natural gradient descent, we see that we need to evaluate these 3 expectation values. We can evaluate all of these with parameter shift rules, a linear combination of unitaries. That's not the problem. But this matrix is a square matrix of the dimension d times d, where d is the number of parameters in our model. And this means that the quantum natural gradient requires the calculation of d squared expectation values per iteration. And that might be fine if you have tens of parameters in your circuit. But if you look at larger models where we have hundreds of thousands of parameters, which are reasonable assumptions because we're moving to hardwares with 50 and more qubits, then this quickly becomes infeasible. Just to give you a sense of how bad the scaling is, if you would have a model with, say, 1,000 parameters, then 300 iterations with the quantum natural gradient would take about 133 days on our superconducting qubit devices that we have here at IBM. And you don't want to wait 133 days for natural gradient optimization. So our work tries to remedy these increasing costs in high-dimensional parameter spaces. And we're basing our work on the idea of a simultaneous perturbation stochastic approximation, or SPSA algorithm. And the idea here is that if I'm interested in a gradient of my function, instead of perturbing or instead of computing the gradient in each dimension of my parameters individually, I'm just going to select one random direction, which I'm going to call delta. And I will do a fine difference approximation of my gradient in this direction and then multiply it with this direction. So in the formula, you would take a small perturbation, you would take a random direction delta and a small magnitude of your perturbation epsilon, and then just perform a fine difference perturbation. So this first term here, the scalar value, where you only need 2 function evaluations, and then you multiply it with the direction. And that then is your approximation of the gradient. So note that the gradient would take a linear number of evaluations, whereas this on the left side now only takes 2 function evaluations, and that's independent of the number of parameters. And if some conditions are satisfied, which are shown, which are included in the paper below, then you can show that SPSA is an unbiased estimator of the gradient, and it will converge into the same conditions as the normal gradient descent. Now, how can we use this for the quantum Fisher information? So our work here consists of 2 steps. Step number 1 is that we need to generalize SPSA, which has first been introduced for gradients, to Hessians. And fortunately, that has already been done. So let's summarize quickly what the idea here is. This algorithm called the 2SPSA is based on a nested finite difference approach. So we've seen before that if we take one random direction, we can approximate the gradient. Now, if we add a second direction in which we perturb, then we can estimate the second derivative, which is the curvature, and gives us the Hessian. So the idea here is, again, that we have in blue here a scalar value that gives us the second derivative at this point with a nested finite difference approach. And then we multiply it with the direction. The direction here is not a vector anymore, but it's a matrix. So this is going to be the symmetrized outer product of these 2 directions in which we perturbed. It's symmetrized because we know that the Hessian is symmetric. So we want our stochastic estimate to reflect that. Just to show you again how this would look like in a more visual sense, you multiply the scalar value, just blue, which takes now not 2 function evaluations, but 4, because we have 2 directions in which we perturb. and we multiply it with this matrix of plus and minus ones. And this gives us an estimate of the Hessian. Now, a very natural question to ask is whether this is a good estimate. And if you're interested in the actual value of the Hessian, then it is not a very good estimate. Assume you have a model with thousands of parameters, then your Hessian is a 1,000 by 1,000 matrix, and you estimate this only with 4 function evaluations. That's not going to be good. However, we're not really interested in the exact value of the Hessian. We want to find the minimum of our function. And for that reason, we don't need the exact value. And secondly, there are some techniques with which you can improve the estimate that you have. So the first one is to do a resampling of your Hessian samples. So you don't only take 2 directions, but you take 2 directions many times, and then you average over all these estimates. And this gives you a systematic Monte Carlo style improvement of your estimate. Secondly, since we're not really interested in the Hessian, actually, we can do some kind of moving average where we start with some initial guess for the Hessian, which we'll usually just take as the identity, because that just gives us the normal gradient descent update step. And then in each iteration, we sample once or a few times, and then combine that with all the previous samples into a estimate. On top of that, we know that the Hessian must be positive semi-definite, so we can ensure that feature with the transformation that you can see here below. Now, this was step 1. We generalized, or we showed you how we can generalize SPSA for Hessians. What we can do now is we can rewrite the QFI as a Hessian. And you can just do that as the Hessian of the Fubini study metric. And if you have that, you can approximate the Hessian with a constant number of function evaluations, and you can write the QFI as a Hessian. That means that you can get a sample for the QFI in a constant number of function evaluations instead of a quadratic number. The algorithm that combines all of these features together, we call that quantum natural SPSA. Quantum natural from the quantum natural gradient and SPSA, because that's how we calculate the gradient and the quantum Fisher information. And the idea is that, like in a normal quantum natural gradient, you start from some initial point. Then instead of calculating the gradient exactly, you take SPSA for that, which costs 2 function evaluations. And then you compute the quantum Fisher information with 4 function evaluations, and then you solve for the update step, which gives you a total of 6 function evaluations per iterations, independent of the number of parameters compared to the order of d squared. And that means that our algorithm only takes a constant number of function evaluations per iteration, which is a quadratic improvement. So let's look at some examples. At first, we simulated we looked for the ground state of a classical Hamiltonian, where we put poly Z on 2 qubits in the middle and use this hardware efficient poly 2 design circuit, which consists of random poly rotations and ZZ entanglements. And then on the right, we compared the vanilla standard gradient descent in the dashed blue line, the quantum natural gradient in the dashed green line, and the stochastic counterparts, SPSA and Q and SPSA. And you can see 2 things. Firstly, really SPSA seems to be an unbiased estimate of the gradient, because the vanilla gradient descent and the SPSA really do seem to coincide exactly. Secondly, you can see that the Q and SPSA seems to approach the quantum natural gradient, and that at the fraction of the cost. We also observed that it doesn't coincide with it exactly, and that's explained in our paper, and is most likely due to the regularization that we add, which acts as an interpolation between the quantum natural gradient and the standard gradient descent. So now what's interesting is that with more qubits, which was a huge problem before, we can scale this problem up, look at larger models, and this is not a problem for our algorithm anymore. So if we take the same example as before, and we increase the size to 22 qubits and obtain a 132 parameter circuit, with the quantum natural gradient, this optimization with 300 steps would take 2.6 million expectation values, which would take roughly a day or 2 to evaluate. Whereas with our algorithm, the Q and SPSA, we only need 2100 iterations, 2100 expectation values. which takes about an hour or two. And this is really the strength of our algorithm. We also looked at an example on real hardware, where we prepared the ground state of the lithium hydride molecule with a bond distance of 2.5 angstrom on 4 qubits and with 25 polygroups. We used the answers that you can see here on the bottom left, and then we compared the performance of SPSA and QNSPSA on the IBM Q Montreal system with Qiskit runtime. And you can see here that our algorithm performs better than SPSA, so we get this quantum natural gradient advantage, and we reach the target accuracy plus some offset due to noise, which we can get rid of with, for instance, zero noise extrapolation much faster and more reliably. Now, one thing that I'd like to point out with this algorithm is that the overhead of the quantum natural SPSA becomes smaller and smaller with the number of Hamiltonians and the number of polys that you have to evaluate in the cost function. So in the first example that we've seen, we had a diagonal Hamiltonian. That means to evaluate the cost function or to evaluate the energy, we only need to measure in one basis. So SPSA needs 2 function evaluations for the gradient. That means we have 2 function evaluations in total for each iteration. Our algorithm, the QNSPSA, takes 4 more function evaluations, so we have 6. And here you can see that, okay, this is still a 3-fold increase in the number of functions evaluations. However, if we look at a molecular Hamiltonian, which has maybe n non-commuting polygroups, then you need to measure n times for each energy evaluation. That leads to 2n function evaluation, 2n circuits per iteration for QNSPSA, for SPSA, while for QNSPSA we only need 4 more, and that becomes a negligible overhead if n is large. And in the lithium hydride example, SPSA took only 50 SPSA took 50 circuits, while we only took 54. And with the faster convergence, our algorithm was really more efficient. But other example that I'm very briefly going to touch, because I'm already a bit over time on, is our quantum Boltzmann machines. So you can show that the quantum natural gradient coincides with variational imaginary time evolution if the loss cost function is just the energy, and then you can use this imaginary time evolution with our cheap evaluation of the Fisher information to prepare Gibbs states. And Gibbs states are interesting because you can do a bunch of machine learning tasks with them, like generative learning or classification. Some open questions about our work are, for instance, what the performance is in comparison to other optimizers, like, for instance, Adam. And one big drawback of our algorithm is that you have to double the circuit depth or width to compute the overlap. Right. And also one very interesting question is if we can select the number of resamplings adaptively so that we get an optimal convergence. And with that, thanks a lot for your attention. And if you have any questions, I'm happy to take them.
Okay, thanks very much. Those are some really impressive results. Okay, thanks. So Yusuf has a question. So he says, can you refer to the work on Hessian approximation? And then he...
Sorry, can I refer to what?
On Hessian approximation. I'm not sure which one that refers to.
He posted the link. Do you mean... So yes, this uses the SPSA work. I can open the link again. Oops. So if you want to look up how this works, well, you can look in our paper where we explain exactly how it works, or you can look at this paper by Spal from 1997, where this is introduced for the first time. I hope that was the question.
Yeah, I think that was indeed a question. Does anyone else have any questions? Okay, well, maybe we should wait for a few more minutes for people to think of questions.
Right. So maybe while there are no questions, I can talk a little bit more. Quantum Fisher. So this quantum Fisher information, it's when we motivated it via quantum natural gradients, but it actually is a quantity which appears a lot. For instance, also in variational time evolution. So both for real and imaginary variational time evolution, we have to evaluate this quantity in every iteration. And if we really want to do real-time evolution or imaginary time evolution on near-term devices that we have today, we have to find some way around that, this expensive evaluation. And this could be one possible path, or maybe you can also use some, I mean, there's other work on projected time evolution, which could also work. But both evaluating like the Trotter step, which is the usual approach, is not feasible for real-time for near-term devices. And also the full calculation of the Fisher information is not something which is feasible, not because the circuits are too deep, but just because it takes way too much time to evaluate all of them.
Do you know of any other ways to approximate the quantum Fisher information besides the one that you have?
There are diagonal and block diagonal approaches. So you just don't compute the full matrix, but just the diagonal or block diagonals. And these also require less circuits. However, you don't capture the parameter correlations properly because you only do diagonal approximations. So you won't get the full advantage of the quantum Fisher information.
Mm-hmm. Yeah, great. So I guess your technique will be useful in cases when like you do want to capture these correlations and you care about the computation or like the computation time for the Fisher information. Yeah.
Well, it's an interesting question when you might not care about the parameter correlations. In that case, maybe these block diagonals are a good approach. However, you could also speed up these block diagonal approaches with SPSA because then you just perturb on smaller blocks.
Yeah, that would be super interesting as well. Okay, I think that with that we come to the end of our session. Thank you to all the speakers for the wonderful talks, and thank you all of you for attending. So yes, I think that is all. Thanks very much.
Well, thank you everyone for the great talks. Thank you, Yui, for chairing the session. So we are closing now. Don't forget we have the poster sessions tomorrow. So if you want to check out the posters, we have 40 posters altogether. So see you tomorrow, I hope. Otherwise, have a nice day in Europe. I'm closing the Zoom session now. Thank you. Thanks a lot.
Bye-bye.
Bye-bye. Thanks, everyone. Bye.